Good morning everyone. I hope everyone's doing well, and today is the day that I'm doing 100 integrals in a single day. So, super exciting. I did a few different sections, and we'll go through them. So I think the first 20 are like just a mix of integrals. The next 10 are some tricky integrals that were given to me by my first year maths lecturer, Harry Wiggins. Then I have, I think, 20 more just mixed bag integrals, a mix of everything. Then I'm doing 15 stats integrals, so all the different distributions and stuff. And then I'm doing 15 more mixed bag random ones. And the last 20 are really hard, so from 81 to 90, those are like famous integrals. So Gaussian, there's a bunch of other tricky ones in there. And then we have the last 10 are some double integrals. And then there's a special 101 from Mr. Jason de Villiers, so you'll see that right at the end. So, before I start, I just want to shout out the company QLess from Becker. He was kind enough to sponsor the video a little bit. So he's starting an app. You can check it out in the App Store. It's spelled, let me write it on the board. It's spelled QLess, and it is basically an app where you can basically get food and connect, and you don't have to queue, and it's really cool. So you guys should check it out. So without further ado, let's get started. So, question number 1. We are doing the integral from 0 to pi of 1013 times sine of x dx. Okay, integral number 1. We can see 1013 is a constant, so we can take that out, so it'll be 1013. And the integral of sine is negative cos. So let's put that in square brackets. Negative cos x from 0 to pi. Okay, 1013, let's sub in our bounds. So we know that cos of pi is negative 1. So negative 1 will give you 1. And then we're going to do minus. And we know that cos of 0 is 1, so it'll be minus 1. So basically we get 1013, and that'll be 1 plus 1, so times 2, which will be 2026. Very cool. I thought I'd make the first answer quite a fun one, matching up for the year. So yeah, that's the first question. Okay, let's move on. Quite an easy one to start off with. Let's move on to question 2. Okay, so question 2 is the integral of sec x dx. So we know that secant is 1 over cosine. Okay, so to do this integral, we're going to do something quite interesting. We're going to multiply by something. So I always think of sec and tan as like friends. So you often want to like kind of include both. So what I'm going to do is I'm going to multiply the top and the bottom here by sec x plus tan x. Cool. So we can multiply by this, because it's kind of just like multiplying by 1. And we're going to get then, we'll get the integral of the top will be sec, oh, it should be not sec, sec. So, sec, there we go. So at the top we're going to get sec squared x, sec x times tan x will be plus sec x times tan x, all divided by sec x plus tan x dx. Brilliant. Okay. What do we do from here? We're actually going to do a u substitution. Okay. So I'm going to let u equal to sec x plus tan x, and you'll see why. So I'm going to say, let's just shift the camera a little bit. I'm going to say let's let u equal to sec x plus tan x. Okay. And now we can do the derivative of this, so du. The derivative of sec is going to be sec x times tan x. So it'll be sec x times tan x. And the derivative of tan x is going to be sec squared x. Okay. Dx, don't forget that. All of this dx. Okay. Now, we can see that, let's get another color. Let's get purple. Now we can see that this is basically that and that. So that whole top thing is going to basically give us our du. So now we can see that it's just going to basically become the integral of 1 over u, because the bottom is u, du. Okay, pretty cool. And we know the integral of 1 over u, pretty standard, it's ln of u. That's going to be the natural log of the absolute value of u. Natural log of the absolute value of u. Yeah. Cool. And now what we can do is we know that, let's move this here. We know that u is equal to sec x plus tan x, so we can just make this equal to the natural log of the absolute value of sec x plus tan x, and we mustn't forget our plus c. And that is going to be our final answer. Cool, 2 down. So what is this? Okay, what do we have to install for number 3? So, number 3 is the integral of the square root of 1 plus 1 over x dx. Okay, so first thing we should do is maybe make it one fraction. Okay, so it'll be x over x, so it'll be integral of the square root of x plus 1 over x dx. Okay, and now maybe we can split it up into like the square roots of the top, square roots of the bottom. So it's going to be the integral of the square root of x plus 1 over the square root of x dx. And now we're going to do a u substitution. So I'm going to say let's let u equal to the square root of x. You'll see why. Okay, so if we let u equal to the square root of x, we can solve for x, so we square both sides. So then we're going to get x is equal to u squared. Okay, and then what we can do is we can do the derivative. So dx is going to be the derivative of this, which will be 2u du. Okay, brilliant. So now we have dx. Oh, we should probably find what that top is as well. So we want the square root of x plus 1. So we have x, so we can add 1 to both sides. Then we get x plus 1 is equal to u squared plus 1. And then if we square root both of them, square root of that, square root of that. So we get this square root of x plus 1 is square root of u squared plus 1. Okay. So we get our overall integral to be the integral of that thing, which is the square root of u squared plus 1 over square root of x, which is u. And then dx is times 2u du. Okay, cool. We see something quite nice here. The u at the top and the u at the bottom cancel, so we kind of cancel that with that. Okay. And that means that we can make this equal to, let me move my chair down a little. We can make this equal to, take the u2 out, so it's 2 integral of the square root of u squared plus 1. Okay. Now this is the tricky bit. So we're actually going to do a trig substitution here. So what I'm going to say is I'm going to say let's let u equal to tan of theta. And you'll see why. Okay. So often we have like x squared plus 1 or 1 over x. We often do trig substitutions. So we're going to say let u equal to tan of theta. And then I'm going to do the derivative in terms of u. And okay, let me try. See in the chat, we're going to zoom in on the whiteboard a little bit. So let me try, maybe move my desk a little bit closer. I'm going to try that. Let's see if that helps. Okay. Hopefully we can see maybe the board a little bit clearer now. Desk a little bit closer. Okay. So we said u equal tan of theta. So then the derivative of tan of theta we said earlier was sec squared of theta. Awesome. Okay. So now let's put in the substitution. So d theta, sorry. D theta. Yeah. Okay. So now we get our integral is 2 times the integral of the square roots. We know that u squared is going to be tan of theta squared, so I'm going to say tan squared of theta plus 1, and there should be a du, and du is sec squared d theta. Okay, brilliant. Let's have a look what we can do here. So now we have 2 times the integral. And we know that tan squared of theta, so I always remember the thing 1 with a tan is sexy. So this actually becomes sec squared of theta. Okay? So we basically get, and we have the square root of sec squared of theta, so the square root cancels out the square, and it'll become sec of theta times sec squared. So it becomes sec cubed of theta, d theta. Awesome. What should we do now? Sec cubed of theta. Let's think. So I think what we should do here is we should split it up. So we can split up into 2 times the integral. So it seems a little bit weird, but we often do it when we have like powers of trig things. So I'm going to split it up into sec theta times sec squared of theta. D theta. I just got a very nice message from my girlfriend, so thank you to her for that lovely message. Okay, so now we split up into this, and now we're going to do integration by parts. We're going to do a lot of like these trig integrals, so you'll see this is actually quite a common technique. So I'm going to say, let's let u equal to sec of theta, and then du is going to be sec theta times tan theta d theta. Yeah, that's it. And then so that's du. And then we're going to say let's let dv equal to sec squared of theta d theta. And then we have to do the integral of this, right, for integration by parts. So the integral of sec squared, because you know the derivative of tan is sec squared, so the integral of that will be tan of theta. Okay, so now let's see what we have. So we basically have, we're running out of space. Okay, I'm going to erase, and I'm just going to put where we are so far. So I'm going to keep our original integral. I'm just going to erase this. Yeah, let's erase like this. Let's erase this. Okay, so we had the integral. We got it to be the integral of sec cubed of theta, d theta. And then we're doing this u substitution. So it's going to be u times v. So it'll be sec theta times tan of theta. Theta times tan of theta minus the integral of v, v du. Okay, so v is tan of theta and du is that. So we can see it's going to be sec of theta times tan squared of theta d theta. Okay, let's see if this makes our lives any easier. So we know that tan squared of theta is 1 minus sec squared of theta. Okay, so we can change this into, so it'll be sec of theta times tan of theta minus the integral. So if we multiply this in, it'll be the integral of sec of theta minus the integral. If we multiply it in, it'll be So it'll be minus minus, I think it becomes plus, because you have a minus here. Sec cubed of theta, that should be d theta. Okay. And let's see what we have here. We have the integral of sec cubed theta d theta. Okay. So what do we notice about this? I notice that we have, I notice that that and that are exactly the same. Okay. Interesting. Right? Is this a plus? Oh, wait. I did this wrong. This is supposed to be sec cubed of theta minus 1. So then I think this one would become plus, and this one would become minus. Yeah, there we go. Okay. So now what we can do is, you see these are the same. So I'm just going to call this, let's call this integral I. Okay. And then if I move it across, we're going to get, that's I and that's I. So it'll be 2I. So let's just wipe off our integration by parts. And we're going to get 2I is equal to sec of theta times tan of theta. And then we know that the integral of sec of theta from earlier was ln of, we know it was ln of sec theta plus tan theta. Theta, absolute value, okay. So now to find I, what we can do is, I think, are we on the right track? Yeah, we got that, but I think this was equal to 2 times it, right? Yeah. So it was 2 times that. So basically, okay, so let's just do it recap. So we have 2I, so now our integral, which is just the integral of sec cubed, will be that all divided by half, but we had 2 times it anyway, so that's where we are so far. So that's good, okay. So we've kind of found the integral, but now we need to convert back to x world, right? Because we're now in theta world, which we don't really want to be. So what we can do is, let's just remember what our substitution was. We said that u is equal to tan of theta. That was our substitution, right? Okay. And we know that our other substitution was u is equal to the square root of x. Okay, so those are substitutions, right? So now let's convert back to x world. So we're going to have to draw a right-angled triangle. So let's draw that. I'm going to draw here. So boom, boom, boom. Right angle. This angle is going to be theta. And we know that tan of theta is this side, square root of x over 1. So it's opposite over adjacent, right? So now, using Pythagoras, we can find out that this side will be the square root of that squared, which will be x, plus that squared, which is 1. Okay? So, overall, let's sub back. So overall, we get that the integral of the square root of 1 plus 1 over x is equal to tan of theta, which is, sec theta. And we know that sec is 1 over cos, so it's opposite of cos. So that's hypotenuse over adjacent. So it's going to be the square root of x plus 1 times tan of theta, which is just the square root of x plus the natural log of sec of theta, which is the square root of x plus 1 plus tan of theta, square root of x, absolute value, plus c. Oh, that was a long one. Very cool, very cool. Long integral, I hope you guys enjoyed that. So let's have a look at the next question. So that's our final answer. Hope you guys can see it. Yeah. Let's erase. Erase, yeah. Okay. Question number 4. How long have we been going for? 20 minutes? Not bad. Okay. Question 4. So it's the classic one. It's the integral of 1 over the square roots of a squared, so we keep it quite general, but a can be any number, so a squared minus x squared dx. Okay. So we're going to use this kind of like formulation or whatever you want to call it quite often. So yeah, I wanted to do it early. So it's another substitution. So I'm going to say, let's let x equal to a times sine of x. And this will lead to some nice cancellation at the bottom, okay? So if we do the derivative of x, it'll be a times the derivative of sine is cosine. So a times cos of x. Okay. So now let's sub in what we just did. So now this is going to be equal to the integral of 1 over the square root of a squared minus x squared, and x squared is a squared times sine squared x. Let's make this a symbol. Dx. Okay. So now what I'm going to do is I'm going to factor out the a squared out of the bottom. Okay. So that's going to be equal to the integral of 1 over square root. So factor out an a squared, so it'll be a squared. We're left with 1 minus sine squared x dx. Okay. And we know that 1 minus sine squared x, because of our identity, is equal to cos squared x. Okay. So now at the bottom we have a squared times cos squared x. They're both squared, so the square root will cancel it. And we basically just get the integral of 1 over a times cos of x dx. Okay, times, oh wait, I've got to sub in my dx. Also, actually, wait, I messed up. I should have written in terms of theta. Let's fix that quickly. Not too big. Sorry, okay. So what I should have done is, because I said, yeah, I wanted to do actually theta, just because I don't want to do the same letters. So theta, theta. Okay. So then our substitution will be theta. And instead of dx, we're going to write, let's see, d theta. So instead of dx, we're going to write a times cos of theta, d theta. So it'll carry through, so a times cos theta, d theta. And then it'll be same here, a times cos of theta, theta, cos of theta, d theta. And now let's see why this is such a nice substitution, right? Because you see we have the same at the top and the bottom, so they cancel out. And we basically just get the integral of 1 d theta. This is really nice because we know that this is just going to be equal to theta, okay? But now we obviously need to sub back in our assumptions. So we said that, let's write this in green. We said that x was equal to a times sine of theta. So if we have to solve for theta, I'm going to divide both sides by a, and then we're going to do the inverse sine to get rid of it. So therefore theta is going to be sine inverse of x over a. Okay, cool. So overall, let's write it, the integral of 1 over the square root a squared minus x squared dx is going to be equal to sine inverse x over a plus c. Good stuff, good stuff. Number 4. Okay, let's do number 5 next. Okay. Number 5. Let's do the integral of 1 plus e to the x all squared divided by e to the x dx. Okay. This one looks a little bit funky. Maybe you could think about a substitution or something, but what I think I'm going to do is I'm going to expand the top first. Okay, so let's square out the top. So it's going to be the integral of 1, multiply them together times by 2, so plus 2 e to the x times e to the x squared, so that'll be 2x over e to the x dx. Okay, and now I'm going to split this up into a bunch of integrals. So it's going to be 1 over e to the x, so that'll be e to the negative x. And then if I split this one up, the e to the x's will cancel, so it becomes plus 2, and then this one will just become plus e to the x dx. Okay, and now we can do this one quite easily. So we can split it up. We know that we'll kind of need to take out a negative, so it'll become negative e to the negative x, and then integral of just 2 is 2 to the x, or 2, not 2 times x, and the integral of e to the x is e to the x, so e to the x plus c. Brilliant, brilliant. Yeah, I think that's the answer for number 5. Not too bad. Okay, number 6 is going to be kind of like this one, except now I'm going to flip the numerator and the denominator. So let's see if it's easier or harder. Probably harder. Let's have a look. So number 6 is going to be the integral of, so now at the top we have e to the x, and at the bottom we have 1 plus e to the x all squared dx. Brilliant. So we could expand the denominator, but I don't think it's going to be so useful. So what I think we should do is we should use a u substitution. Okay, so I'm going to say let's let u equal to 1 plus e to the x. Okay, and let's see what happens. So then du is going to be the derivative of this, which will just be e to the x dx. Okay, so now what we're going to get after our substitution is going to be, yeah, that works out quite nicely, because then this part in purple is basically du. Yeah, so then it's basically going to be 1, the integral, of 1 over u squared du. Okay, and this is quite easy. We can write it as the integral of u to the negative 2 du, use the power integral thing, so we're going to add 1 to the power and divide by it. So it's going to be negative u to the negative 1. Okay, and then let's just sub back in what our u is. So we said our u is that. So it's going to be equal to negative 1 over 1 plus e to the x plus c. Brilliant. Whew, and that's number 6. Let's move on to number 7. Okay, hope the board's clear and you can see everything. I'll try to move the desk a little bit forward, just that it's a bit clearer. So yeah, hope it's good. Okay, number 7. Integral of tan inverse of the square root of x dx. Okay, this is going to be another, what is this going to be? Let me have a look. Tan inverse. So I don't think we're going to do a substitution. I think it's integration by parts, because we can do, we can do the derivative of tan inverse quite easily. So let's let u equal to tan inverse of the square root of x, and then we can find that the derivative of that is going to be, so the derivative of tan inverse is, so we need to do chain rule. So the derivative of inverse tan of like x would be 1 over 1 plus x squared. So it'll be 1 over 1 plus, except whatever this is, so square root of x squared. Then we need to do the chain rule, so we need to do the derivative of square root of x. So that's going to be a half, x to the negative a half, which you can write as 1 over 2 root x dx. Okay, so that's going to be a u. And then we're going to, our dv is equal to dx. So then v, the integral of like 1, will just be x. Okay, so now let's do our integral is going to be equal to, so it's u times v, so that's going to be x times tan inverse of square root of x minus the integral of v du. So it'll be x times, so that'll be 1 over 1 plus x times 1 over 2 square root of x dx. Okay, brilliant. what can we do here? So we can take out the half, because that's a constant. Maybe it's an actually. So we can say it's going to be x times tan inverse of the square root of x. So I'm taking out this half, so it'll be minus a half, and let's multiply together. So it'll be integral of x over square root of x times 1 plus x dx. Okay. Now, I kind of don't want the square root of x at the bottom, so what I'm going to do is I'm going to multiply it by 1, which is like a fancy one, so square root of x over x, and that'll cancel, kind of remove the bottom a little bit. So, let's see what we get here. So now we're going to get x times tan inverse of square root of x minus a half. So now the top will be x root x, and square root of x on square root of x will give us x times 1 plus x dx. Okay, that's quite nice, because now this x and that x cancel. Okay. So, what should we do now? Let me think. Often you have square roots, you do a u substitution, so let's give that a go. So let's let u equal to square root of x, and then du, the derivative of this will be, this is looking quite nice. Let's make it easy for ourselves. Instead of doing du, let's do dx. So then let's say x will square both sides will be u squared. So that implies that dx is equal to 2u du. Okay. So then we can move up to the top here. So it's going to be x times tan inverse of the square root of x minus a half times the integral. So we said that square root of x is u, so it'll be u. And then it's 1 plus x. And we said that x was u squared. So it'll be 1 plus u squared. And then it's going to be times dx, which is 2u du. Okay. Well, firstly, we can see that the half and the 2 will cancel. So that will cancel with that. And then we can multiply the u's together, so we get x times tan inverse of the square root of x minus the integral, so u times u is u squared over 1 plus u squared du. Okay. Now we can use a very common trick. So it would be nice if we had like a 1 plus u squared at the top here, because then it would just cancel out with the denominator, right? Very nicely. So what I'm going to do is I'm going to add 1, but then we also have to subtract 1, because you can't. So those basically cancel out, but it allows us to do a nice little trick here. So now we have x times tan inverse of the square root of x minus, so the integrals, let's do this like first bit. So x squared plus 1 over 1 plus x squared will give us 1, right? So that'll be 1. And then we just have minus, so that's du. And then minus will give us a plus, the integral of 1 over 1 plus u squared du. Brilliant. Okay. Nice. So we can pretty much do everything now. So this is going to be x times tan inverse of the square root of x. We know the integral of u is going to, the integral of 1 is going to be u, because of du. And the integral of this is just, it's a very common one, it's tan inverse of u. Okay. We're going to be using this one a lot. So, okay, it's 1 over 1 plus something squared, like x squared, u squared, whatever the dummy variable is. So it'll be tan inverse of u. Okay. But we obviously need to sub back in, so we see that u is equal to the square root of x. So to get our final answer, we just need to sub that in. So it's x, let me write it down, we have a bit more space. So our final answer is going to be x times tan inverse square root of x minus u, which is the square root of x, plus tan inverse square root of x plus c. Awesome. And that is question 8. Sorry, question 7, yeah. Getting ahead of myself. How long we've been going for? Half an hour? Okay. Awesome. Okay, that was number 7. Okay. Oh, hey Julian, nice to see you in there. Hope you're doing well. Always nice to see the chat. Okay, number 8. So, question number 8 is, just a reminder, this is like a charity challenge. So in my, let me actually post it again. I'm going to post the link in my story. So if you guys are watching and you want to donate to CHOC, which is a childhood cancer thing, foundation, you can donate to them. Any donations would be really appreciated. So let me just I'm going to repost the link on my story. Let me just find the link. Here it is. Let me repost that on my story quickly. Text. Paste. Okay, so I've reposted the link on my story. So if anyone's watching and you'd like to donate to CHOC, yeah, that would be greatly appreciated. Awesome. So number 8 is the square root of 1 plus, or the integral of it. Integral of the square root of 1 plus square root of x dx. Okay, looks very scary, but we can do some nice u substitutions to make it a bit easier. So firstly, let's let u equal to 1 plus square root of x. Okay, so then what we can do is we can do du, right? So du, derivative of this is going to be half and x to the negative a half, so 1 over 2 root x. Okay, dx. I think it might be a bit better if we can solve for dx. So we just divide both sides by this. So dx is going to be 2 root x du. Okay, cool stuff. So let's sub everything in. So it's going to be equal to the integral. So we know that that's u. So it's going to be square root of u times 2. Ooh, this isn't looking too good. Du. Maybe there's like a nice trick we can do. We can make this into u using this. So then we can say that this is going to imply that the square root of x is equal to u minus 1. Okay, so now we can take out the 2. So we can say that this is equal to 2 times the integral of square root of u, and we have square root of x, which we said was u minus 1 du. Okay, so now we know that u square root of u is u to the half. So it's going to be 2 times the integral of u to the half times u to the 1 will be u to the 3 over 2. And then minus u to the half, just multiplying in du. Okay, and now we can just use the normal power rule. So it's going to be 2 times, you add 1, so it'll be u to the 5 over 2. Divided by 5 over 2 will be times 2 over 5. U to the 5 over 2. That'll be u to the 3 over 2, so it'll be 2 over 3, u to the power of 3 over 2. Yeah. Let's go up here. So then it's going to be 2. Let's actually multiply it in. So it's going to be 4 over 5. And let's sub back in our u substitution, right? So we said that u was 1 plus root x. So it's going to be 1 plus the square root of x to the power of 5 over 2 equal sign minus, so 2 times 2 over 3 is 4 over 3, and u is 1 plus square root of x to the power of 3 over 2 plus c. And I think that's our answer. Brilliant, number 8, cool. Let's erase this. Hope you guys are enjoying so far. It's lots of fun setting this up, so yeah, really cool. Okay, number 9. Okay, so number 9 we had fractions. So we have the integral of 1 over the square root of x minus 1 over this x minus 1 dx. Okay, so firstly, no one really likes working with like fractions over fractions, or especially I don't. So I'm going to kind of multiply this by square root of x over square root of x. Okay, so that should cancel out nicely with the bottom. So then that's going to cancel out with the square root, so it'll become the integral of 1 minus the square root of x over, and it'll be, should I multiply it in? No, let's just leave it out for now. So it'll be square root of x times x minus 1 dx. Okay. What can we do here? So it'd be nice if we could like cancel out with that top somehow. So we can actually see that x minus 1 is the difference of two squares, which seems quite weird because normally I don't think of x as like a square number, but it's kind of like square root of x squared. Okay. So we can kind of change this into the integral of 1 minus the square root of x over square root of x times what, so the x, so it'll be square root of x minus 1 square root of x plus 1 dx. Okay, and we can see that it's almost the same. If we take out like a negative, for example, then this will become negative, positive, then it's square root of x minus 1, then that'll cancel with that. Very nice. Yeah. Okay. So now what we get is we get the integral, let's put a negative out front, because we have the negative there, of 1 over the square root of x times the square root of x plus 1 dx. Okay. What should we do here? So let's do a u substitution for maybe this thing, because this thing looks quite tricky. So let's like make it more simple. So let's let u equal to the square root of x plus 1. Okay, and then du, let's just do the derivative of this. Yeah, du will be, it's a half square root of, yeah, it's x to the negative half dx. And that's quite nice because we see that if we combine, if we have a 2 here, so if we can just put a 2 here, if we multiply by like a half on the outside, then it cancels out. So then we can see that like 1 over 2 roots x dx, that gives us our du. So now what we have is we have negative a half, the integral of 1 over u du. Oh, classic. We're going to see this so many times today. Oh, actually, wait. I just realized we're dividing by a half, so this should actually be a 2, I think. Not a half, because we're putting 2 at the bottom. So this should be minus 2. Good. Okay. So then it's going to be minus 2. We know that we've done this before. Ln of absolute value of u. Let's go back up here. So minus 2 ln. We know that u is the square root of x plus 1. Okay. Absolute value plus c. And that is our final answer. Almost 10 down. Nice. Okay. Oh, I see Layla in the chat. Hello, hello. Okay. Let's do number 10. Number 10. Okay. Number 10 is another, looks kind of similar to the previous one. So it's the integral of x divided by 1 plus the square root of 1 minus x dx. Cool. So what we're going to, we could do a u sub. Would that help? I kind of want to get rid of the square root at the bottom. So what we could do is we could multiply by the conjugate of the bottom, which will, it sounds like a fancy word, but it basically just means you change this to a negative, and it basically makes it like a difference of 2 squares. So it becomes 1 minus the square root of 1 minus x divided by 1 minus square root of 1 minus x. Multiply the top and the bottom, so there's no problem there. And then we see that that's equal to, let's not multiply it actually. Let's just have integral of x times 1 minus the square root of 1 minus x divided by, and then when we multiply this in, it's just a difference of 2 squares. So you multiply the first things, which become 1, and then the last things become minus 1 minus x. So basically you multiply them together, so it gets rid of the square root dx. Okay, and now we see that it's going to be 1 minus 1, so we can see that that and like that are going to cancel, and it becomes minus minus, it becomes kind of like positive x, right? we see positive x at the bottom. And then we have a positive x at the top, so that and that will cancel. Brilliant. So now, we're just left with the integral, I'll split it up maybe, of 1 dx minus the integral of the square root of 1 minus x dx. Okay, very good. The first one's easy. The integral of 1 is just x. But now we've got to think about how do we do the integral of 1 minus x, okay? I think let's do a u substitution. Okay, yeah, let's actually do the u substitution now before we do that first one. I think it'll just be a bit cleaner. So let's say that u equal to square root of 1 minus x. Okay. Let's think about du now. So the derivative of this is going to be, let's actually do dx. No, I don't think it'll make it easier. So du, so that's going to be basically, so we have the square root of that. Maybe that's actually not, let's do it a different use. I think that's going to not help us actually. So let's do a different u substitution. So instead, let's do the u substitution, where u is just whatever's in the square root, so 1 minus x. So now du is equal to negative dx. So if we have a negative here, then we, negative, then we get our du's. I'll put a positive outside. Negative outside to cancel out. So the integral of 1 is just x. And the integral of this is going to be the integral of square root of u, now it's working nasty, du. Okay. This is nice. So now we can just say this is going to be x plus, so it's u to the half. So that basically becomes, we add 1 to the exponent, so it becomes u to the 3 over 2 times 2 over 3. Okay. And then we can just put it up here. We know that u is 1 minus x, so it becomes x plus 2 over 3 times 1 minus x to the power of 3 over 2. Hey, we are 10% of the way through. We've done our first 10 questions. Awesome, awesome. I hope you're enjoying so far. Let's keep cracking on. Okay, number 11. Okay, so we're doing some nice general ones now. So, what was number 11? So, number 11, we're doing the integral of sine of x to the power of n dx. Okay, so this might look a little bit weird, but we're basically doing like an integral of a general power of sine. So like it could be sine squared, sine cubed, any power. Okay, could even be sine to 100. So it's just like, it's probably going to be, we're going to come up with like a recursive equation. Okay. So similar to that other one where we did sec cubed, we're going to split this up into the integral of sine x, and then we're going to be left with sine x to the power of n minus 1 dx. Okay, and this is going to be useful because we can now use it for integration by parts. Okay, so I'm going to say let's let u equal to the second part, which will be sine x to the power of n minus 1. Okay, because we can't do the integral of it, so we're going to have to do the derivative. I'm blocking the camera a little bit. And then the integral of that, which will be du, is going to be, we bring down the power, so it'll be n minus 1 times sine to the power, n minus 1, and then we subtract 1 from the power, we're doing the derivative. Sine x to the power of n minus 2. Okay, that's going to be what we do for the u's, and then dv is basically going to be what's left, which will be sine x dx. Okay, makes sense, right? And then the integral of sine x is negative cos x. So we're going to put negative cos x over here. Okay, so let's even see if this helps us. So now what we get is that is equal to, so uv, so it'll be negative cos x times sine x to the power of n minus 1, okay, minus the integral of v du. So I'll take out this minus, it becomes plus let's actually take out the n minus 1 to the front because it's just a constant. So it'll be plus n minus 1 integral of cos x times sine x power of n minus 2. Okay. Brilliant. I forgot to do the chain rule here, I just realized. So I did that part, and then the integral of the derivative of sine x is cos x dx. I forgot that. Okay, that's going to help us because then when you do this, v du is going to be an extra cos. Now it's going to be a cos squared x dx. Okay, sorry about that. Yeah, forgot about that part. Okay, brilliant. So now we have that, and this is still tricky, but maybe we can, if we change it back to sines, maybe we can see a little pattern that's like a recursion. So we can change cos into 1 minus sine squared x, right? So let's sub that in and split it into integrals and see what we get. Okay, so we get negative cos x times sine x to the power of n minus 1, okay, plus n minus 1 times, so sine to n minus 1 times 1 will be the integral of just sine to n minus 2, sine x to the power of n minus 2 dx, plus n minus 1 times the integral. Now I'm going to multiply the other thing, I'm going to multiply that in. And we see something quite interesting, right? Because we have sine squared, first it should be a negative, I think, because we have the negative here. And then we get sine squared times sine to the n minus 2. So we actually get, basically, sine x to the power of n dx, because you add the exponents, so it's n minus 2 plus 2. Okay. And a similar trick to before, this, if we call this I, then it looks really similar to that, right? Which we can also call I. So it seems like we kind of have like almost like a little repeating pattern. Okay. So I'm going to do similar to before, and I'm actually going to move this kind of like to the other side of the equation. Okay. So we're going to get, so we're going to get I minus n plus 1i, right? So double check I'm not making any mistakes here. So it'll become, okay, let's just write that. So you basically get I minus ni, well, it becomes plus actually, because we're moving across. So plus ni, and then that'll become plus minus, so minus I. Okay, let's see what that's equal to. That's equal to everything else basically. So it's equal to negative cos x times sine x to the power of n minus 1 plus n minus 1 times the integral of sine x power of n minus 2 dx. Okay, and we can see that that I and that I cancel. So now we're almost there. So now all we have to do is we have to divide everything by I. So I'm going to say I is equal to negative 1 over n cos x times sine x to the power of n minus 1 plus n minus 1 over n times the integral of sine x to the power of n minus 2 dx. Brilliant. So, and let's just reiterate that when I said I, I'm basically talking about our original integrals. I is the integral of sine x to the power of n dx. Awesome. So basically we now found a recursive expression to basically like reduce the powers each time. So we started with sine to the it might seem a little bit like unsatisfactory because our answer still has an integral in, but basically it still lowers the powers. So it's kind of like a recursive way to figure it out. Okay, that is number 11. Okay, let's do number 12. So number 12, it's another general integral of like a trig thing. So we're going to do it. Last one was sine. Now we're going to do of tan x to the power of n. Okay. So we're going to do a really similar thing, except now we know like tan and sec are friends, and we know like tan squared and sec kind of go together. So instead of splitting it up into like tan times tan to the n minus 1, we're going to take out a tan squared. So it's going to be integral tan squared x times tan x to the power of n minus dx. I'm a bit sloppy with my notation. N minus 2 dx. Okay. But we know that's what is tan squared, right? We already used this like property. So tan squared is sec squared minus 1. Okay. So we're going to say that this is sec squared x minus 1. Okay. So let's split this up into the two integrals. So we basically have the integral of sec squared x times tan x to the power of n minus 2 minus the integral. So now I'm going to do this, multiply negative 1 by that. So it's just going to kind of stay the same. So it'll be tan x to the power of n minus 2 dx. Okay, that seems quite nice. And now we can do a u substitution here, because if we let u equal tan x, the derivative of tan x is sec squared x. So we kind of have the derivative in front. So let's let u equal to tan x, and then du will be equal to sec squared x dx. And we see that, I'm drawing my dx's naughty. Okay, so that's going to be equal to, so that and that will give you the du. So it's going to be the integral of u to the power of n minus 2 du minus the integral of tan x to the power of n minus 2 dx. Okay. I see Matt Northing in the chat. How are you doing? Thanks for the message. Hope you're doing well. I don't know if you like integrals, but I hope you're just enjoying the vibes anyway. Okay, so let's keep going. So this is quite an easy one. We can do this using the power rule. So we can basically just add 1 to that and divide by it. So we can say it'll become u to the n minus 1. We can times it by 1 over n minus 1. Minus integral of tan x to the power of n minus 2 dx. Awesome. Okay, so now what we can do is we just need to sub in our u sub we just need to sub back tan x for u, and then we're basically done. So that is going to be 1 over n minus 1 times tan x to the power of n minus 1 minus the integral of tan x to the power of n minus 2 dx. And plus c, can't forget that. Good. So you can see again, we end up with like another integral, but it's like tan to the power of n minus 2, so it kind of gets rid of the power, so you can just like iterate this thing, and yeah, you'll be good. Brilliant, that's question 12. Oh, 1 hour into the video, 1 hour into the stream. Hope everyone's enjoying, all 6 of you. There's actually more people than I thought, honestly. I thought I'd just have maybe 1 if I'm lucky. Okay. You guys are probably tired of tricks, so let's do something else. Let's do question 13. Let's do the integral from -1 to 5 of an absolute value, which is quite cool. Absolute value of x minus 3 dx. Good. So we could break it up into parts and like do it based on that, but I think an even nicer way to do it is doing it with pictures, because when you think of an integral, it's literally just the area under a curve. So if we can draw this curve, we can work out the area. It'll be brilliant. So let's draw what the absolute value of x minus 3 looks like. So absolute value of x minus 3 is just an absolute value graph, which is like that V shape, but we're shifting it to the right 3. So it's going to look something something like that. This is going to be a 3. Okay. Let me get my, let's use green. So we're basically going from -1, so I'll say this, this is -1, and then we're going up until 5. So let's say that's 5. Okay, we're trying to find this area, so let me shade it in. Find that area there. Okay. I think that's Aaron, Reese Aaron in the chat. Hello, hello, hope you're doing well. Hope you like my beautiful picture. Let's keep going. So we're basically trying to find that area. So it's basically just 2 triangles, right? So it's actually not too hard. So we can basically say that it's going to be the area of that triangle. Everyone knows the area of a triangle is half base times height. So that's going to be half. This base is -1 to 3, which is 4. And then the height, let's actually see what the height is here. So it's at -1. So if you sub in -1 here, it'll be -1, -3, so -4. The absolute value of that will be 4. Okay, so the height is 4. 4. So that's that triangle, plus half base of this triangle is 2. And the height of that, let's see what it is. So if we sub in 5, we get 5 minus 3, which is 2, absolute value. So that will be, this point here, for example, will be at x equals 5, y equals 2. Okay, let's sub in 2 here. Okay, we need to work this out. So it's 16 halved is 8, 4 halved is 2. Our overall answer is 10. Nice. So that's like quite a cool integral because sometimes when you do integration, you actually forget that integrals are an area under a curve. So yeah, sometimes it's nice to actually draw the curve and do the integral of this. Nice. Let's move on to question 14. Okay. So question 14 is the integral of 1 over square root of e to the x dx. Okay. We can write this in a bit of a better way. So instead of writing it like a weird fraction, we can just change the power. So you can rewrite it as the integral of e to the, so we know square root is e to the like half, but it's under the denominator. So we can write it as negative a half x dx. And that seems really nice, right? Because we want a negative a half at the front, because then that's the derivative of the top. So then to cancel that out, we need a -2 here. So we can say that's going to be equal to the integral of -2 times e to the negative a half x plus c. And then if we want, we can rewrite this maybe back like in the square root form, because maybe you don't like negative exponents. So we can write it as -2 over the square root. Let's write that answer. Square root of e to the x plus c. Cool. Number 14, not a quick one. Okay. Number 15, let's get it. Okay, another trick one. So number 15, we have the integral of cos squared of 2x dx. Okay, how do we do this? So hopefully some of you guys, so we have this nice identity we can use. So we can use this identity, cos squared of like theta, for example. It's just going to be a half times 1 plus cos of 2 theta. Okay, you can see that's going to be really nice because then you can just sub this in here and then it's going to simplify it a lot. So in our case, theta is 2x, okay? So we need to be careful because it's going to be 2 times 2x, okay? Integral of, let's take out the half to the front, and then it's going to be 1 plus cos of 2 times 2x, which will be 4x dx. Okay, we can already see this makes it a lot simpler, right? So what I'm going to do is now I can just do the integral of this like normal. So it's going to be a half integral, this is 2, integral of 1 is x, integral of cos of 4x. So we know that integral of cos x is sin x, but we have to do like the reverse chain rule. So we need to divide by the derivative of the inside, which is 4. So we need to say plus 1 over 4 sine 4x. Okay, and then just multiply in, final step, so it'll be x over 2 plus 1 over 8 sine of 4x plus c. Brilliant. And that is number 15. Okay. Number 16. Okay, let's do the integral of x times sine squared x dx. Cool. So again, we're going to use another trig identity. So we know that sine squared of x, we can rewrite this as a half of 1 minus cosine of 2x. Yeah. If you really want, you can prove this thing using like the cos of 2x is equal to, I think, is it cos squared x minus sine squared x, maybe it's the other way around, and you can just like rearrange it, you can get this identity. Okay, so let's use this identity by subbing it in. So we have a sine squared x, so this is basically going to become the integral of x, let's take out this half, so let's put a half at the front, x times 1 plus 1 minus cos of 2x dx. Okay. Hope everyone's happy with that. So now what we're going to do is I'm just going to kind of multiply the x into the brackets and split it up. Okay. So it's going to be a half. Let's use square brackets. We're going to have like lots of integrals. Integral of x dx minus the integral of x times cos of 2x dx. Square bracket. Okay. Hope everyone's happy with that. Actually, let's just leave this negative inside, it'll be fine. Okay. So now we're going to use something called the DI method. So it's basically like, it's whenever you need to do integration by parts. But if you need to do it like lots of times, it's often like nice and quick to use this. Okay. So I'll do it here. So DI, so D is what you differentiate and I is what you integrate. So what we want to differentiate is our negative x, because it's going to kind of reduce powers and it basically becomes 0. And then once it becomes 0, we don't need to do anything. And then we'll integrate the rest. We'll integrate cos of 2x. And remember you have to do plus, minus, plus. Okay, so if you haven't seen this, there's a really good video by Black Pen, Red Pen. He does a nice explanation of this. So the derivative of negative x is negative 1, and the derivative of constant is 0. Now let's do this side. We have to do the integral, remember? Integral of cos of x is sine of 2x, where we need to do the reverse chain rule, so times by half. And then we need to do integral of sine, which is negative cos of 2x, and then half, and we have to times by another half, so it'll be a quarter. Okay. And then to do the integration by parts, you basically just multiply like down diagonally, like this. So we basically get that this is equal to, okay, well, the first one's easy. So integral of x is half x squared. Half x squared. And then plus, and then basically what we're doing is we're doing the integral of this, which will be negative, it'll be negative x times a half. So let's put that in front, so it'll be minus actually. So minus half x times sine of 2x. And then we do that times that, but remember it's negative. So basically it becomes negative, 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 so it becomes minus a quarter cos of 2x. Brilliant. Okay. Now all we need to do is multiply by half and then add our c and then we're done. So it's going to be equal to 1 over 4 x squared minus 1 over 4 x sine 2x minus 1 over 8 cos 2x plus c. Brilliant. It's Luke Cable. That's what he said. And this is the sole reason for studying AXA, right? Yeah, definitely. Just doing 100 integrals on a Thursday afternoon, or Thursday day, basically. It's going to take me the whole day. I wonder how long. So I've been going for an hour. It's number 16. Maybe take me like 6 to 8 hours, 6, 7 maybe. Okay, cool. And I think that's the answer. Yeah. Good stuff. Let's keep going. Okay. Number 17. Okay. So, number 17 says the integral of 1 over the x squared times the square root of x squared plus 1 dx. Okay. What are we going to do here? So we're actually going to use like quite a... let me think. What do you want to do? It would be nice if we had like the derivative at the top. So maybe what I'm going to do is x squared. I'm going to factor out like an x squared from the square root. So it'll be like x squared, and then if you say x squared divided by x squared will be 1, and then 1 divided by x squared will be plus x to the negative 2 dx. Okay. And we can see that that is kind of going to cancel, that the square root is going to cancel that. And then it's just going to be an x, so it's going to be x times x squared, which will be x cubed. So it'll be the integral of 1 over x cubed times the square root of 1 plus x to the negative 2. Make that longer, dx. Okay, and then this is going to look really weird, but what I'm going to do is I'm basically going to move this x to the top, because then it's going to be like in the nice form that we want. So it'll be x to the negative 3 over the square root of 1 plus x to the negative 2 dx. Okay, and now you'll see why I did all of this, because we can do a really nice u sub. So we can say, let's let u equal to this bottom thing in the square root. So it's let u equal to 1 plus x to the negative 2. So then du is going to be minus the power divided by it. So it'll be negative 2x to the negative 3. Yeah. So now you see x to the negative 3 is what we have here. So we just need a negative 2 here for that to be equal, dx, sorry. Yeah. So now we just need a negative 2 here. So we can put a negative 1/2 here, and then that just cancels out nicely. So, yeah, that looks good. So then what we can do is it's going to be negative 1/2 integral of, it'll be 1 over square root of u, so we can write that as u to the negative 1/2 du. And let's move up to the top here. So that is going to be negative 1/2. We can just use the power thing, so we add 1 to the power and divide by it. So u to the 1/2, and if you divide by 1/2, it's timesing by 2, so times 2. Okay. That is going to cancel nicely with that 1/2. Okay, so we just get basically negative u to the 1/2. So that's going to be negative, and we know that u is that, so it's going to be negative the square root of 1 plus x to the negative 2 plus c. And that is our final answer. Cool. Yeah, very nice. Number 18. I think at number 20 I might have a little water break. And just a reminder for anyone watching, this is it's like a charity challenge. So if there's any new viewers, I'm raising money for this charity called Chalk. If you came to the stream through my story, there's also a link there to the donation. So it'd be awesome if any of you guys could donate, even if it's just like 20 Rand or whatever. Every little bit helps. And if not, I can also send the link in Twitch chat. So just message me if you want me to send the link there as well. Okay, without further ado, let's do question 18. Okay, so question 18 is the integral of cos square root of x dx. Okay. So often we have square roots, we want to do u subs. So let's let u equal to the square root of x. Okay. So then I want to find dx. So let's just square both sides. So x is going to be u squared. So then that means dx is going to be 2u du. Brilliant. Okay, let's see if that even helps us. So that's now we're gonna have the integral of cos of square root of x is u, so cos of u times, I'm gonna take this 2 out to the front, 2u du. Okay, and this actually does seem to help us because now we can do integration by parts. And again, I'm going to use the DI method that I spoke about earlier. So we're going to differentiate the u, and we're going to integrate the cosine of u. Okay, so cosine of u. Okay, so derivative of u is 0. Sorry, 1, yeah. Sorry, I don't know why I'm going crazy. Too many integrals. Derivative of u is 1, and the integral of cos is sine. So sine of u, and we want to go until we get 0, so derivative of 1 is 0, and derivative of this is going to be negative cos of u. Okay, this one's even easier because we don't have like I think we had 2u before, something like that. Okay, so now all we have to do, same as before, is we multiply that by that, and that by that, and that gives us basically our integral by parts. So it's going to be 2, and this integral is going to become u times sine, put that in there, u times sine of u. I've got the plus minus plus, plus minus plus. Okay, and then we get negative 1 times negative cos u, so that'll be plus cos u. Yep, good. And then we can just multiply the 2 in, and then also u is going to be square root of x, and let's sub that back in. So it's going to be 2 root x times sine square root of x plus 2 times cos of square root of x plus c. Brilliant. Good stuff. Okay. Oh, I just see Layla donated 200 Rand, so thank you so much, Layla. Really appreciate it. Shout out to you. Okay, and I think that's the answer. So, yeah, I think the nice trick here is when you do the u sub, it basically gives you something where you can do integration by parts. So that's the big trick here. Now let's keep going. Okay. Number 19. Number 19. Integral from 3 to 5 of x minus 3 to the power of 9 dx. Okay, so this one's quite easy. We can just multiply it out, but we would be multiplying forever. So maybe instead of using like 10 sheets of paper by multiplying out that, you could maybe do a binomial expansion using like the Pascal's triangle. But what I think I'm going to do is I'm going to do a u sub. Okay, so I'm going to say let's let u equal to x minus 3. Okay, that means that du is going to be just dx, so that's very nice. And now we have the integral from 3 to 5 of u to the power of 9 du. Okay, very nice. Now we can just do the basic way where we add 1 to the exponent and divide by it. So that's going to be u to the 10, 1 over 10. Let's do 1 over 10, u to the 10 from 3 to 5, because it's a definite integral now. Let's write that better, 3 to 5. Okay. Oh, wait, I didn't sub in my bounds. Oh, that's bad. Naughty. So when you do a u sub, you also need to check your bounds. So if x goes from 3 to 5, then u goes from x minus 3. So 3 minus 3 will be 0. And then 5 minus 3 will be 2. So it goes from 0 to 2 now. Okay, yeah, there we go, fixed it. So now I can sub in this. So it's going to be 1 over 10 times, let's take that out because it's like a constant. So it'll be times just 2 to the 10, I guess, because 0 to the 10 will be 0. Okay? So 2 to the 10 is 1,024 over 10. And 1,024 is actually one of my favorite numbers. It's a really cool number because you can write it using its digits. You can write it as 4 minus 2 to the power of 10. And you use 4, 2, so 4, 2, and then 0, 1. 0, 1. So it's a really cool number. You can write it using its own digits. I think there's another number like that, 128. You can also write it. So you can write it as 8 minus, no? Yeah, so 2 to the power of 8 minus 1, yeah. Write it as 2 to the power of 8 minus 1. So those are cool. I really like those numbers. I think they're quite interesting. Little side note. And yeah, that's your final answer for this question. Okay, let's not get too distracted by cool numbers. Okay, number 20. Number 20. Okay, so number 20 is the integral of e to the power of 2 times ln of x dx. Okay, so it almost looks like we can cancel the e with the ln x, but we can't do it yet because we have that 2. Okay, so what we have to do is we have to move this 2 into like the ln x. So it'll be e to the power of, integral of e to the power of ln of x squared, okay, because we know log laws we can do that. And now we can see they cancel really nicely. So now, basically that e cancels with the ln, and we just get the integral of x squared dx. Standard, so it's going to be 1 over 3 x cubed plus c. Brilliant. The first 20. I'm just going to go grab some water. Let me just put water break on the screen, and I'll be back in like 3 minutes. So, water. Water break. Okay. I'll be back in like 2 minutes. Okay, I'm back. Let's get cracking. Let's raise this. Okay, 20 down, not bad. 20 down in an hour and a half. Okay. So now we're doing the next 10. So that was just like a mixed bag of some cool integrals. The next 10 are specifically by my first year maths lecturer, Harry Wiggins, and he said some pretty tough ones, so these are going to be quite challenging. So let's see how we do. So the first one by Harry was the integral of ln x cubed dx. Okay, so it would be nice if this was like u cubed, so let's do a u substitution, right? So let's let u equal to ln x, okay? So then du would be 1 over x. Yeah, du will be 1 over x dx. Okay. Yeah. And let's find what x is, because we want, so yeah, so then x would be, so we raise both of these to e, so it'll be e to the u. Okay, yeah. Because we're going to sub, you'll see. Okay, so it'll be the integral of u cubed times, and dx is just, let me actually write that. So we have that basically dx, I'm going to multiply both sides by x, is x du. So instead of, so I would write x du, but x is e to the u, so I'm going to say e to the u du. Okay, classic. This is another really good candidate for the DI method, because we're going to basically have to do integration by parts a lot of times, because every time we do it lowers the power, so it'll be like x u to the 3, u to the 2, u to the 1, and then finally a constant. So let's use the di integration by parts method. So we obviously want to differentiate this, and we want to integrate the e to the u. Plus, minus, plus, minus, plus. Okay, I don't know how many times we'll double check. Derivative of this is 3u to the 2, derivative of that is 6u, derivative of that is 6, and 0, okay? And this is nice because it's just e to the u every time, right? E to the u, e to the u, e to the u, e to the u. Okay, so to do integration by parts, that times that, that times that, that times that times that. I think I should have written one more, just for the 0, e to the u, but we don't use it, yeah. No, actually it lines up, yeah, because this one should line up with the last one, okay. So, our integral will be equal to, so u cubed e to the u minus 3 u squared e to the u plus 6u e to the 6u e to the u minus 6 e to the u. Okay. So maybe let's factor out e to the u, and we know that u is ln of x, okay? So let's also sub that in. So I'm going to factor out e to the u, but instead of u, I'm going to write e to the ln x, and then we get u cubed, so it'll be ln, I don't know if you can, I'm just going to write like ln, ln x cubed minus 3 ln x squared plus 6 ln x minus 6 plus c. Okay, and there's one simplification you can do. We know that e to the ln x is just equal to x. So instead of that, I can just write that as x. And that is our final answer. Oh, I see Hayden in the chat. Hey Hayden, hope you're doing well. Thanks for the message. Hope you, I don't know if you enjoy integrals, but hope you're enjoying the stream. We should go for a run sometime. I'm in Joburg, so if you're ever keen, you must let me know. Okay, so that was number 21. Number 22. Okay, so we're doing integral from 0 to 2 pi of sine x plus cosine x to the power of 11 dx. Okay. So what I want to do is I'm going to let this whole function just be equal to f of x. What am I going to do? Let's maybe split it up first. So let's split it up. Integral from 0 to pi of sine x plus cos x to the power of 11. And then we can split that up into from pi to 2 pi of sine x plus cos x to the power of 11 dx. Okay, so now I've split it up. So now I'm going to say f of x, I'll just write it here. F of x will be just this thing. So it'll be sine x plus cosine x. Can you see that on camera? Oh, I'm blocking a little bit with my head. Let me move across. The power of 11. Ah, okay, cool. I forgot about my mic as well. Hopefully the sound wasn't too bad. Okay, and now let's just do something interesting, right? Let's see what f of x plus pi is. Okay, so let's do that here. So let's see what f of x plus pi is going to be. Okay, so it's going to be sine of x plus pi, right? Yeah, let's write it. So it's going to be sine of x plus pi plus cosine of x plus pi to the power of 11. Okay, and we can use our expansions like sine of alpha plus beta. Let me do this in purple. So this can be expanded into sine x. So sine x times cosine of pi, I think it's plus, yeah, plus cosine of x times sine of pi. Okay, and we know that cosine of pi is going to be -1, and we know that sine of pi is going to be 0. Okay, so that basically just gives us just negative sine x. So I'm just going to say this basically becomes negative sine x. Okay, so now let's do the same for this one. Okay, so if we expand this one, it's going to be cos x times cos pi. So cos x times cos pi minus sine x times sine pi. Okay, and we know that cos of pi is -1, sine of pi is 0. So this is again cancels out, so it equals negative cos x. Okay, that's quite nice. So we see that when you sub in x plus pi into our function, we basically just get okay, well, let's do it in steps. So we've basically shown that f of x plus pi is equal to, so it gives you negative sine, I'm going to factor out the negative, so negative sine x plus cos x to the power of 11, right? And if we take out this negative, because since it's an odd power, it's still going to give us a negative. So it basically equals negative, and if you take this is just our f of x. So it equals negative f of x. Okay, that's quite interesting. So we found that f of x plus pi is equal to negative f of x. Okay, so let's go back to here. Okay, so I'm going to write this as the integral from 0 to pi of f of x dx. And then what I'm going to do for the second integral is I'm going to do a little substitution. So I'm going to say, I should probably write the substitution before I write this. Make it clear. So I'm going to say, let's let u equal to x minus pi. Well, let's write it the other way around. So let's let x equal to u plus pi. Okay, so if we rearrange that, then u is equal to x minus pi. Okay, do you see? Because we did x plus pi, so u plus pi, like we're kind of using what we did earlier. Okay. So then it's quite nice, du is equal to dx. Okay. And let's just be careful with our bounds when you do that. Okay. So it's going to be integral from 0 to pi of f of x dx. Right? And then it'll be plus the integral. Let's check our bounds. So in terms of u, we're going from x, so if we're going from pi minus pi will be 0, and then 2 pi minus pi will be pi. Okay? And this will be f of, we're saying this is f of x, now instead of x we're writing u, so it'll be f of, it was f of x, now we're subbing in u plus pi, so f of u plus pi du. Yeah. Okay. And this is quite nice because we just proved that this is going to be equal to negative f of u. So we just proved that this thing is going to be equal to negative f of u. Okay. So I'm going to rewrite this. Integral from 0 to pi of f of x dx plus integral from 0 to pi of negative f of u du. Okay. And this u and this u is just a dummy variable, so I can switch this back to an x. And I can also take this negative out, and now you'll see the magic. So, I just dropped a stain in my carpet. So that's going to be equal to the integral from 0 to pi of f of x dx minus the integral from 0 to pi of f of x dx. So I just swapped u to x. That and that cancel. How cool is that? They cancel out so nicely. So we're just left with big fat 0. How cool is that? All that work just to get 0. Okay, let's erase that and keep going. A sip of water. That was 22. Let's do 23. 23. We have the integral of 2 sine x plus 3 cosine x over sine x plus cos x dx. Okay. So one thing to notice is that if we do the derivative of the bottom, the derivative of sine is cos, the derivative of that is negative sine. So it almost looks like we have it at the top, but we kind of have some like constants. So it's not like exactly right. Okay. So it would be nice if we could rewrite it kind of in like this way. Okay, so if we could rewrite it as like a times, let's just say times just this, because then that'll cancel out. So if we write it as a times like sine x plus cosine x plus b, and then times the derivative, because then we'll get the whole ln thing. So derivative of that is cos x minus sine x over sine x plus cosine x. So it would be nice if we could write it in that kind of form, right? So let's kind of work out what a and b here would be for our equations, and then we can write it in that form. Okay. So let's multiply, because we're basically saying that this top is equal to that top. So let's multiply it out. So it's going to be a times sine x plus a cosine x plus b cosine x minus b sine x has to be equal to the top there. 2 sine x plus 3 cos x. Okay, so now we see a sine x, so we can group the sines together. So we can see that, let's say a minus b sine x. Let's group the causes, so plus a plus b cos x has to be equal to 2 sine x plus 3 cosine x. Cool. Okay, so now we can equate. We know that a minus b has to be equal to 2 and a plus b has to be equal to 3. So we have simultaneous equations now. So we have that a minus b has to be equal to 2, equation 1. And we have that a plus b has to be equal to 3, equation 2. Okay, so if we rearrange this, we get that a has to be equal to 2 plus b. And if we sub that in here, then we get that 2 plus 2b is equal to 3. So if we move that across, we get b is equal to, I think, half. Okay, b is a half. Good. So now let's find a. So therefore a is 2 plus a half, so it's 5 over 2. Brilliant. Okay. A lot of work. Okay, I'm just going to erase this to make a bit more space. But we're just going to remember that b is a half and a is 5 over 2. And we're going to rewrite it in this form. Actually, I'm going to like reuse that, yeah. I'm not going to erase that. So I'm basically saying we can rewrite our integral like this. And we said that a was 5 over 2. And we worked out that b was a half. Okay. Do you see that? And now, the reason I wrote it like this is because now that cancels with that. So we can split it up into the integral of that over that, but it'll cancel. So it's just 5 over 2 dx plus, let's take out a half, integral of cos x minus sine x over sine x plus cos x dx. Okay, good. So for this first one, it's going to be easy, but for the second one, we're going to do a u sub, because we already saw if we that equal to u, that's the derivative. So let's say that u equal to sine x plus cosine x du is going to be cos x minus sine x. Okay, and then we can just do that, yeah. So integral of 5 over 2 will just be 5 over 2x plus half integral. So that, do you see that this gives you, I should have written du, dx, yeah, sorry. Do you see that gives you du, and this is just 1 over u now, so 1 over u du, okay? So then that's going to be 5 over 2x plus a half. What integral of 1 over u is ln of u, ln of absolute value of u, plus c. And then let's just bring in a paper answer. So our final answer is going to be 5 over 2x plus ln. We should sub that u back in, so it's going to be ln of sine, if I'm not blocking, sine x plus cos x plus c. Brilliant. Good stuff. Okay. Let's keep going. Number 24. No, yeah. Oh, 25, I'll be a quarter of the way through. Not bad, not bad. Okay. Number 24. Integral of the square root of x minus 1 over x dx. Okay, so often when we have square roots, like I've said before, is we want to do a u sub. Okay, so let's let u equal to the square roots of x minus 1. Okay, we could integrate this, but let's rather just solve for x, and then we can get dx. So then if we solve for x, we can square both sides and move 1 across. It'll be u squared plus 1. So then dx will be 2u du. Okay, we don't need x anyway for that. Okay, so what we have now is we have the integral of that square root of x minus 1, which is u, over x, which is u squared plus 1, and then times 2u du. So I'm going to take this 2 out, put a u here, du. Okay. This looks quite similar to something we did earlier. It's like a similar trick. So the 2 integrals, so it'll be u squared over u squared plus 1. And then I'm going to do plus 1 minus 1, same as like similar trick to what we did earlier. Okay. Because now this is going to give us 2 integral of, so u squared plus 1 over u squared plus 1 will give us 1 du. Minus, because minus here, 1 over u squared plus 1 du. Okay. Brilliant. Let's move up here. So that's going to equal 2. Integral of 1 in terms of u is u, minus 2. The integral of that, we've seen it before. It's tan inverse, or arctan, or whatever you want to call it. I like to do tan inverse of u. Yeah, times the 2. Good. And now we just need to sub in our u, which is square root of x minus 1. So that's going to be 2 root x minus 1 minus 2 tan inverse of square root of x minus 1 plus c. Good stuff, good stuff. Cool, that's number 24. Let's do number 25. Okay. Number 25. It is the integral from 0 to e of x to the power of 1 over ln x dx. Okay, so guess what? Surprise, surprise, another u substitution. So we're going to say, let's let u equal to maybe ln x, right? ln x. Okay, so then we can say that x, if we raise both sides to the power of e, will be e to the u, right? So then dx will be equal to e to the u du. Okay, let's see if this helps us. So now what we have is we have the integral from 0 to e of x, which is ln x, right? Wait, x, sorry, no, x is not ln x. X is e to the u. So we have x is e to the u to the power of 1 over ln x, which is 1 over u. That looks nice, cancels out quite nicely. And then dx is e to the u du. So we can see that 1 over u and u will cancel. So we're going to get the integral 0 to e of e to the basically 0, which will be 1. So it'll be 1 times e to the u du. We know that the integral of e to the u is just e to the u from 0 to e. So we sub in the bounds. Wait, this will be e to the 1. I should have actually, this will be e to the 1. So let's just put e here. Yeah, it's not e to the 0 because u times 1 over u is 1. So e to the 1 is 1. Yeah, sorry. So it's e times that. So that'll be e times e to the e, lots of e's, minus e to the 0, which is 1. Brilliant. Oh, actually, let me think about my bounds. I didn't even think about when I did the u sub. So I'm saying u is ln of x. Oh, ln of 0, let's say it's 0 plus, should be infinity. And then ln of e is just 1. So the negative infinity, actually, yeah. Negative infinity, because the ln graph looks like that. So as it gets, you see, as it gets closer to 0, it gets to negative infinity. Negative infinity is 1. Let me fix that up. Change that, change that, change that. Okay, so this should be negative infinity to 1, negative infinity to 1, okay? And then it'll be e to the 1, which is just e. And e to the negative infinity is like 1 over infinity, which is 0. Then our final answer is just e squared. Okay, no mistake there. Fixed it up. Good. 25. Halfway through the tricky integral Harry section. All of these are tricky, to be honest. Okay, this one looks quite scary. The next one, 26. Integral of the square roots of x square root of x square root of x. And it just basically goes on like that forever. So it's basically repeating forever. So often with these things, you can often use a trick where you let a variable equal to the whole thing, and then you can use some like kind of trick to, so let's let like y, for example, equal to the whole thing. So okay, let me try it out. Y is the square root of x square root of x square root of x, blah, blah, blah. Okay, and then what happens if we square both sides, right? So then we get y squared is equal to, basically get rid of that square root, because basically what I'm doing now is I'm going to square both sides. So that square is going to get rid of that square root. So we're going to be left with x, and then we're also going to be left with another infinite thing. And we know the infinite thing is y. So it'll be x times y. Brilliant. Yeah, that's really cool. Okay, and then if you move that across, you get y squared is equal to x minus, I'm moving it across. So we get y squared minus xy is equal to 0. Okay, and then we can factor out y, and we get y minus x equals 0. So then y equals 0, or y equals x. Okay. Okay, so now we got two solutions for y, because we basically said that y is equal to that whole thing. No, y is just the thing, it's not the integral actually. So we know that therefore the integral of 0 dx will be 0 if that's the case. So let's just do this case then. So basically that is going to be the integral, because now this like infinite square root thing is, we just showed that it's equal to x. So now it's just the integral of x dx. Okay, and the integral of x is just a half x squared plus c. Brilliant. Cool. Looks really scary, but if you do some simplifications, not too bad. Not too bad. Okay. Let's move on to question 27. Dun dun dun. Okay. Question 7. We have the integral from 0 to... we're more than quarter of the way through. Nice. We're only almost 2 hours in. Okay. Integral from 0 to infinity of 1 over x plus 1 over x all squared dx. Okay, cool. So what I'm going to do here is I'm going to do a trig substitution. So let me put this here. So what I'm going to do is I'm going to say, let's let, might seem a bit mysterious, but let's just try it out. So let's let theta equal to tan inverse of x. Okay, let's see why we do this, right? Right? Yeah. So basically what we're doing, if we let that, then if we solve for x, we can just say let x be equal to tan of theta. Okay, so I'm kind of doing that substitution. I'm saying let x equal to tan of theta, so then if we solve for theta, it's going to be tan inverse of x. So let's do dx is going to be, the derivative of tan of theta is going to be sec squared. We already saw this earlier. Sec squared of theta d theta. Yeah, and we know that sec squared is 1 over cos squared. So maybe so that's equal to 1 over cos squared theta d theta. Okay. How does this help us? Let's sub in. Maybe before we sub in, let's just do like that. So let's just do like x plus 1 over x, okay? So we know that x is tan of theta. Plus, and then 1 over x is 1 over tan of theta. Theta. So that's tan is sine over cos. Sine theta over cos theta. Plus 1 over it will just be the opposite. So it'll be cos theta over sine theta. Okay. Let's make a common base. So our common base will be cos theta times sine theta. So to get that, we need to say this will be sine squared theta, this will be cos. This is nice. This basically cancels out, and this whole top bit gives us 1. Okay, that's really nice. So now let's just sub it back into our integral. Okay, we're gonna remember this, but I'm gonna erase this just to make a bit more space. Yeah. So we're basically going to get Okay, let's erase this bit. Let's remember this result. So we basically get 1 over cos theta. Okay, so this time let's remember our bounds. So we get the integral. So now we're doing in terms of theta, so we need to go we need to sub our bounds to this. So tan inverse of 0 is still 0. The tan inverse of infinity, because it kind of like levels out, it goes to pi over 2. Okay, good. And then we get 1 over... So now we get 1 over that. So now we already had like 1 over, so we can flip it. So remember, it was like sine, it was 1 over sine theta times cos theta, so now it's 1 over that. So now it's just sine squared theta times cos squared theta. Good. So now, because remember we did this, but we need to square it, and we're flipping it as well. And then we times that by dx, which is that. So 1 over cos squared theta d theta. Okay, that's two black pens open. Let me close this one. Very nice. Cancel. And we get the integral of sine squared theta. Okay. Let's use this. So we know that sine. Let's use this identity. So you can derive this from the cos of 2 theta is equal to cos squared theta minus sine squared theta. So we get that sine squared theta is just equal to 1 minus cos of 2 theta over 2. Okay, so let's sub that into the integral. So we get the integral from 0 to pi over 2 of this. Yeah, so it'll be of, let's just do the first one, a half d theta minus the integral of half of cos of 2 theta d theta. Okay, brilliant. This one's easy. This one's just going to be a half theta from 0 to pi over 2 minus a half. This one we need the derivative inside here, so I'm going to put a 2 here, so we need like a half on the outside. So now we're actually going to get like a quarter minus a quarter, and the integral of cos is sine, so it'll be of sine. You want basically put the thing here for, like, if you wanted to use that, you could say that u equals to 2 theta, blah, 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 and then d, yeah, but I'm not going to do it. You can just see that. And then we're going to do that from 0 to pi over 2. Pi over 2. Okay. Now all that's left is to sub in, so let's do that here. So we get minus a half times pi over 2, which will be pi over 4, and that'll just be 0, so that cancels out. And then minus a quarter, sub that in, so it'll be sine of pi minus a quarter sine of 0, which we know will be 0. Okay, so that's going to become pi over 4. And what's sine of pi? We know that sine of pi is also actually 0. That's just going to be 0, 0. So our final answer is just pi over 4. Very nice, very nice. Okay, I want to keep my pens here just so it's easier. Okay, brilliant. So that's number 27. Ah, not 7. 27, sorry. Let's keep going. Okay, let us do question 28. Okay, question 28 is the integral from 1 to 4 of 6 over the square root of 1 plus the square root of x all to the power of 3 dx. Okay, good. What should we do here? Probably another u substitution. So let's let u equal to 1 plus the cube root of x. Okay, so let's do du. Du is going to be 1 over 2 root x. Okay, dx. Okay, so maybe let's solve for dx instead. So then dx is just going to be 2 root x du. But we know that square root of x, right? I'm not saying no. Yeah, that's good. I like that. Okay. So then let's sub everything in. So it's going to be the integral. Let's check our bounds. So it's going to be from 1 plus the square root of 1, so 2, right? Up until 1 plus the square root of 4, which will be 3 of 6. Actually, let's take the 6 out to the front. Of 1 over, so square root of x, I'll keep it because it'll cancel out with this thing, and then that'll be of u cubed. And the dx we said was 2 root x du. And we see now that this square root of x cancels nicely with the square root of x. Brilliant. Okay. So we're going to get 12 integral from 2 to 3 of u to the negative 3 du. We do the normal thing, so it's going to be 12 times u to the negative 2 over negative 2 from 2 to 3. Okay. So I cut what this is. So that's going to be 12. So that'll be 1 over 9. 1 over 9 times negative 2. Wait, no. 1 over 9. Let's actually take out the negative 2. I think it'll be easier. So if I take out this negative 2, 1 over negative 2, it'll be negative 6. And then I can just do 1 over 3 squared, which would be 9, minus 1 over 4. Okay, good. Common base 36, so 1 over 6, we can do that as times 4. So that'll be 4 minus 9 over 36, which will be minus 5 plus 5 because it's minus 6 over 6. 5 over 6, final answer. Good stuff. Hope that was a good one. 5 over 6, final answer for this one. Okay, number 29. Let's get going. Okay. Number 29. So, number 29, we're going to do the integral of the square root of tan x dx. Okay. Square roots. Remember, we often use u sub, or I don't know if that's like a real rule, but that's just what I always think of. So let's let u maybe equal to the square root of tan of x. Okay, we're probably going to get some sex here, because sec and tan are friends. U is going to be the square root of that. Then if we solve for u squared, is going to be tan of x. Okay, so if we do the derivative of both sides, we're going to get sec squared x dx, and the root of this is going to be 2u du. Okay. One thing we know is that we know that 1 plus tan squared is going to be sec squared. Okay. So, how can we use that? So we can say that, we know that tan is, so we know that, I'm going to put it here, move it a bit. So we know that 1 plus tan squared of x is going to be sec squared of x. Okay? Yeah, sec squared of x. So we can say that sec squared of x is going to be 1 plus, we know that tan x is u squared. So now it's going to be u to the 4. Does that make sense? Okay. So sec squared x is 1 plus u to the 4. Now we can sub that in here and move it across. So then we get dx is equal to 2u over 1 plus u to the 4 du. Yeah. So basically what I did, I'm using this, and I'm subbing that in for sec squared here, and then I'm just dividing it to get dx on its own. Okay. I think that makes sense. So let's see what we left with. So this is basically equal to the integral of u, right, because we left that equal to u, and then we said that dx was this, so times 2u over 1 plus u to the 4, oh, not d4, it's supposed to be du. Okay. Let us multiply this in, so it's going to be the integral of 2u squared over 1 plus u to the 4 du. And then, what should we do now? Maybe we should split it up into a certain way. So maybe let's split this up into the integral of, like, let's do u squared plus 1 plus u squared minus 1 over 1 plus u to the 4 du. Okay, because those ones cancel, and u squared plus u squared is 2u squared. Okay, so now let's split this up into two separate integrals. So that's going to be the integral of u squared plus 1 over 1 plus u to the 4 du plus the integral of u squared minus 1 over 1 plus u to the 4 du. Okay. And let's see why we've done this. So what I'm going to do is I'm going to divide the top and the bottom of both of them by u squared. Okay. So then we're going to get the integral of u squared divided by v squared is 1 plus 1 over u squared over u squared plus, sorry, this was 1 over u squared plus u squared, okay, du plus the integral of 1 minus 1 over u squared over 1 over u squared plus u squared du. Okay. Let me erase this because we're going to need some more space because we're going to do another u substitution now. So now what I want to do is, okay, we've already used u, so maybe let's use like v. So I'm going to say maybe for this first integral, let's let v equal to, so u, yeah, it's going to be u minus 1 over u. Okay, so let's see what dv would be. And dv would be the derivative of this would be 1, and that would be that, so it would be 1 plus 1 over u squared. Okay. Let's also see what else do we need? So we also need u squared here. So let's see what u squared would be. Well, let's get maybe v squared, and then we can solve from there. So v squared, if we squared this, would be u squared. That times that would be 1, so we minus 2. That times that would be plus 1 over u squared. Okay? So therefore that implies, okay, we can get like this bottom quite nicely. We can get the u squared, 1 over u squared, which is that. So we can get 1 over u squared plus u squared is equal to v squared plus 2. Okay. Nice little substitution. So that's the first integral. So for the second integral, let's do something similar, but I'm just going to use a different letter. So let's use w, okay? So I'm going to say let's let w equal to this, but I'm just going to use a plus. So it's going to be u plus 1 over u dw. It's going to be 1. That's going to be minus 1 over u squared. Again, let's do w squared is equal to u squared plus 2 plus 1 over u squared, which implies, what do we want here? We want, so we want 1 over u squared plus u squared is equal to w squared minus 2. Okay, cool. So now we're going to sub all of this in, and I think a lot of nice cancellations are going to come out. So going from here, we get that that's equal to the integral. Let's have a look. So, so all of this v stuff. So, let me just write the du. I was naughty. This is du, yeah. So let's have a look. So we get 1 plus 1 over u squared du. Do we see that that's exactly what's at the top here? 1 plus 1 over u squared du. So that's just going to give us our dv. And then at the bottom, we get 1 over u squared plus u squared. And we show that that's equal to 1 over v squared plus 2. Does that make sense? dv. Okay. Similarly here, we see that 1 minus 1 over u squared du gives us the dw, and then the bottom just becomes w squared minus 2 dw. Brilliant, okay. And now what we're going to do is, let's write what we know in general about arctan. Where's my green here? So we know in general that if we have the integral of 1 over x squared plus a squared dx, right? That's going to basically be 1 over a times arctan of x of a. Cool. Hope I'm not blocking there. A little bit of glare. Okay. Hope you can still read it. Good. And we kind of have this because we can kind of write, let me do this in purple. We can kind of write 2 as the square root of 2 squared, And then here, okay, that'll be for the first one, right? And then for the second one, we know this general identity that the integral of 1 over x squared minus a squared is just 1 over 2a times the natural log x minus a over x plus a. Okay, so we're going to use these actually, and we're basically going to get, so this one's going to be that one, so this one's going to be 1 over a, and our a is like the square root of 2, so 1 over root 2 arctan of x over root 2 x. Ah, wait, no, I'm doing it in terms of v, so it should be v. Okay, plus, and then this one is that one, so it's going to be 1, we can write this as like also square root of 2 squared. Okay, so that's going to be 1 over 2 root 2 natural log of w minus root 2 over w plus root 2. Okay, we've done our integration now. Now we just need to do a million different substitutions to get back in terms of x. Okay, so I'm going to do some erasing, and then we're going to do a bunch of different substitutions. Okay, let me erase all of that. Okay, hopefully that's enough space. Cool. So, we're going to do, we basically have to sub this back in. So let's see, what is v? We know that v is equal to 1 minus u minus 1 over u. And then I think in the beginning we said that u is equal to tan of x. So our overall answer is going to be 1 over square root of 2 times arctan of v, which is u minus 1 over u, and u is tan of x, so square root of tan of x. So I think it'll be square root of tan x minus 1 over square root of tan of x all over square root of 2. Okay. Yeah. Okay. Plus 1 over 2 root 2 natural log of w. We know that w is u plus 1 over u, so I'm going to say it's going to be square root of tan x plus 1 over square root of tan x minus root 2 over w plus 2. So that's just exactly that. So tan x, square root of tan of x, plus 1 over the square root of tan of x plus root 2. Oof, plus c. Long one. A little bit worn out after that one. But that is number 29. Very long one. But not too bad, I didn't think. Actually, it's too bad. Yeah, it's a tough one. But we got there in the end. Okay. So erase this and do number 30, the final one of Harry's tricky ones. Oh, what's a sip? Okay. Number 30. Okay. Number 30 is the integral from 0 to 22 pi of sine of x times sine of x minus x dx. Okay. So, we can maybe multiply in first. So our first step will be the integral from 0 to 22 pi sine squared x. Maybe let's split this up, dx minus the integral of x times sine of x dx. Okay, cool. We're going to use an identity that we actually proved earlier. We're going to use the identity that sine squared x, we proved this earlier using the cos of 2x thing, is equal to 1 minus cos of 2x over 2. Okay. I'm going to use that for that one. Okay. So it's basically going to be a half times the integral of 1 minus cos of 2x dx. Okay. And then that's the first one, pretty chill. And then the second one, this is going to be let's just do R1. Let's do the first one and the second one. I think this is going to be integration by parts. So let's do this I1, okay? So this is going to be a half. I should put in the bounds as well. We didn't do any substitutions, so I don't need to change it. 22 pi. Okay. So we know the integral of 1 is going to be x minus the integral of this is going to be, so the integral of that is sine x, but we need to divide it by a half, so I'll do a half sine 2x from 0 to 2022 pi. Okay. Let's sub in our bounds. So it's going to be a half times 2022 pi. So let's just have a look at this. So this will be 44 pi. And we know that sine of like 0 is going to be 0. And we can minus 2 pi from anything because it's like kind of rotating around the whole circle. Okay. So we can basically minus all of this. So it'll become sine of 0, which will become 0. Okay. So basically minus 0. And then minus 0, so we can leave that out. And then sine of 0 is again 0. So just everything cancels out. And we get 1011 pi for our first integral. So now we still need to do this one. Okay. So let's call this maybe R2. So R2, let's leave that one. And let's do, actually let's before I write that, let's do a u substitute. It's going to be about parts, I said, yeah. So let's let u equal to x. Then du is going to be dx. And dv is going to be the rest. So it's going to be sine x dx. And then v is just going to be the integral of that. Integral of sine x is negative cos x. Okay. Sure. Okay. Let's do a little dotted line. So our integral 2 will be u times v, so it'll be negative x times cosine of x minus the integral of v du. So it'll be minus the integral of that, which will just be plus cosine of x dx. Good. Okay, you can do the bounds. So I'll just, for everything, the bounds are from 0 to 22 pi. Okay, I will sub it in hand. So that's going to be what negative x times cos of x. Integral of cos of x, easy, sine of x, plus sine x from 0 to 22 pi. Okay, so it's going to be negative 2022 pi. Cos of 2022 pi is basically cos of 0, which will be 1. So I'll say times 1. So we already said sine of that is 0. And then if you sub in 0 into x, will be 0, that'll be 0. So it basically just becomes negative 2022 pi. Okay, so our overall integral, so integral of this whole thing, is going to be the sum of those. So it'll be that plus that. It's a minus, so it's that minus that. So it's basically 1011 pi minus negative 2022 pi, which is just going to be 3033 pi. Ooh. End of the Harry Gauntlets. Okay, that's all 30 questions done. That's 30 questions done so far. Go take a quick bathroom break. Let me just write that here. bathroom break. And I'll be back in like 5 minutes. Okay. Okay, I am back. Let's move on to the next section. Let's erase this. Quite a hard workout erasing all this stuff. Okay, let's keep going. So now we're going to do another. So that was like Harry's 10 questions. Now we're just going to do another mixed bag of random questions. So question 31. We're going to do the integral. So we already saw the integral of ln x cubed. Now we're going to do ln x squared. Okay, so it's actually very similar. We're going to do integration by parts. So we can use the let me think. Yeah, I think integration by parts will be good here. So let's let u equal to ln x squared. So then the derivative of that will be 2 ln x. We need to do the chain rule, so then it's going to be over x. Okay, and then dv will be equal to dx. Then v will be equal to x. Okay. So what we get for our integral is going to be u times v. So it'll be x times ln x squared minus the integral of v du. So the x will cancel, which is 1. So it's minus the integral of 2 ln x dx. Okay, very nice. And now we just need to do this integration by parts one more time, and then I think we'll be done. So now let's let u equal to, again, ln x du will be equal to 1 over x, and then dv will be equal equal to, say, 2. Then du will be equal to 2x. Should be dx here. Okay, so we're going to get x times ln x squared minus all of this. So it'll be minus uv, so it'll be minus 2x times ln x minus will become plus the integral of, oh, this is not d, this is, what? Yeah, this is supposed to be b, sorry. Just mislabeled it. B. Okay, so minus the integral of v du, so minus the integral of 2 over x dx. Okay, not too bad. So now what we can do is we can just say that that's going to be equal to, that's like ln of x, so 2 times ln of x. Basically, let's put it over onto here. It's going to be x times ln x squared minus 2x ln times ln of x plus 2 ln of x plus c. That's right here. What do you think? So minus u minus that. What did I make a mistake? So that's, oh wait, 1 over, I forgot to times that, so that should actually just be 2, integral of 2. Then it'll just be, instead of 2 times ln of x, it'll just be 2x plus c. Okay, I think that's the final answer. Good. That's 31. Let's go on to 32. Okay. Question 32. Okay. Question 32 is the integral of cosec of x. Okay. So we're going to use a similar trick to something we did earlier, where we multiply this. So we want to multiply this by, oh, I just see Rob donated 250 Rand. So thanks a lot, really appreciate it. Let's keep going. So we're going to multiply this by cosec of x minus cotangent of x over cosec of x minus cotangent of x. Okay, that's going to be useful, and you'll see why, because it'll give us like a nice, use of. So let's multiply this in. So we multiply that by that, so you get the integral of cosec squared x minus cosec x times cot x over cosec x minus cot x dx. Okay, and now you'll see why we do this, because now we're going to let u equal to this bottom bit, which is cosec x minus cot x. Okay, and now let's see what du is. So the derivative of cosec is negative cosec times cot x. So negative cosec times cot x. So I would say, like, what I think is cosec and cot are friends, and like sec and tan are friends. That's how I always remember it. So then the derivative of cot x will be negative cosec x. So it will be negative, so it will be plus cosec squared x dx. And do we see that what we have here is basically that and that. So now we're just left with the integral of 1 over u du. How nice is that? Really nice cancellation. And we know that the integral of 1 over u is going to be ln of u. And if we sub in u, is this. It's basically just going to be ln of the absolute value, the cosec of x minus cot x plus c. And that is question 32. Okay, I'm just going to close my door and I'm going to continue with 33 next. Okay, good stuff. Where's my eraser? Here it is. how many? 2.5 hours in, not bad. We're moving at a decent pace, so after 33, we're a third of the way. It'll take us like 7 hours, roughly. Okay, not bad. Question 33. I'm going to do the integral from 0 to 5 of the floor function of x dx. Okay. So to do this, the floor function is tricky, but we can actually draw it, similar to what we did with the absolute value function we did earlier. So we can draw this like that. And then I'm going to label this maybe 1, 2, 3, 4, make it a bit longer. 5. Okay. And then let's draw what our floor would be. So the floor kind of rounds it down. So anything between 0 and 1, let's get some green. Anything between 0 and 1 will be 0. Okay. That's okay, open dot. Because at 1, it'll now be 1. Going on to 2, and at 2, it'll be 2. Going on to 3. 3, it'll be 3. Like that. Open. No, that should be open. Close dots, open. Okay, and this is at, let's label this. This is at 1, 2, 3, 4. So now we can find this integral just by using the area. So it's just basically the base times the height. So the base is 1 times the height here is 1. Or this is just 0, 1. And then this will be 1 times the height is 2. 2 plus 1 times the height here is 3 plus 1 times the height between, like 4.5 will be rounded down to 4, so 4. Okay, and that is just 1 plus 2 plus 3 plus 4, 3, 6, 10. Nice. Very cool. Let us keep going. Yeah, and you've got a floor function, it's nice to draw it, and then you can just do it easily. That's a quick one. So 33, we're a third of the way through. Nice. Okay, let's look at question 34. Question 34, we're going to do the integral of sec inverse of x dx. Okay. What we're going to do for this one is we're going to start with a u sub, and it's going to help us out quite a lot, because we can easily do u sub. Maybe we should do integration by parts, because we can do the derivative of that easily. Yeah. Okay, so I'm going to do integration by parts. So I'm going to say, let's let u equal to sec inverse of x. And we know that's the derivative of that. So you can kind of think like, yeah, I know this, maybe not everyone knows this, but it's basically x times the square root of x squared minus 1. Okay. And then dv will obviously just be dx. So then v will be x. Okay, and let's see if this helps us out. So our integral is going to be equal to u times v. That's going to be x times sec inverse of x minus the integral of v du. And if you see, if we multiply that by that, these x's are going to cancel. So it's just going to become the integral of 1 over the square root of x squared minus 1. Quite nice, eh? So now we just need to really find out this. So we can do another, let's do a trig substitution here, because often when you have these kind of things, you do a trig substitution. So maybe, let's just focus on this integral for now. Let's do it here. Okay. So we're just going to do the integral of 1, and we'll add it back then. Square root of x squared minus 1 dx. Okay. So let's do this substitution. Let's let x equal to, we're going to do sec x, sec theta, yeah. Okay. And then, yeah, that looks good. And then dx, we know that the integral of sec theta is sec theta times tan theta d theta. Okay. So now let's see what we're going to get for this. So we're going to get equal to the integral of 1 over x squared, which is square root of sec squared theta minus 1 times sec theta tan hopefully I'm not blocking, it's tan theta d theta. Okay. Now let's see. So we know that sec squared minus 1, this is actually the same as tan of theta, tan squared of theta, okay? And we have the square root of that, so that just becomes 1 over tan of theta. So we actually notice that like this thing is going to cancel out with that thing, okay? And then we're just going to be left with the integral of sec of theta, d theta. And I think we did this earlier, I think it was like question 2 or something. We found the integral of this was just ln of the absolute value of sec theta plus tan theta. Sec theta plus tan theta. Brilliant, so we worked out this on the side, so we can write our final answer now. And our final answer is going to be x times sec inverse of x minus the natural log of sec theta plus tan theta plus c. Okay, well that's actually our final answer because we need to convert back to x, I just realized. Okay, well we can do that using a right triangle. So let's draw a right triangle over here. And let's say that's 90 degrees, that's going to be our angle theta. And which sides do we know? I said that x is sec of theta. Okay, so we know that sec is 1 over cos. And we know that cos is adjacent over hypotenuse, so it's a hypotenuse over adjacent. So we know that that's x and that's 1. By Pythagoras, we can say that's that squared, x squared minus 1. Okay, and now we can use these. So we can use these to sub back. So it's going to be x, this is already in terms of x, so we don't need to do anything here. Sec inverse of x minus the natural log. Sec is going to be sec. Well, we already said sec is just x, I think, yeah, because that was our substitution. We just need to work out tan. So tan is that over that. So it's just going to be square, just the square roots of x squared minus 1. That's going to be plus the square roots of x squared minus 1 plus c. And that's our final answer. Cool. 34. Okay, let's erase that and move on. What I might do quickly is I'm just going to go into OBS and save my video and then like restart another video just to make sure it doesn't. So I'm going to say stop recording and then start recording again. Okay, cool, hopefully that works. Let's move on to 35. So 35 is, we have the integral negative 1 to 1 of the square root of 4 minus x squared dx. Okay. Or we can recognize this. Imagine we have like y squared is equal to 4 minus x squared. That will be a circle. So if we have the square root of that, it's kind of like the top half of a circle. Okay, so maybe let's draw it up. That could be useful. That's a bit skew. So that's our axis. So maybe let's draw. It's going to look something like semicircle. Okay, and we know that it has a radius of 2 because it's 2 squared. So it's 2, 2, and that's also going to be 2. Okay, and then we're doing the integral from negative 1 to 1. So let's plot that down. So I'm going to say that this is negative 1. I'm going to say that this is 1. Okay, so you kind of want to find that area. You want to find the area like there, okay? But do you see it's symmetrical? So we can simplify this. Because this thing is symmetrical, we can make it equal to 2 times the integral from 0 to 1 of the square root of 4 minus x squared dx. Okay, so now we're only really looking for like this area, okay? So I'm going to do something quite interesting now. So I'm going to split this up into a triangle and a sector. So if I draw a line like this, then we see that this is a triangle and a kind of like a triangle and a sector. Okay, so I first want to find, so we want this whole area, but I'm first going to find this area, okay, which is easy. It's half base times height. Or maybe the height's actually not so easy. Okay, we know the radius is 2 because it's a circle. So that this is 2, so we can work out this. This will be the square root of 2 squared minus 1 squared, so that's root 3. So we know that the length of this is root 3. So then we can say that it's going to be 2 times, so this will be half the base, which is 1, times the perpendicular height, which is root 3. Square root of 3. Okay, so that's that. So now we just need to find the area of this sector here. Boom, 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 boom. Like that. Okay, and then we've got this whole part. So let's write the area of a sector. Formula. Area of a sector. Okay, it's basically just half times the radius squared times the angle theta. So it's half times the radius squared times theta. And in our case, do you see that like this is us, I'll do it, it's like a pizza slice. That thing's our sector. So that thing's going to be our theta. Okay. So we need to work out what our theta is. So let's do that here. So we have that, and we have that as 2. We have that as let me think. Let me think. Okay, so we can use maybe that sine of theta is equal to a half. So then theta is equal to inverse sine of a half. And we know that that is going to be pi over, pi over 6. Okay, so now we can just sub that in. So area of a sector is half radius squared, which will be 2 squared, times theta, which is pi over 6. And then if we multiply in the 2, cancel out nicely, so we just get root 3, and that'll be half times 4, which will be 2, cancel out this, or like simplify it, so it'll be pi over 3. Cool, quite nice. Right? I think that's right, eh? Let me just double check. So half. Yeah. That seems right to me. Okay. Cool. I don't know. I'm sure I'll make some mistakes at some point, but yeah, that's good for now. Let's go on to the next one. So, question 36. Okay, question 36, we're looking for the integral from, the integral of 1 over x cubed minus 4x squared dx. Again, so this looks like a this looks like a classic partial fraction question. Okay. So we can factorize this into x squared times x minus 4. Okay, and now we're going to split this up into fractions. So let's show how. Let's do it here. So we basically we have 1 over x squared times x minus 4. And we want to split that up into like something over x squared. So if you have x squared, you have to write ax plus b plus c over x minus 4. Okay, let's split this up so we can write both over x squared, so the x's will cancel, so it's a over x plus b over x squared plus c over x minus 4. Okay, so let's use the cover-up method for b and c. So if we have a look, what we can do is we can cover up the x squared, and what we do is we Let's do b first. So b is equal to. So what we do is we cover up the x squared and we sub in 0 for x. So if we cover up that x squared, then we just get 1 over 0 minus 4, which will be 1 over negative 4. Okay? And then for c, we can do the same. So we cover up the x minus 4 and we sub in 4, and we get 1 over 4 squared, which is 1 over 16. Okay. So now we've got b and c. Now we just need to find a. Let's use x equals 1. So let's say use x equal 1. Okay. So what I'm going to do is I'm going to sub in 1 into both sides of this equation. Let's see what we get. So it'll be 1 over 1 squared, which is 1. 1 minus 4, which is negative 3. So we get 1 over negative 3 is equal to, so a plus b over 1 squared, which is 1. So it'll be, I'm going to sub in what b is, so minus 1 over 4. And then c is going to be plus c, which is 1 over 16. 1 over 16 times 1 over negative 3. Okay, cool. Now we can just solve for a, shouldn't be too hard. So we can say that a is going to be, if we move everything to that side, so it's negative a third plus a quarter, that'll be 48. So plus 1 over 48. We get everything over 48. So we have to times that by 16. We have to times that by 12. So that's going to be 16 minus 4 minus 3 over 48, which will be minus 1 over 16. Okay. So now let's just underline what we have. We have B, we have C, and we have, this is A. Let's just remind ourselves that's A. Okay. So, now what we can do is we can write our integral in a nice way. So our integral is going to be, let's just write equal to, the integral of, we said was A over X. So we can write it as negative 1 over 16 over X plus, and B was negative 1 4 over X squared, and then plus C, which is 1 over 16 over X minus 4 dx. Okay, and we'll see this will be very nice because it'll give us a bunch of lns, except for this one. Okay, so we can see that this is just going to be negative 1 over 16 ln x. This is going to be x to the negative 2, so if we do the integral of that, it will be x to the integral of x to the negative 2, we add 1 to the power, so it'll be x to the negative 1, divided by negative 1, so it's going to be plus, and we're going to move the 4 down, so 1 over 4x, and then plus 1 over 16, and this is just a ln of x minus 4 plus c. There we go. So a nice little partial fraction question. Okay, let me erase that now. A little sip of water. Okay, let's do question 37. Okay, so question 37. So we're going to do the integral of the square root of x squared plus 4x dx. Okay, so the trick that we're going to use for this one is we're going to complete the square. Okay, so to complete the square, we can say x squared plus 4x. So we divide this by 2, so plus 2 squared minus 2 squared. And then that's just going to be x plus 2 squared minus 4. Okay. So we can, basically that's the same as that, so we can put that into our integral. So we're going to say it's going to be equal to the integral of square root x plus 2 squared minus 4. Okay. And now we're going to do, let's actually make that, instead let's write that as 2 squared. Okay. So now what you're going to do is we're going to do a substitution. So I'm going to do a substitution for x plus 2. So I'm going to say let's let x plus 2 equal to, and you'll see why I do this, equal to 2 times sec of theta. Okay. So now let's do dx, therefore, is going to be the derivative of that, which will be 2 sec theta times tan theta. Okay. D theta. Yeah. D theta. I need to remember this more often. So now our integral will become integral of the square root of, we said that that's going to be, that is that squared, so it's going to be, I'll say 4 times sec squared of theta minus 4 times this, which will be 2, let's take the 2 to the front, 2 sec theta tan theta d theta. Okay. Let's have a quick look at this, right? So we can factor this out, so we can make this 4, and then we can make this sec squared theta minus 1. And we know that sec squared of theta minus 1, we know that this is just tan squared of theta. Okay. So we basically have the square roots of 4 times tan squared of theta, so we can square root that quite easily because they're both squared. So it's 2 times the integral of 2, and we'll give this tan theta times tan theta, will be tan squared theta times sec of theta, d theta. Brilliant, right? So now we can change tan theta into, because we're going to have tan theta, same as what we just did there, is sec squared theta minus 1. Okay. So we can say that this is going to be 2 times the integral of sec cubed theta, yeah, multiply that, sec cubed theta d theta minus 2 times the integral of sec of theta d theta. Okay, and we've actually already done both of these integrals previously. Double check. Oh, I dropped this 2. This should be, because there's a 2 here, so I'm just going to change this into a 4 and change this also into a 4 because I'm taking out this 2. Yeah. Okay. We've done both of these integrals earlier in the video, so I'm not going to redo all the steps. But we know that this is basically going to be 4, so we did that this integral was a half of sec theta tan theta. And then this integral, plus then of sec theta by a half, can't forget the half, plus a half sec theta plus tan theta, and then the integral of this, yeah, let's put it all in brackets. I'm going to factor out that 4, so minus the integral of that was just ln of sec theta plus tan theta. Good. Okay. So we can combine these and then multiply in the 4. So I'm going to do that. So that's going to give us our not final answer yet. So it's going to be 2 sec theta tan theta. So we have 1 minus a half minus 1, which will be minus a half, and then a half times minus half times 4 will be minus 2 ln of sec theta plus tan of theta. Okay, so we're almost there, but now we just need to convert back to the x world. So we're going to do that using a right triangle. going to be theta. And what was our sub? Our sub was that. So that means that sec of theta is x plus 2 over 2. Okay, so let's just write that. So sec of theta is equal to x plus 2 over 2. Okay, so know that sec is hypotenuse over adjacent. That means that this is x plus 2, and this is 2, and this is going to be the square root of that squared. So it's going to be the square root of x plus 2 squared minus that squared, 2 squared. You can simplify this, so that'll become square root of x squared plus 4x, and then plus 2 squared minus 2 squared, so we'll cancel out. So we're just left with square root of x squared plus 4x. Okay? Now let's work out whatever everything is. So it's going to be 2 times sec theta, which is that, so the 2's will cancel, so it just becomes like x plus 2, and then tan of theta is that over that. So it's going to be times the square root of x squared plus 4x over 2. I'm running out of space, I'm just going to do it on the next line. Minus ln of the absolute value of sec, which is just or minus 2 ln x plus 2 over 2 plus tan, and tan is that of that. So square root of x squared plus 4x over 2 plus c. Question 37. Nice. Good stuff. Okay, let's keep going. Let's erase this for now. I think what I'll do at 50, I'll have a lunch break. Getting hungry. Yeah, still far away though. 3 hours in. Okay, not bad. Not bad. 38. Okay. Hopefully we can see it a little bit. Let's do the integral of sine x plus cos x squared dx. Okay. Let's start by multiplying it out. So it'll be integral of sine squared x plus 2 sine x cos x plus cos squared x dx. Okay. Well, we can see something quite nice. We know that sine squared x plus cos squared x, so these two together, you add them, are going to equal 1, right? So we can just simplify this into the integral of 1 plus, and what is, this is like an identity, right? The 2 times sine of x times cos of x, I think this is just sine of 2x, okay? So it's just the integral of 1 plus sine of 2x dx. The integral of 1 is x, the integral of this is going to be plus this. Integral of sine is negative cos, so minus cos of 2x, and then you have to do the derivative, 1 over the derivative, plus c. That's question 38. That's a quick one. Good. Let's erase that. Okay, question 39. Okay, let's do the integral of 2 to the power of natural log of x dx. Okay, so we're going to do a nice little trick here. So let's do it in Greek. So let's do on the side. So what we have is we have 2 times ln of x. Okay, we can write 2 in a special way using e. So we can write it as e to the power of ln of 2 to the power of ln x. Do you agree? Okay, because that gives you 2. Okay, when you have something to the power of something, you multiply them, so it's e to the power of ln of 2 times ln of x. And we can split that up into e to the power of ln x to the power of ln 2, just regrouping it. And then e to the power of ln x is x to the power of ln of 2. Quite nice, eh? So this thing is just equal to x to the power of ln 2. So it's not nice to have x in a power, but it's nice to have a constant as a power. So I'm going to write that as the integral of x times the power of ln of 2 dx. And now this is just easy, right? Because now we can just use the power rule. So it's going to be, you add 1 to the power, so it's x to the power of ln of 2 plus 1 divided by ln of 2 plus 1 plus c. Brilliant, brilliant stuff. That's a really cool one. I actually really like that one. If anyone's a maths fan that's watching, you can, yeah, that's a very nice one. Very nice, like, little trick that you do here. Okay. Let's do question 40. Let's go. So, question 40. The integral of sine of 1 over x divided by x cubed. Okay. What are we going to do here? Let's think. U sub, what do we sub? U sub 1 over x. Maybe dx. Let's do integration by parts. I think that'll probably be the best. So let's let u equal to what do you think? Okay, let's try this. So let's let u equal 1 over x, and then the derivative of that will be negative 1 over x squared. And then what will be left will be sine of 1 over x divided by x squared. And then that means that v, the integral of that, will be, yeah, this is nice, will be cosine of 1 over x. Okay, because basically if you think about it, if you did the, if you did the derivative of this, what do we get back? So the derivative of cos of 1 over x would be sine of 1 over x. We need to do the chain rule. So we need to do the derivative of this, which would be 1 over, will be negative sine x, and then negative 1 over x squared. So it would cancel. So that's exactly right. Good. Okay. What are we going to do now? So now we have that. Now, so we're going to have du dx. Okay, so let's, so u times v. So it's going to be 1 over x cos of 1 over x minus the integral of v du, which will be plus 1 over x squared cos 1 over x dx. Okay. Brilliant. Okay. So, what are we going to do now? So, what we kind of want is we're going to do a u sub now, because, it kind of looks good, Now I'm going to say, let's let u, just for this integral, let's let u equal to 1 over x, right? 1 over x, okay? Then the derivative of that is going to be negative 1 over u squared. So we almost have that. If we have a negative here, it'll be good. So then this thing is going to be equal to 1 over x cos 1 over x minus the integral. That gives you, let me try dx here. This should be 1 over x squared, 1 over x squared dx. Okay, so then that and that gives you du. So then it's going to be cos of u du. Brilliant. Okay, and we know that the integral of cos is sine. So it'll basically be equal to 1 over x times cos 1 over x minus. So it'll be sine of u, but u is 1 over x. So it'll be sine of 1 over x plus c. Good. That is question 40. Let's erase that. Okay, cool. Let's move on to question 41. Question 41 is the integral of tan inverse of x over x squared dx. So this looks like probably integration by parts because we can easily differentiate that. So I'm going to say let's let u equal to tan inverse of x. So the derivative of that is going to be 1 over 1 plus x squared, yeah. Okay, and dv is going to be 1 over x squared. And we need to do the integral of that, so we're going to add 1 to the power, which will be x to the negative 1 divided by negative 1. So it'll be negative 1 over x. Should be dx. Should be dx. Okay. dx. Yeah. Okay, so then our integral basically becomes u times v, so it becomes negative 1 over x tan inverse x minus the integral of v du. So we're basically going to have to, minus becomes plus, so it becomes 1 over x times 1 plus x squared dx. Okay. So now we really only need to do that. So let's do this integral on the side. So let's do integral of 1 over x times 1 plus x squared dx over here. So we're going to use another kind of similar trick where we get the integral on the top. So we kind of want, we're probably going to have like a, okay, well, let's see what we get. So x, I'm going to factor out x squared here. So x squared, and we're left with 1 over x squared, or let's write it as x to the negative 2, plus 1 dx. Okay. And then now we have x cubed. Let's bring that up to the top. So it's going to be the integral of x to the negative 3 over x to the negative 2 plus 1. Now we have the, now what do we have? We have the derivative of that at the top, right? Which is quite nice. So if we have, well, the derivative of this is going to be negative 2x to the negative 3. So if I run negative 2 here, negative half here, then it works out nicely. And then we know that if you have the derivative of the top, it's just going to be ln. So it's going to be a half ln of x to the negative, negative 2 plus 1. Perfect. So that's what that thing becomes. So now we can sub that in into our overall integral here. And it's going to be negative 1 over x tan inverse of x plus that, which is, or minus, minus a half, minus a half ln of x to the negative 2 plus 1 plus c. Brilliant. Okay. That's question 41. Let's erase that. Perfect. Okay. That was question 41. Let's do question 42. Hope everyone, there's actually quite a few people there, 6 people. Maybe everyone's having lunch. So question 42 is the integral from 0 to infinity of x times, that's a nice easy one, finally, e to the negative x squared dx. Okay, so we want the derivative of the top bit at the bottom. So we almost have it. The derivative of the top would be negative 2x. So if we have a negative 2 here, we'll be happy. So to allow that, we have to have a negative 1/2 at the front. Okay. So then what this is going to become? It'll become negative 1/2, and the integral of that is e to the negative x squared, and we're doing it from 0 to infinity. If we sub in infinity, it's e to the negative infinity, which is going to be 0, so it's 1/2 times 0. If we sub in 0, it gives us 1, so minus 1. And if you do that, minus 1/2 times minus 1 is 1/2. That will be your answer there. Cool, let's erase that and move on to the next one. Okay. Hey, we got Mr. Tyron Bayless in the chat. I hope you're doing well. I hope you enjoyed your holiday. Okay. We'll dedicate this one to you, Tyron. I'll even do a drawing. Integral from 0 to 1 of the natural log of x dx. Okay, so let's do this one. So, how would I do this? Maybe let's do it doing a picture. So let's draw a picture on this side. So we know that the natural log of x graph kind of looks like that, okay? And we're doing from 0 to 1, so we're kind of doing from like here up until this point will be 1, okay? So we're kind of trying to find that area. And this is, let me just label my graph. This is ln of x. Okay, so one thing we could do to find this is, I remember we did this in maths, we can reflect this about the line y equals x, and it'll actually be the same area. So let's say this is the line y equals x. And if we reflect it around this line, then we'll have this kind of shape. Be that. And this graph will now be e to the x, right? That's the reflection of it. And now we're trying to find this area of it. The one thing we must remember is this is below the line, so this is going to be negative and this is going to be positive. Okay, so we must remember that. Okay, so we're doing this integral. So now we can say that this is going to be the same as the integral from, you see we're doing negative infinity to 0 now. Negative infinity to 0 of e to the x dx. But remember, we have to remember this one's negative, this one's positive, so we should put a little negative there, just to remind ourselves of that. Okay. After all our pictures, it's easy integral, so it's e to the x from negative infinity to 0. So e to the 0 is 1, e to the negative infinity is 0. So our answer is just negative 1. Very nice. Okay, hope you enjoy that one. Let's erase and move on to question 44. Okay. I just want to check on Twitch. It says unstable. Tyron, can you just type in the chat? Is it like lagging for you, or is it kind of chill? I don't know. It just says like unstable for me, but maybe it's just like bugging. Okay. So let's do question 44. So we're doing the integral from negative 1 to 1 of sine x over 1 plus 2 to the power of x squared dx. Okay, this one looks kind of crazy, but let's see if there's anything that we can do to, okay, very stable, awesome. So let's see if there's anything that we can do to make this a bit easier. So the one thing I immediately notice is that the bounds are like the same, like, or it's like symmetrical, it's like negative 1 to 1. So if we can show that this is an odd function, then it'll be 0. So what's the definition? Thinking back to first year. The definition of an odd function is if you sub in negative x to it, it basically gives you negative f of x. So let's try sub in negative x into this function and see what we get. So sine of negative x divided by 1 plus 2 to the power of negative x squared. Okay, we know that sine of negative x, that's kind of in quadrant 4. So it's going to give us negative sine x. And this is going to be 1 plus 2 to the x squared. Because it's, negative. And you see, that's just equal to negative. It's like equal to negative f of x, right? So therefore, we have, let's just write what we have. We have the integral from negative 1 to 1 of an odd function. And we know the integral of an odd function is always 0. So we can chill there. Hey, we got olive oil. I don't know who that is, but thanks for the clap. Very cool. Okay, let's erase this and move on to question 45. So thirsty. Okay. Question 45. We have the integral of negative 1 to 1. Oh, wait. Sorry, is that the one I just did? Oh, no. Okay, we're kind of doing the same one, but now it's flipped. So x squared over 1 plus 2 to the power of sine x. Okay, so before we had sine x and we have x squared. Yes, now it's kind of different. So I think now it wouldn't be an odd function. So I don't think we can use the same trick, but let's try maybe a u substitution. Okay, so let's let u equal to, let's try this. Let's let u equal to negative x. So then du will be equal to negative dx. And also let's just show that x, if we multiply both sides, is negative u. Okay. So then what we're going to get is we're going to get the integral from, let's just check, the bounds will swap because it's negative. So now it'll be from 1 to negative 1. Okay. Of x squared, which is negative u squared, over 1 plus 2 to the power of sine of negative u, and d, or it should be dx, sorry, and then dx is negative du, so negative du times. Okay, I'm going to use this negative to flip the things back, so it's going to be the integral from negative 1 to 1. Negative u squared will just be u squared over 1 plus, and then it'll be 2 to the power of negative sine of u du. Okay, so now we're going to do a little trick here. I'm going to multiply the top and the bottom by 2 to the power of sine of u. Okay, and that'll kind of get rid of this, and you'll see it'll do some nice things. So that's going to give us the integral from 1 to negative 1 of u squared times 2 to the power of sine of u over 2 to the power of sine of u plus 1 du. Okay, so does this even look much better? But what we've shown is that that is the same as that. Okay, and they look kind of similar. Okay, so what I'm going to call this, we know that, let's call this I. Okay, we know that they're equal. So this is also equal to I, right? So what I'm going to do is I'm going to add these together. Add both of those integrals together. Okay, so this might be a bit unusual, but we actually use this trick quite a lot in some of these questions that I'm going to do today. I think more later on when the harder questions come. So 2i, do we? Just I is 2i. So let's add these together. Also, we can change this back to x because this is just a dummy variable. So we can just, this is the same as like x squared sine of, because x and u, you can like, it's just a dummy variable of integration. So we can say this is the integral from negative 1 to 1. We add the tops, x squared plus x squared times 2 to the power of sine x over, obviously when we add fractions the bottom stays the same, so it'll be 1 plus sine, 1 plus 2 to the power of sine x dx. Quite nice, eh? One thing that I noticed is we can factor out an x squared here, so that's equal to the integral from negative 1 to 1 of x squared times 1 plus 2 to the power of sine x. Ooh, now we're getting excited here. Because this cancels with the bottom. 1 plus 2 to the power of sine x dx. And this is really cool because that cancels with that. So now we just have integral from -1 to 1 of x squared dx. How awesome is that? It's like simplification, really cool. And the integral of x squared is x cubed over 3, evaluated from -1 to 1. So it's going to be 1 over 3 minus -1 over 3, -1 cubed over 3. And that will basically be equal to oh wait, so this is 2i. Yeah, so this is equal to, sorry. Yeah, we're almost there. So this is 2 over 3. So then our overall integral, which is I, which we called it earlier, is basically a half of this. So it's a half times 2 over 3. So it's just a third. And that's your final answer. Okay. That was a bit of a crazy one, but we got there in the end. So the big thing of that one is we kind of made two equivalent integrals and we added them, and then that helps us to cancel some things from it allows us to factorize and cancel it, and then it gives us a very easy integral. Okay, let's erase and do question 46. Okay. Question 46. Okay, we're doing the integral of 1 over, what do we have? 1 plus sine x plus cos x dx. Okay. So I'm going to use quite an interesting substitution in here. We're going to say, let's let t equal to tan of theta. Okay, and this, sorry, not tan of theta, tan of theta over 2. And this is actually called the Weierstrass. I think that's called, right? Substitution. It's the Weierstrass substitution. Okay. I'm going to derive everything of this one, but you can also remember them because sometimes you use the substitution quite a lot. So, yeah. So let's draw a right angle triangle. That's going to be 90 degrees. We're going to say that that's theta over 2. So we're saying that tan is t, right? So then tan is opposite over adjacent, so it's t over 1. And then by part angle, we can say this is t squared plus 1. Okay. So what we really want is sine and cos, right? So let's find what a sine of theta will be. So sine of theta is equal to, we want it in terms of theta over 2. So we can kind of use the theorem of sine of 2 theta, but instead of 2 theta, we'll call this theta, and everything else will be theta over 2. So this will be 2 times sine of theta over 2, theta over 2, times cos of theta over 2. Okay. Let's sub in what you know. So we know that sine is opposite over hypotenuse. So it'll be t over square root of t squared plus 1 times cosine is adjacent over that. So it's going to be 1 over t squared plus 1. So if we multiply everything out, it's going to give us the top 2t over the bottom, or this should be a square root, sorry. Square roots will cancel, so it becomes t squared plus 1. Okay, that's what sine of theta is. Now let's work out what cos of theta is. So, cos of theta is going to be, which density should we use? Maybe we're going to use cos squared of, because yeah, we're going to say this is like theta, like 2, you really use that 2x one. Minus sine squared theta over 2. Okay, so you know that cos is that basically. So it's going to be that squared, which will be 1 over t squared plus 1 minus, and then sine is that, so it's that squared, so it's, you can actually make it all over, because it'd be the same, plus t squared. No, minus. Right? Yeah, minus. Yeah, because others will just cancel. Let me write that a bit better. So it's going to be, the cos is going to be that squared, and then it's going to be minus that squared. The bottoms will be the same, so it's going to be 1 minus t squared over t squared plus 1. And that's going to be cos of theta. Okay, let's also work out what dt would be. Okay, so we know that dt is basically just the derivative of this, so it's going to be a half sec, because we know the derivative of tan is sec squared of theta over 2 d theta. Okay. And we know that sec is 1 over cos, so it's going to be, cos is that over that, so it's going to be that over that. So it's going to be a half times square root of t squared plus 1 over 1 squared d theta. So you can multiply that out, and it's basically just t squared plus 1 over 2 d theta. Yeah, brilliant. Yeah, I think that's good for now. So that's dt. So then if we get d theta, if we want to just solve the other way around, so d theta will just be 1 over that. So it'll be 2 over t squared plus 1 dt. Okay. So these are the important results. That one, that one, that one. Okay, I'm going to erase this because I need to make more space, but we'll remember them. So sine of theta is going to be that. It's going to be 2t over t squared plus 1. Cos is going to be 1 minus t squared over t squared plus 1. And d theta is going to be 2 over t squared plus 1 dt. Okay, let's erase this, and then we'll do the substitution. Okay, so we did all of that work to prove the Weierstrass, but you don't need to prove it every time. You can just use it. But it's the integral of 1. Oh. So 1 over 1 plus, and sine was 2t over 1, 2t over 1 plus t squared. And then cos was 1 minus t squared. That's the Weierstrass. 1 plus t squared. And then I think we said d theta was 2 times 2 over 1 plus t squared dt. Okay. That's our substitution. Okay, so what are we going to do now? So let's take out this 2 from here. And then I'm going to multiply this into the bottom, because I know it seems like it's already at the bottom, but yeah, this is like a fraction over a fraction. So it basically becomes 1 over 1 plus t squared. Okay, multiplied by that one, it cancels out, so it just becomes plus 2t. Multiplied by that one, it cancels out, so plus 1 minus t squared dt. Okay. So now what I'm going to do, we see that the t squared cancels out with this minus t squared. So we basically just get 2 times the integral, sorry, the integral sign, 1 over, we also get 2, so we can cancel out, or factor it out, and then 1 plus t dt. Okay. We see that this 2 will cancel with this 2, and we know that this is just going to be a lim. So this is just going to be ln of 1 plus t plus, let's not do c yet. And remember, from before, we said that our substitution was t is equal to like theta over 2, but in this case it's x, so it's going to be tan of x over 2. So we can write our final answer as the natural log of 1 plus tan of x over 2 plus c. Good, that's 46. Okay, so erase this and do 47. Yay, almost halfway. Thanks, Layla. I'm gonna have lunch at halfway, so almost there. Only 3.5 hours. Yeah, not bad. Okay. 47. Okay. 47 is the integral of 1 over x times the square root of x to the power of 15 minus 1 dx. Okay, this looks a little bit whack. Okay, so make it look a little bit less weird, let us do a u substitution. Okay, so let's let u equal to the square root of x to the power of 15 minus 1. Okay, it's going to be hard to differentiate this, so let's rather simplify it a little bit. So then we can square both sides and add 1, so we get u squared plus 1 is equal to x to the power of 15. Okay, then let's just do the derivative from here, I think it'll be fun. So then du will be, we can do the chain, so the derivative of this will be 2, and then square root of x to the power of 15 minus 1. Then the derivative of the top will be inside that, because it's a chain rule. So it'll be 15x to the power of 14 dx. Yeah. Yeah, good. Okay. And we can notice that this is actually just equal to u. So we can just, when you write, we can just write that as u. Okay. So our integral is going to be equal to the integral of 1 over x times, and that is u, times, and we know that we can just dx is going to be like 1 over that. So it's going to be 2u over 15 x to the power of 14 du. Okay, we see that u cancels with that u, quite nice. And I'm going to take 2 over 15 out. So we want to, okay, we'll deal with this. So it's 2 over 15. The integral of 1 over x times x to the 14 is x to the 15 du. But we know that x to the 14 is u squared plus 1, so we can just sub that in, right? So it's going to be 2 over 15 times the integral of 1 over u squared plus 1 du. We've done this plenty of times. That is going to be tan inverse. So it's going to be 2 over 15 times tan inverse of u du. But we need to sub in what u is, so I'm going to sub that in for u. It's going to equal 2 over 15 tan inverse of the square root of x to the power of 15 minus 1 plus c. Brilliant stuff. Very nice one. Okay, that's 47. Let's erase and go on to 48. Let's put the cap on these and then dry out. Okay, question 48. Here's my mark, there we go. Question 48. Okay, so question 48 is the integral from 0 to infinity of sine x dx. Okay, we know the integral of sine x is negative cosine of x from 0 to infinity. But what happens if we sub in infinity to cos, right? It doesn't really make sense because cos oscillates, so it never really converges to something. So this actually will have no solution, but I'm just going to say it diverges. Okay, diverges. Happy with that. Oh, nice quick one. I don't know if I typed that in wrong or whatever. Okay, whatever, that diverges. Let's do question 49. Okay, so question 49 asks for the integral from 2 to infinity of 1 over the square root of x squared minus 1 dx. Okay. We're going to do another trig sub. I think we've seen one kind of similar to this. We're going to say x is equal to sec of theta. I think we kind of did a similar sub earlier. Okay. And that means that dx, derivative of sec, will be sec theta tan theta d theta. Okay, so if we sub that in, we're going to get integral from 2 to infinity of 1 over the square root of sec squared theta minus 1 times, and dx is sec theta times tan theta d theta. Okay, brilliant. We know that sec squared theta minus 1 is the same as tan squared theta. Okay, so we have 1 over the square root of tan squared theta. So that the square root and the square will cancel. So we basically have 1 over tan, and that'll cancel with this tan. So then that cancels. So now all we have is the integral from 2 to infinity of sec of theta. Okay. We've actually done this before. We did this, I think, one of our first questions. I think it was question 2. It's ln of the absolute value of sec of theta plus tan of theta. Yeah, and we're evaluating this in square brackets from 2 to infinity. Actually, wait, before we sub in, we should actually we should sub back in our x's, because I don't want to mess with the bounds. Yeah. So we know it's that, but we need to kind of sub our x's in. So I'm going to do a right triangle. Let's draw it here. I'm going to say that's theta. We said that sec x, sec theta was x. Okay, so sec is hypotenuse over adjacent, and then this one will be the square root of x squared minus 1. So if we sub back in for x, it's going to be ln of sec, sorry, not sec, because now sec of theta is just x. Tan of theta is that over that, so it's the square root of x squared minus 1. Okay, and now we can sub in our bounds, because now it's in terms of x. Our bounds are in terms of x. Now we can sub in 2 to infinity. Okay, if we sub in infinity, we get, ln. So we're going to get, let's write out what we get. Like, we get ln of, like, infinity plus, and infinity squared minus 1 is infinity. So infinity, so we kind of get ln of infinity, which is already infinity, minus ln of 2 plus root 5. Ooh, so therefore it diverges as well. Because this is kind of going to give you infinity minus a constant, so that's going to give you just infinity, so it diverges. Okay, and that's question 49. let's move on to question 50, and then we're going to have a little lunch break. Your neck gets surprisingly sore from looking sideways for the whole time. Okay. Question. Let me get my mic. Question 50. Okay. Question 50. We have the integral from 1 to 2 of 1 over x squared plus x minus 2 dx. Okay. So whenever you get questions like this, it's probably going to be a partial fraction question. Because we can factorize the bottom into x plus 2, x minus 1. Okay. So we know that, let's do it on the side. So we know that 1 over x plus 2, x minus 1 has to equal to a over x plus 2 plus b over x minus 1. Okay, so if we do the cover-up method, we cover up that and we sub in minus 2, we're going to get 1 over, so it's going to be minus 2 minus 1, so it's going to be minus 3, 1 over minus 3. Okay, and then b is going to be, if we cover up that and we sub in 1, it's going to be 1 over 3. It's going to be 1 over 1 plus 2. Yeah. Alright. So using the cover-up method, you split this into the integral from 1 to 2 of negative 1 over 3 over x plus 2 plus 1 over 3 over x minus 1 dx. Okay. So we can evaluate this. This should be 2 ln, so it's minus a third ln of x plus 2 plus a third ln of x minus 1 from 1 to 2. So we get minus a third ln of 4 plus a third ln, 0, that's not going to be good. minus plus a third ln of 3 minus a third ln also 0. Okay. Well, we know that. Well, let's. Let's think. What can we do here? Ln of 0. Okay, I actually want to do, maybe I'll try this a different way. Let's see if it works out. Maybe this sounds just dumb, so what I'm going to try to do. I'm going to try to combine these lns. So I'm going to write this as, maybe factor out, I'm going to factor out a third. And then we're going to get ln of basically that one, that was a positive one, so it's going to be x minus 1 over x plus 2 evaluated from 1 to 2. Yeah, I think, okay, well let's do it. So that's basically going to be a third ln of 1 over 4 minus a third ln of, because it'll be 0. So I'm just going to say ln of 0, so you get basically this becomes, let's look at the ln graph. It looks like that. So as you tend to 0, it actually goes to minus infinity. So basically this thing is equal to minus infinity. So it's basically equal to infinity, which implies diverges. Okay, and that is question 50. So I'm just going to have lunch now. Let me actually go into OBS and just I'm just going to put something on the screen that says lunch break. How do I do that? So I go plus text lunch. Okay, let's go into OBS and just save our video. So let's stop recording and start recording. Okay. Where are we? We're up to 51. Oh yeah, these are the stats integrals now. Cool. Okay, welcome back from the lunch break, and let us get started. 51. Okay. So for the first few, there's going to be with a uniform distribution. Okay. So I'm going to say x distributed uniformly between A and B. Okay. And if this is the distribution, then the density of it, fx of x, is basically with the distance. So 1 over the distance, so 1 over b minus a. Okay. And now let's show that this integrates to 1 over the whole bounds of interval. Okay, so this will be our first integral. So this is the integral from a to b, a to b of 1 over b minus a dx. Okay, quite a chill one, because what we can do is we can just, this is all constant, so this is just going to be equal to 1 over b minus a. The integral of 1 basically is x, and we're going to sub in a and b. Okay, so that's going to be 1 over b minus a times, if we sub in b minus a, and then we notice that that cancels with that. So cancel, and we're just left with 1. So that's exactly what we've expected. The integral of the whole density is equal to 1. Now, we can actually leave that on. Now let's do the expectation of x. Okay, so the expectation of x is going to be the integral of x times f of x. So x times 1 over b minus a dx. Okay, let's take that out. It's going to be 1 over b minus a. Integral of x is 1 over 2 x squared. Or I should say it's over, the expectation is over the bounds. So it's from a to b. So this will be from a to b. So 1 over b minus a times b squared minus a squared over 2. And we can factorize this. We can do difference of 2 squares, so b minus a times, so the top will be b minus a, b plus a over 2. And we can see that that cancels with that. So our expectation is going to be b plus a over 2, and that is integral 52. I don't think I labeled it 52. Okay. Good stuff. Let's erase this and then we'll move on to 53. Okay. Integral 53, we're going to do the normal distribution. Okay, so 53. I'm going to say that x is distributed normally with a mean of mu and variance sigma squared. So I'm going to do the integral over the whole bound. So the normal goes from negative infinity up to infinity of the density. And the density is 1 over the square root of 2 pi times sigma, so sigma is not in the square root, times exp, so that means e to the power of exp of negative a half, and then it's x minus mu over sigma squared dx. Okay, so for this integral, we're actually going to do a u substitution. Okay, so I'm going to say let's let u equal to this thing. So u is going to be x minus mu over sigma. Okay, and then if we want to solve for x, then we can say that we're going to multiply both sides by sigma and minus mu. So we're going to get that. Wait, what do we try to solve for x? Yeah. So we basically say that x is equal to sigma u minus mu. Don't mix up the u's and the mu's. So then dx is going to be just sigma du. Okay, perfect. So, what does that say? Okay, so what we can do now is we can. My mom just sent me a message saying there's an echo, but she said it's good now. So what we can do now is we can notice that we can basically just sub it in. So it's going to be equal to the integral from negative infinity to infinity 1 over the square root of 2 pi times sigma times exp negative a half, that's just u, so u squared, and then dx is sigma du. Okay, and we can see that this sigma will cancel with this sigma. Very nice. Okay, so now what we can do is we can take that out, and because it's a constant, so we get 1 over square root of 2 pi, pi integral from negative infinity to infinity of e to the negative a half u squared du. Okay, and this one is quite similar to the Gaussian. We haven't done the Gaussian yet, but we actually are going to do it later. And we'll find when we do it later, we'll see that this will be the square root of 2 pi. Okay, and then we can see that that will cancel with this. Boom, boom, and we'll just get 1, which is exactly what we'd expect. Very cool. Okay, that's number 53. Let's erase and then go on. Okay, let us do number 54. So now we're going to do some exponential stuff. So I'm going to say x is distributed exponentially with some parameter lambda. And let's show that the integral of the density is 1. So we're going to do the integral from exponentials only positive values. So 0 to infinity of lambda e to the negative lambda x dx. Okay, this one's quite a nice one because we can see the derivative of this is just going to be, if you put a negative there, then you have the derivative at the front. So then we can say, I have 2 pens open of black, but I need one. So then we can say that's going to be equal to negative e to the negative lambda x evaluated from 0 to infinity. Okay, well, we know that if we sub in infinity, it's going to be e to the negative infinity, which will be 0 minus, and then e to the 0 is going to be 1. Okay, so it's minus minus 1, so it's 1. Perfect, exactly what we would have expected. Okay, that is question 54. Let's do 55 next. Let me just erase this. Okay, question 55. Cool. So again, we're going to say x is going to be exponential with some parameter lambda. And now I want to find the expectation of x. Okay. So the expectation of x, just like before, it's the integral over the whole bound, but now it's of x times the density, which is e to the negative lambda x dx. Okay. So it's now we just need to do integration by parts. Okay. So I'm going to say let's let u equal to that thing, because we want to differentiate that. So let's let u equal to x. And then du will be equal to 1 dx. And then dv is just going to be whatever's left. So it'll be lambda e to the negative lambda x dx. Okay. And then v, we initially do the integral of this. We basically have the thing, but we just need a negative here. So it'll be negative e to the negative lambda x. Cool. Okay, so now we say out our thing will be u times v, so it's negative. I'll sub in the bound end, so negative x e to the negative lambda x minus the integral of v du. So minus minus, that becomes a plus e to the negative lambda x dx. Okay, so it's negative x e to the negative lambda x plus the integral of this is going to be, we need a negative lambda here, so we need a negative 1 over lambda here. So it would be minus 1 over lambda e to the negative lambda x. And now let's do our bounds. So it's from 0 to infinity. Okay. So we can't, so this is going to be a problem, so we're going to have to do L'Hopital. So I'm just going to write it, for example, now as a limit. So it's going to be the limit as x tends to infinity of negative x over e to the negative lambda x, because it's the negative exponent. But we can sub in infinity here, and e to the negative infinity is going to give us 0. So it'll become plus 0. And then when you sub in 0 here, that's instantly going to give us 0. I guess minus 0. And then when you sub in 0 here, that's going to give us minus lambda. Because if you sub in 0 here, it gives you e to the 0, which is 1. So 1 times minus lambda is minus lambda, but it's minus lambda. Okay, cool. So now we just need to do this. So we're going to do this using L'Hopital's rule. So we do the derivative of the top, derivative of the bottom. So it's going to be the limit as x tends to infinity of negative 1 over derivative of this is going to be negative lambda e to the negative lambda x. Okay, plus 1 over lambda. Okay. And if we sub in, now we can sub in infinity because there's no x to the top. So that just becomes 1 over infinity, so it becomes 0. So our whole answer is just 1 over lambda. Quite cool. So we've just proven that the integral, that the expectation of exponential, which is this integral, is equal to 1 over lambda. Okay, I'll erase this now. Okay, question 56. Okay, so again, it's also going to be exponential. So x is exponential with a mean lambda. And now what I want to find is the variance of x. Okay, so we know for the variance of x, we can find it using expectations. We can say it's the expectation of x squared minus the expectation of x all squared. Okay. We already know that from the previous integral we did, this was 1 over lambda. So now we just need to find the expectation of x squared. Okay. Expectation of x squared. That's just going to be the integral from 0 to infinity of x squared times the density, which is lambda e to the lambda x dx. Okay. So this is going to be an integration by parts, but we're going to have to do it twice. So I recommend using the DI method. DI. So we're going to have to do the derivative of x squared and the integral of of, let's make this lambda. Actually, I'm going to group it. I'm going to group it like this. There'll be lambda x squared, and then this will be e to the negative lambda x. Okay, and then it becomes plus, minus, plus. I think we need one more, maybe, minus. Okay, so derivative of this is going to be 2 lambda x, derivative of this is going to be 2 lambda, and derivative of that's going to be 0. Okay, now we need to do a bunch of integrals. The integral of that, 1 over, because you do the 1 over the derivative, e to the negative lambda x. That's going to be plus 1 over lambda squared, e to the negative lambda x. And this will be minus 1 over lambda cubed, e to the negative lambda x. Okay, and then to get our integral by parts, we just times that by that, and that by that. So, it will be, let's get our black pen. It's going to be that times that, so lambda x squared. Ooh. You see that and that actually cancel out, lambda times 1 over lambda. So it's just going to be minus x squared times e to the negative lambda x. And then that times that is going to be minus. You have lambda over lambda squared. So the lambda at the top is going to cancel. We just get minus 2 over lambda e to the minus lambda x. And we get that times that, so it becomes minus 2 over lambda squared e to the negative lambda x. Okay, we're evaluating this from 0 to infinity. Okay. Brilliant. Okay, I think now what we can do, those two are going to be problems, so we're going to have to do those by L'Hopital. Let's just do it on the side, actually. So I'm going to do the derivative of that thing. So the derivative of that is going to be negative 2x over negative lambda, becomes plus here, e to the lambda x. Okay, but we still have a problem here, so we need to do another derivative. So then that'll give us 2 over lambda squared yeah, sorry, it should actually be negative. I don't know, I mean positive negative. Negative 2 over lambda squared e to the negative lambda x. Okay, that's for that one. Then we also need to do L'Hopital for this one, so let's do the derivative of that. So it's going to be negative 2 oh, sorry, I forgot to put x here. Yeah. So it's negative 2, and then the derivative at the bottom is going to be negative, so I guess I'll make it a positive. I guess that's why it's a positive. Yeah, it's a positive, yeah. Lambda squared e to the negative lambda x. Okay, so now we can evaluate this. So if we sub in infinity into this one, we get 2 over blah blah blah. You get e to the negative, should just be not negative, just e to the lambda. So you basically get 1 over infinity, which is just 0. That'll give you 0. Plus, that'll also give you 0, because if you sub in here, you also get something over positive, yeah, e to the lambda x. So something over infinity is 0. If you sub in here, you also get 0, because you get e to the negative infinity, which is 0. Now let's sub in 0. So this gives us, so 0 times x, well, that will immediately give you a 0. So you have an x here, immediately a 0. So the only thing that will really have anything is this one. And if we sub in 0 here, we get a 1. So it just becomes minus 2 over lambda squared. So this whole integral is just equal to minus 2 over lambda squared. Oh, but it's minus, so it should actually be plus. Yeah, so it's just plus 2 over lambda squared. So that's the answer of the integral, but now let's find the variance. So the variance of x, remember we said it was this, expectation of x squared, which we found was 2 over lambda squared, minus that, so minus 1 over lambda all squared. So the base is going to be lambda squared, and it's going to be 2 minus 1. So it's just going to be 1 over lambda squared. So we showed that our variance of an expectation of an exponential is 1 over lambda squared. Awesome. Let's erase this and then keep going. Okay, and I see Layla said I must dedicate the number 67 to Sonia, so I'll when I get there I'll dedicate it to her. Okay, that was number 56. Let's go on to 57. Okay, we're still an exponential, but now I'm going to find the CDF. 57. Okay, so to find the CDF of an exponential, well, the CDF of anything is the integral from 0 to x of the density, which is lambda e to the negative lambda x. Okay, so we can put the derivative at the bottom, negative, negative, and then that will give us negative e to the negative lambda x from 0 to x. Well, should I maybe just, I'll do this in terms of like t maybe, because I don't want the same variable. So I'll call this dt, and then I'll call this t. Okay. So then we sub it in, so I'll get negative, if we sub in x, it'll be e to the negative lambda x, and if you sub in 0, it gives you 1, so minus 1. And then I'm going to distribute in the negative, which will basically swap the order, so it becomes 1 minus e to the negative lambda x. Boom! And that's your, you can call this your CDF of x for exponential. Okay, we finished with exponential, now we're going to go on to the gamma, but let me just erase this first. Okay, we are on question 58, and we are going to call this one the Dev-Lacey integral. Shout out to Devin Lacey, absolute legend, and we're dedicating this one to him. So, we're going to say that x is distributed gamma with parameters alpha and beta. Okay, and I want to show that the integral of the density is 1. Okay, so the gamma is only defined for like x greater than 0. So it's going to be the integral from 0 to infinity, and the density is beta to the alpha over gamma of alpha times x to the alpha minus 1, x to the alpha minus 1 times e to the negative beta x dx. Good. So yeah, man, the class chose the gamma function, which is really cool. A lot of things linked to gamma. We use this a lot in Bayesian analysis and stuff like that. So, pretty cool one. So, what I'm going to start with here is I'm going to start with taking this out, because this doesn't involve x, so it's kind of all constant, okay? So I'm going to say that's equal to beta to the alpha over gamma of alpha, then the integral from 0 to infinity of x to the alpha minus 1 e to negative beta x dx. Okay. Now I'm going to do a u substitution. So I'm going to say let's let u equal to beta of x, which is that thing, right? Okay. So then x, that means x, if we divide both sides by beta, is going to be u over beta. And then dx is going to be, in terms of u, 1 over beta, u. Yeah, no, just 1 over beta, because it goes away, yeah. du, yeah. Okay, so now let's sub in what we have. So it's basically going to be equal to the front bit, beta to alpha, gamma of alpha. The integral, let's check our bounds. So if x is 0, then u will also be 0. And if x is infinity, then u is also infinity. Okay, and then x is u over beta to the power of alpha minus 1, and then e to the negative u. Okay, cool. E to the negative u, and it's dx is 1 over beta du. Cool. Okay. So let's see what we can do. So I'm gonna beta to the alpha over gamma of alpha. So what I'm gonna do is I'm gonna distribute this in. So it's gonna be the integral from 0 to infinity of u to the alpha minus 1 over, and DC will get beta to the alpha minus 1, but then we also have a beta here. So we have to add that one, so it'll be alpha minus 1 plus 1. So it'll just be beta to the alpha. Okay? And then e to the negative u du. Okay. And that's quite nice because now we can cancel this with that. Okay. And another thing you must know is that we have this definition. Let me write it here. This definition that gamma of alpha, the definition of it is the integral from 0 to infinity of x to the alpha minus 1 times e to the negative x dx. Okay, so that's the definition of the gamma function. And we're actually going to do later on, in the famous integrals, we're actually going to prove that, we're going to prove a few things about this. So we're going to show that it's equal to the factorial. We're going to show that gamma of alpha plus 1 is gamma of alpha times alpha. So we're going to show all of that stuff. But for now, you can just accept this, okay? So you can see that that's actually exactly what we have here, except u and x are switched. So it just means that, and it's basically the same because it's just a dummy variable of integration. So this whole thing is just equal to gamma of alpha, okay? And now we can see, that's quite nice because we have 1 over gamma of alpha and gamma of alpha here. So they just cancel out. And you're just left with 1. So the de Lacy integral, the integral of the whole of your gamma function just ends up being 1. Okay, let's erase this and then I'm going to move on to the next one. Okay, question number 59. Okay, so again, we still continue with the gamma. So x is distributed gamma with parameters alpha and beta. But now what I want the expectation of x. Okay, so we saw earlier how to find the expectation. All you have to do is you do the integral over your whole bound of x times the times the density. So it's beta to the alpha over gamma of alpha times x to the alpha minus 1 times e to the negative beta x dx. Let's take out our constants. So it's going to be beta to the alpha over gamma of alpha times the integral. So you see an x here, so we can add them. So it just becomes the integral from 0 to infinity of x to the alpha, right? Because it's alpha minus 1, and then this is x to the 1. And then e to the negative beta x dx. Okay. Now what I'm going to do is I'm going to write this in a certain way. So we have x to the alpha. So what I'm going to do is I'm going to write this as x to the alpha plus 1 minus 1. And I'm actually going to rewrite the definition of the gamma function. So gamma of alpha is the integral from 0 to infinity of x to the alpha minus 1 times e to the negative beta x dx. Okay, so now we can see that what we have here looks really similar, except instead of an alpha, we have an alpha plus 1. Okay, so basically this is the definition of gamma of alpha plus 1. Okay. No, wait. Is it? I just want to check something? Oh, it's not quite, because that and that aren't the same. Okay, no, we can't do this yet. Sorry, we first need to do our substitution. I was getting my order confused. Okay, so it's almost there. Yeah. We can't quite do that. Let me just erase this. So we just have x to the alpha. Yeah, for now. Okay. So now what we're going to do is we're going to do a substitution. Okay. Same substitution as before. We're going to say, let's let u equal to beta x. And that's going to mean that x is equal to u over beta, and dx is going to be 1 over beta. Okay. So our expectation is going to be beta to the alpha over gamma of alpha. Integral, the bounds will be the same, integral 0 to infinity. Instead of x, we're going to write u over beta to the alpha times e to the negative u du. Okay, cool. So now what we're going to see is that we're going to get beta to the alpha over gamma of alpha, integral from 0 to infinity of u to the alpha, beta to the alpha, e to the negative u du. Okay, so once again we see that this beta to the alpha and this beta to the alpha will cancel out. Okay, and now I can write this as same as what I tried to do earlier, so u to the alpha plus 1 minus 1. Okay, but now I see that this u and this u are the same, so now it works. Okay, so this is basically the same as that, but here we have alpha minus 1, here we have alpha plus 1 minus 1. Okay, so this is basically the definition of gamma of alpha plus 1. Yeah. Okay. So now we can say that this is equal to alpha plus gamma of alpha plus 1 over gamma of alpha. Okay. And as we're going to show later on, wait. I forgot to times my d. This is supposed to be dx is 1 over beta. It's supposed to be 1 over beta here. So it cancels. So we're actually supposed to have this. We're supposed to be 1 over beta here. And this should have a beta here. Yeah, there we go. Okay. I was wondering, something looked weird to me. Okay. So there's a property. We'll prove it later, but there's a property where you can say alpha of gamma is equal to gamma of alpha plus 1. So you can basically like reduce the gamma of alpha plus 1 to that. Okay, so we're going to use that here. So I'm going to write this as alpha gamma of alpha over beta gamma of alpha. Now we can see nicely that the gammas of alpha cancel, and then our expectation is just alpha over beta. And that is the expectation of a gamma. Okay. Got the expectation, so it's question 59. Question 60, we're going to do the variance, but let's just erase this. Hey, it's Brady. Hope you're doing well. Hope you're ready to learn about the variance of gamma. So we're doing the variance of x, where x is gamma. So we know the variance is the expectation of x squared minus expectation of x all squared. Okay. And in the previous integral, we showed the expectation of x is alpha over beta. So now we just need to do expectation of x squared. It's going to be the integral from 0 to infinity of x squared times the density of the gamma, which is beta to the alpha, gamma of alpha, x to the alpha minus 1, e to the negative beta x dx. Let's take out our constant. So beta to the alpha over gamma of alpha times, if we combine these x's, it becomes the integral from 0 to infinity of x to the alpha plus 1 times e to the negative beta x dx. Okay, Now we're going to do a substitution. So I'm going to say, let's let u equal to that, beta x. Okay, if we rearrange this, then x will be equal to u over beta, and then dx will be equal to derivative of that, 1 over beta, in terms of u. Yeah, du. I don't know if I wrote the du last time. Anyway, let's put this in. So it's going to be beta to the alpha over gamma of alpha, integral from 0 to infinity, of, instead of x, we're going to write u over beta to the power of alpha plus 1 times e to the negative u, and then dx is 1 over beta, don't forget this time, du. Okay, cool. So I'm going to expand this again. So it's going to be beta to the alpha over gamma of alpha, integral from 0 to infinity, of u to the alpha plus 1 over beta to the alpha plus, it's going to be plus 1 and then another one, so plus 2, times e to the negative u du. Okay. We can cancel out this beta with alpha with the beta, and we're left with beta squared basically. So this is going to leave us with like a beta squared here. We'll take that out. So let's do that here. So basically we have 1 over beta squared times gamma of alpha, integral from 0 to infinity, of u to the alpha plus 1. I'm going to write this in a certain way. Alpha plus 1 minus 1 times e to the negative u du. And again, if you have a look here, this looks very similar to gamma of alpha, but except instead you have u to the alpha plus 2. Okay, so this is going to be the definition of gamma of alpha plus 2. Okay, so this is going to be equal to gamma of alpha plus 2 over beta gamma, so beta squared, gamma of alpha. Yep. And then I want to use the same expansion. So I'm going to say this is equal to alpha plus 1, gamma of alpha plus 1 over beta squared, gamma of alpha. I want to expand it again because I want to cancel it with this. That's going to be equal to alpha plus 1 times alpha, gamma of alpha, over beta squared, gamma of alpha. Okay, now we can see that the gamma of alpha cancels nicely with the gamma of alpha. Yeah, and that is our expectation of x squared, but we're looking for the variance, right? So, the variance of x is going to be the expectation of x squared, which is alpha squared plus alpha over beta squared, minus that squared. So it's going to be minus alpha squared over beta squared. That's quite nice. And then you can see the same base, so you can see that that is going to cancel out with that. And then our variance is just going to be alpha over beta squared. Very cool. So variance of the gamma, alpha over beta squared. Okay, let me erase this, and then we're going to go on to the beta distribution. Okay. There's my pen here. Number 61. Okay. So I'm going to say x has a beta distribution with parameters alpha and beta. There's going to be a lot of betas. And then I want to show that the integral of the whole area is going to be, of the whole bound is going to be 1. Okay. So I'm going to do the integral from 0 to 1 because beta is defined when x is between 0 and 1. And the distribution is 1 over the beta function. So this is just like a normalizing constant kind of. times x to the alpha minus 1, and then times 1 minus x to the beta minus 1. Okay, so we're going to do this integral. Okay, so the first thing we should do is I'm going to take out a constant. So it's equal to 1 over beta of alpha and beta function, integral from 0 to 1 of x to the alpha minus 1, 1 minus x to the beta minus 1 dx. Okay, it's probably good to know what this beta function is, so let's show the definition. The definition of beta of alpha and beta is equal to the integral from 0 to 1 of x to the alpha minus 1, 1 minus x to the beta minus 1 dx, which is exactly what we have here. I know you're going to say it's a bit of a cheat or whatever, but this thing is basically just the beta function of alpha and beta. Okay, so we can see it's going to nicely cancel with the bottom here, and we're just going to be left with 1. Brilliant, so that's exactly what we wanted to do. Okay, let's erase this, then I'll go on to 62, where I'm going to show you the expectation of the beta function. Okay. Number, I'll just skip the definition, whatever. Number 62. Okay. So again, we're going to say that x has a beta distribution with parameters alpha and beta. And now I want you to find the expectation of x. That's going to be integral from 0 to 1 of x times the density, beta function of alpha and beta, x to the alpha minus 1, 1 minus x, beta minus 1 dx. Okay. Brilliant. So, what I'm going to do is I'm going to take this out and combine our x's. So this is going to be 1 over beta function of alpha and beta, the integral from 0 to 1 of x to the alpha times 1 minus x to the beta minus 1 dx. Okay. And I should have kept this definition. The definition of the beta function of parameters alpha and beta is the integral from 0 to 1 of x to the alpha minus 1 times 1 minus x to the beta minus 1 dx. Okay, so what we can do to kind of get in the same form, we're going to write as alpha plus 1 minus 1. So now it's going to be, so now this thing is going to be the beta function of alpha plus 1 and beta. Okay, so this is basically just going to be the beta function of alpha plus 1 and beta over the beta function of alpha and beta. Okay, so now how do we simplify this? You have to know another thing. So we have to know that we can write betas in terms of gammas. So the beta function of alpha and beta, we can also write this as gamma of alpha times gamma of beta divided by gamma of alpha plus beta. Okay, that's going to be really useful here. So now we can write this as, so let's first do that one. So it's going to be gamma of alpha plus 1 times gamma of beta over gamma of the sum of them, right? Alpha plus 1 plus beta. So it's divided by this. I'm just going to do times and I'm going to flip it. So it's going to be times gamma of alpha plus beta, and it's the sum of them, divided by gamma of them each individually. So gamma of alpha, gamma of beta. Okay. And we can see already that that is going to cancel with that, which is quite nice. Okay. And then I'm going to expand them so that even more stuff can cancel. So I'm going to expand this one, and we know that gamma of alpha plus 1 is alpha times gamma of alpha. and then that's times gamma of alpha plus beta. And I'm going to expand this one, and that's going to be equal to alpha plus beta times gamma of alpha plus beta, because I basically just minus 1. And that's all times by gamma of alpha. Now we can see really nice. Gamma of alpha cancel gamma of alpha. Alpha plus 1, gamma of alpha plus beta. Yeah. And we just left with our expectation, which is alpha over alpha plus beta. Very cool, very cool. Okay, that's our expectation. So now let's rub this off, and I'm going to show you how to find the variance of the beta function, of the beta distribution, sorry. Ugh, my mic keeps falling. Just go to OBS, how's it looking there? Yeah, it's looking good, I think. Wait, just increase the volume a little bit. Yeah, that looks good. Okay. Okay, should not erase that. I'm just gonna keep that. Okay, so let me figure out this definition. Definition, beta function of alpha and beta, integral from 0 to 1, x to the alpha minus 1 minus x, beta minus 1, dx. Okay. So, now what we want to do is now I'm going to ask you to find the variance. Okay, well, let's just write it. It's question 63. So I'm going to say x has the beta distribution with parameters alpha and beta. And then I'm going to say what is the variance of x. Okay, so similar to what we've done before, we know that the variance is equal to the expectation of x squared minus the expectation of x all squared. And we found in the previous one that the expectation of a beta is going to be alpha over alpha plus beta. Yeah, okay. So now we just need to find the expectation of x or x squared. So the expectation of x squared. So it's going to be the integral from 0 to 1 of x squared times the density beta of alpha and beta. These are a bit repetitive, so if you're getting bored, you can tune out and come back in like 10 minutes when I'm finished with these. X squared times beta of alpha beta times x to the alpha minus 1 times 1 minus x to the beta minus 1 dx. Okay, cool. I'm going to take out this, combine our x's, just like similar to before. It's just going to be a little bit different now. So it's going to be, take out our constants, so it's going to be 1 over beta of alpha and beta, integral from 0 to 1 of x to the alpha plus 1, okay, and then times 1 minus x to the beta minus 1 dx. Yeah. Okay, and I'm going to try writing this form again. So I'm going to write it as like plus 1 and then minus 1, and now it's in that form, kind of. So now this thing, this is going to be gamma of, sorry, not gamma, beta, it's the beta function, yeah. Beta of alpha plus 2, because you see in brackets we have alpha plus 2, and beta. Okay. So what we have is we have beta of alpha plus 2 and beta, the beta function, sorry. Yeah, there's a difference between the beta function and our beta variable, but it's, yeah. And the beta function of alpha and beta. Oh, I feel like I've said beta like 10 times in the last minute. Okay, so now we're going to do the same thing. We're going to use this, how we can write betas in terms of gammas. So this thing is going to be gamma of alpha plus 2 times gamma of beta over gamma of alpha plus 2 plus beta. So it's divided by this thing, so I'm just going to times it by the inverse. So it's going to be times gamma of alpha plus beta over gamma of alpha, gamma beta. Okay, cancel that. And then we can use this fact. We can use the fact that gamma of alpha plus 1 is equal to gamma of alpha to basically expand these. So it's going to be alpha plus 2. So now alpha plus 1. So that'll be times gamma of alpha plus 1, but I want to expand it even more. So let's times that by alpha, and that'll be gamma of alpha. Okay. Divided by, I'm going to do the same here. So it'll be alpha plus 1 plus beta. I want to expand it one more time, so alpha plus beta, gamma of alpha plus beta, times gamma of alpha plus beta over gamma of alpha. Cool. You see some really nice cancellation now. Cancel. And we're left with our expectation of x squared being this basically. Okay? So I'm going to multiply it out, so it basically becomes alpha squared plus alpha. Should I multiply the bottom squared? No, let's not. Over alpha plus 1 plus beta times alpha plus beta. Okay, so we've got our expectation of x squared, but what do we want? We wanted the variance, right? So to find the variance of x, it's going to be that. So it's going to be alpha squared plus alpha over alpha plus 1 plus beta times alpha plus beta minus, it's minus that squared. So it's minus alpha squared over alpha plus beta squared. Okay, we need to get this over a constant denominator. So our denominator is going to be alpha plus 1 plus beta times alpha plus beta squared. Okay, so we need to multiply this by alpha plus beta squared. So let's do that in our heads. So it's going to become, if we multiply, I'll just write it just so we can see. So we want to multiply this by alpha plus beta. Okay, so if we multiply that, we're going to get, it's hard to write this angle, alpha cubed, so that's that, and then plus alpha squared beta plus alpha squared plus alpha beta. Okay, and then we need to multiply this thing by alpha plus 1 plus beta. Okay, so it's going to become minus alpha cubed minus alpha squared beta. You get some nice cancellation. That cancels with that. Alpha squared beta, alpha squared, oh, not that. Alpha squared. Okay. And we are left with our variance being equal to alpha beta over this, which is alpha plus beta plus 1 times alpha plus beta squared. Okay, that is the beta distribution. Hope you guys are not too sick of it. I'm going to now erase this and I'm going to do the chi-square distribution. Yeah. Okay, before I do the next one, also just a reminder, I'm doing this is like it's like a charity challenge, and I'm raising money for the charity called Chalk. So if any of you guys joined through the link on my story, the next thing is like I think it's the link to the charity. So a lot of you guys have already donated, and I really appreciate it. But yeah, if you have anything to give, it would be really cool if you could donate there. Okay, let's move on to the next one. So this is question. Hey Tash.
How's it going?
Good.
Okay. Good.
Yeah.
Well done on the last one.
Thanks.
Tricky.
Okay, this is question 64. So we're going to say x has a chi-squared distribution with k degrees of freedom. Okay, and I want to show that the area under the whole density is going to be 1. Okay. So let's do the integral from the chi-squared is from 0 to infinity. So it goes from 0 to infinity. And the density is 1 over 2 to the power of k over 2 times gamma of k over 2. X to the power of k over 2 minus 1 e to the power of negative x over 2 dx. Okay, so this is basically the density of the chi-squared. Okay, so maybe let's start by taking out our constants. So these things are all involving, not involving x, so we can take them out. So it's just basically going to be 1, 2 to the power of k over 2, gamma k over 2, integral from 0 to infinity, 0 to infinity, of x to the power of k over 2 minus 1, e to the negative x over 2 dx. Okay, so now we're going to do a substitution. I'm going to say let's let u equal to x over 2. So if u is x over 2, then that means that x, if we multiply both sides by 2, is going to be 2u, right? And that means dx is going to be 2 du. Okay. So we're going to get our front bit, so 2 over k over 2, gamma of k over 2 integral. So let's check the bounds. So if we sub in 0, it'll still be 0. Sub in infinity, it'll still be infinity. So instead of x now, we're going to write it as 2u to the power of k over 2 minus 1, and then e to the negative u du. Okay. So let's expand this. So it's going to be 1 over 2 to the power of k over 2, gamma k over 2, integral from 0 to infinity, of 2 to the power of k over 2. This should be a 2, yeah. So remember, we changed it to du, and dx was 2 du, yeah. So the 2 will be 2 to the power of k over 2 minus 1 plus this one. So it just becomes 2 to the power of k over 2. And there'll be u to the power of k over 2 minus 1, e to the negative u du. And we see this is really nice, because now this cancels with that, which is very nice, okay? So now we get, and that's another thing, let's also remind ourselves what's the definition of gamma of alpha, okay? The definition is integral from 0 to infinity of x to the power of alpha minus 1 e to the negative x dx. Okay, so we can see that this thing looks really similar to this, and if we subbed in alpha equal to k over 2, okay? And that's really cool, because that means that this is the definition of gamma of k over 2, right? Because this is gamma of alpha, gamma of k over 2. Then we can see that that means that we have a gamma of alpha k over 2, gamma of k over 2. So that cancels out, cancels, and we're just left with 1. I've shown that the area under the whole chi-squared is just 1. Okay. Our final distribution that we're doing for stats is I'm going to show you the expectation of the chi-squared. So let me rub this off and then we'll do that. Whew, how many hours? 5 hours. Okay, going strong. Okay, so now what I want to find, we're still going to say x is chi-squared, but now what I want to find is I want to find the expectation of x, okay? So we know that that's going to be, I'm actually going to take out the constant right away just because it's going to be easier. So the constant was 2 to the k over 2, gamma of k over 2, integral from 0 to infinity of x times the density, which is like that times what I'm about to write now. So it's x to the power of k over 2 minus 1, and then e to the negative x over 2 dx. And we see that we can combine that x and that x to basically make this just x to the power of k over 2. Okay, so now let's do our u sub. So I'm going to do exactly the same u sub as when we were before. So I'm going to say let's let u equal to x over 2. Okay, so that means that x is going to be 2u, and that means that dx is going to be 2 du. Okay, so, okay, let's show this one here. Don't really need this. Okay, so that means that our expectation is going to be equal to this constant, 1 over 2 to the k over 2 gamma k over 2. Bounds are going to stay the same because 0 times 2, yeah. And it's going to become 2u to the power of k over 2 times e to the negative u times 2 du. Okay, so I can see that when you distribute in, this 2 to the power of k over 2 is going to cancel with that. Okay, I'm also going to take that 2 out. So we're going to have 2 over gamma k over 2. And we have the integral from 0 to infinity of u to the power of k over 2 times e to the negative u du. Okay, again, it looks kind of like the definition of the gamma, but we need like a minus 1. So what I'm going to do is I'm going to say plus 1 here, and then minus 1. Okay, and now this is the definition of gamma of k over 2 plus 1. Okay, so we can sub that in. So we basically have 2 gamma of k over 2 plus 1 over gamma k over 2. Okay, we're going to use this law of gamma. So gamma of alpha plus 1 is equal to alpha gamma of alpha. So I'm going to say that that's equal to 2 times, I'm basically taking out like, so 2 times k over 2 gamma of k over 2. So basically that expands to that over gamma of k over 2. Yeah. Okay. That gamma is going to cancel with that gamma, and that 2 is going to cancel with that 2. So we're just left with k. Oh, cool. So the expectation of the chi-squared distribution with k degrees of freedom is just k. So it's basically how many degrees of freedom you have. Oh, I think this was question 65 actually. I think I miswrote it. I'm pretty sure that was our last. Yeah, I think I just didn't erase that first part. Yeah, that was question 65. So that is the end of our stats integrals. Okay, so I'm going to erase this, and then we're going to go on to some like mixed bag integrals. There'll be a bunch of different things, all lots of fun. Okay. Question 66. All finished with the stats. Okay. So question 66, we're going to do the integral of e to the power of square root of x dx. Okay. So this is going to be a u sub. So we're going to say let's let u equal to the square root of x. Okay. So we probably want to solve for x to do the derivative. So then x is going to be u squared. So that means that dx is going to be 2u du. Yeah. Okay. So then our integral is basically going to be equal to integral of e to the u times 2u du. Okay. So now it looks like a classic integration by parts. Okay, I know it's going to be weird with the u's and u's because I use u's for my integration by parts, but let's just let u equal to 2u. So then du is going to be equal to 2 du. Okay, don't worry too much about the letters. Maybe I should use different. No, it's fine. I think you guys understand. And then dv is going to be e to the u du. So then v is just going to be e to the u, because we know the integral of e to the u is e to the u. Okay. So after that integration by parts, we know that it's going to be uv, so it's going to be 2u e to the u minus the integral of v du. It's going to be minus 2 integral of e to the u du. Okay, so 2u e to the u minus 2 e to the u plus c. Okay, we're not finished because we still need to sub in what our u is. Just write it here. So our final answer is 2 root x e to the root x minus 2 e to the root x plus c. And that is our final answer for question 66. Someone seems really excited for the next question, so yeah. And now, the one that you guys have all been waiting for. Integral 6/7. Okay, hope that wasn't too cringe. So, let's do, I think I gave myself an easy one for this one. Yeah. Little break. So it's the integral of the fourth root of x dx. I see everyone in chat. I'm glad you guys liked that. I'm glad you guys liked it. Okay, so it's a nice easy one. We can just expand this as x to the quarter dx. And we know that we'll integrate, we add 1 to the power. So it's going to be x to the 5 over 4, and then we divide by that. So we times by the inverse, and then we add c. Super quick one for 6/7. Awesome. Okay, happy with that one. And wait, I had to dedicate this one. So this is Sonia's integral dedicated. Okay. Hope you guys all enjoyed that one. Let's move on to question 68. Like an old man getting out of the chair. You think I'm a nerd because I said 6/7? I've done 60 integrals. I think that makes me more of a nerd than saying 6/7. Okay, let's do question 68. Okay, we're back to the spicy one. So this integral of the square root of tan x divided by sine of 2x dx. Okay, this is going to be another u sub, our favorites. So let's let u equal to the square root of tan of x. Okay, so then let's do the derivative of this. So we're going to have to use the chain rule. So it's going to be 1 over 2 square root of tan of x. So that's like the derivative of that. And then you have to times by the derivative of tan x, which will be sec squared x dx. Okay. So now let's sub that in. That's going to be the integral. So of u over sine of 2x. So we can make expand sine of 2x using like 2 sine x times cos x. Okay, we'll see what we have to do there. And we have to times it by, what should we do here actually? Okay, I guess we just sub this in. So it's basically going to be sec squared x. Oh, that should be. I want to, okay, yeah. We want to do u. So basically I want to do 1 over this. So basically I want to do 2, and square root of tan is u, so 2u over sec squared x dx. Okay. Yeah, I think that's right, because you're basically flipping it, yeah. Yeah, okay. And we know that, okay, well let's multiply this along. So we can cancel these 2's, that 2 cancels with that 2. And then at the top we're going to get the integral of u squared. And we know that sec is 1 over cos, so this is like 1 over cos squared x. So we can kind of cancel this cos with one of them, and then we get basically sine times 1 over cos. So this basically becomes u squared over sine over wait. It's 1 over cos. So it's 1 over 1 over. So this basically becomes cos x over sine x. Should be du actually. Du. Okay. And we know that this is the definition. This is like 1 over, this is 1 over tan, right? So 1 over tan is called cotan or cot. This is cot x. Okay. So we have the integral of u, let's write it as u squared times cot x dx. du. I've been messing that up. Okay. We know that, but, okay, so now let's find what cot x is, right? So from here, we know that tan x, is, if we square both sides, is u squared. So that implies that cot x, which is 1 over tan, is going to be 1 over u squared. Ah, now we see it's really nice. Because now we're going to get basically the integral of u squared times 1 over u squared du, which just gives us integral of 1 du, which is equal to u. And we know that u is the square root of tan x. So that is our final answer. I think that's a very nice one. Plus c. How could I forget the plus c? Plus c. That's number 68. Tristan says genuinely screw trig integrals. not a big fan. Okay. Well, the next one I think you'll like even more because it's an inverse trig integral. So keep yourself ready for that one. Ugh. Okay, so number 69. Okay, it's going to be a cool one. So that's going to be the integral sine inverse of x over the square root of 1 minus x squared dx. Okay, so whenever you have an inverse like trig thing, you almost always want to do a u sub. So I'm going to say let u equal to that. So let's set u equal to sine inverse of x, and then du. So you know to get like it's 1 over the square root of 1 minus x squared. So it's going to be 1 over square root of 1 minus x squared from first year, dx, can't forget that. And we see we have that right here. How cool is that? Almost like someone chose it. Okay, so we get the integral of u, and then basically this stuff gives you du. So it's just u du. So it's just a half u squared, and we know that u is equal to that, so it's basically just a half sine inverse of x squared plus c. Very cool. Hope you guys like that one. Very cool, eh? Even Justin said nice. Nice. 69, nice. Cool. Out of the 60s into the 70s. Great age. Let's erase this and then let's move on to 70. Also, shout out to Tristan. I just got a message. He donated 100 Rand, so I really appreciate it. Yeah, really appreciate it. It means a lot. Sick. Okay. So let's do question 70. Okay, so this one will be the integral of tan inverse of x dx. Okay, so again, as I said, often when you have inverse trig, you want to do u sub because they integrate really nicely. So let's let u tan inverse of x. The derivative of this, anyone in chat know? Nah, I got it. 1 over 1 plus x squared. Okay. I think actually what we should do is because we don't have anything to cancel this. So we'll still do this, but let's do by parts. So then let's let dv equals dx, and then v will be x. Okay, so let's do that because then it integrate. Yeah. Okay. So then our integral will be by parts. So it's u times v. So it's x times tan inverse of x minus the integral of v du. So Let's also have a dx. So it'll be x over 1 plus x squared dx. Okay, so we have this. So now we just need to do the integral of this. And we see that the derivative of the top would be 2x. Okay, so if we had a 2 here, we can multiply by half to just give us a 2. And now we have the derivative of that at the top, so now we can do our normal ln stuff. So basically our integral is going to be x times tan inverse of x minus a half, and we know this is going to give us ln of the absolute value of 1 plus x squared plus c. Very cool. That's number 70. Let's erase this and go 71. Yeah, 30 to go. Shout out, Layla. shout out. Thank you so much. Thanks for the support. Hope Sonia liked her shout out, by the way. Okay. 71. Let's go. Integral of x to the power of x over ln x dx. Okay, Layla, do you have any ideas of what we should do here? You can type in the chat if you have a suggestion. It's a tricky one. Okay, what I would say is it's hard to work when we have powers of x in the exponents, okay? So what I think we should do is maybe let's try switch this to like an e, okay? So we can write this as the integral. We can write x as e to the ln x, okay? And then we can write that to the power of x over ln x dx. And then we can see that the ln x's cancel out, which is really nice. So that's going to basically be the integral of e to the power of x dx, and the integral of e to the x is just e to the x. So yeah, r plus c, can't forget that. Awesome. Okay, good stuff. I see Reese in the chat. Yeah, I took a little 20-minute lunch break just to refuel. Okay, so that's number 71. Let's erase that and then go on to 72. Okay, let's see what number 72 is. Number 72. Okay, we're doing the integral of 1 over e to the x plus e to the negative x dx. So yeah, seems like a nice one. So also Reese, I hope you're doing well. I haven't seen you in a while, so I hope you're chilling, hope you're doing well. So what I'm going to do is I'm going to multiply this by e to the x over e to the x to get rid of this negative exponent. Okay? And then we also get like a nice derivative at the top, you'll see. So the top will become e to the x, the bottom will be e to the x squared. Okay? And then that times that will just be 1, because it like cancels out. Yeah, Brie Reese, you should have come earlier. You missed 6, 7, and 6, 9. You were a little bit late. Yeah. So what we can see now is that we can do a really nice u sub, right? Because we can basically let u equal to e to the x, and then du will be equal to e to the x dx, which is basically what we have at the top here. It's that. Okay. So then that's going to be equal to the integral of 1 over u squared plus 1 du, because of all of that stuff. And we've done this so many times, should be familiar. Integral of 1 over something squared plus 1 is going to be tan inverse of u. Then we just sub back in what u is, so it's tan inverse of e to the x plus c. Yeah, I'm doing good, thanks Reese. So yeah, that's our answer for 72. Good stuff. Let's erase it and go on to 73. Yeah, we're in the home straight now. Oh, my hands are looking crazy dusty and like all filled with Cokie. Okay, that was 72. Let's do 73. Okay, so 73, we're doing the integral of log base 2 of x dx. So this seems really tricky because we normally work with log base e or ln, okay? So we'd love to switch this into a ln, okay? So we can actually do that using our log laws. So we know we can change log base 2, we can change it into ln x over ln 2. Okay, so that's our log laws. If you have if it was base a of x, you can basically change it into ln a over ln x over ln a in general. Yeah. Okay, so now we know that this is just a constant. So it's basically just 1 over ln 2 of the integral of ln x dx. Okay. There's nothing really to cancel, so we can't do a u sub, so let's try it by parts, right? So let's let u equal to ln x, because it's nice to differentiate it, 1 over x, and then dv is going to be dx, so then v is going to be x. Okay, so our integral is going to be 1 over ln 2, u times v is going to be x ln x minus the integral of v du is going to be x times 1 over x, which is just 1, because they cancel out. So that's going to be 1 over ln 2. Let's actually times it in already, so it's going to be x times ln x over ln 2 minus the integral of 1 dx is going to be x, so x over ln 2 plus c. And if you want, we can, you see we did this, we can change it back into log base 2. So we can say it's going to be x, because x over ln 2 is log base 2, so x times log base 2 of x minus x over ln 2 plus c. Brilliant. And that is number 73. Cool. Let's do 74. So yeah, we're going back to some more trig integrals. So 74, we're doing the integral of 1 minus tan x over 1, I'd love to try 1 minus tan x, much easier integral, dx. Okay. Where should we start? So maybe instead of working with tans, let's try maybe expand them into sines and causes, okay? So let's say the integral of 1, we know that tan is sine x over cos x. So let's expand it at the top and the bottom. And then I want to I don't like fractions over fractions, so I'm going to multiply the top and the bottom by cos x. So I'm going to multiply by cos x over cos x. Okay? That's going to give us the integral of cos x minus sine x over cos x plus sine x dx. Okay. And what do we notice now? We notice that the derivative of this, the derivative of cos is negative sine, derivative of sine is cos. So we have the derivative at the top, right? So we can see, okay, you can just write it as ln of the bottom, but I'll do the u sub just to show you. So if we let u equal to cos x plus sine x, then du, derivative of that is going to be negative sine x, and the derivative of sine x is cos x. So we see we have like du with these parts, dx, sorry, dx. Yeah, du with those parts. So our integral basically becomes the integral of 1 over u du, which is ln of u, which I'll write here as ln of cos x, because that's what u is, cos x plus sine x plus c. Brilliant, brilliant, good stuff. Okay, number 75, let's go. number 75. Okay, we're going to be doing the integration of x squared times e to the x cubed dx. Okay, so a really nice one, because the derivative of x cubed is 3x squared, so we almost have that. So if we put a 3 here and a 1 over 3 here to cancel it out, then we have the derivative at the front. So then we can just say this is 1 over 3 e to the x cubed, not dx. It's the answer, plus c. Oh, one liner, what a treat. Okay, now we are 3/4 of the way through. Just a reminder, if anyone's watching, this is like a charity live stream, and I'm raising money for this charity called Chalk. You can click the link in my WhatsApp status if you join from there. And if you aren't following, if you don't like have my number on WhatsApp, or you're just like here, I can also post the link in Twitch chat, so you can just send a message if you want me to post it there. Yeah, hope you guys have enjoyed it, and I'm going to keep going with 76 now. And also, before I start, a massive thank you to everyone who has already donated. It means a lot. So yeah, thank you everyone. Okay, number 76. We are doing the integral of tan x times the natural log of cos x dx. Okay, so let's do a u substitution. Let's do a u sub, because I think it's going to work out nicely. So let's let u equals this whole thing. So u is going to be ln of cos x. Okay, so that means that du, the derivative of this, so we're going to have to use the chain rules. The derivative of ln of something is 1 over that. So it's going to be 1 over cos x, but we also need to do the integral of the inside. And the integral of cos x is negative sin x. Okay, so, and we can see that this, sin x over cos x, is just tan x, right? So we almost have the derivative at the front, we just need a negative. So I'm going to put a negative there to cancel out. So then we get that this is going to be, dx, yeah. There we go, now we have our du, okay? So it's going to be negative, the integral of u du. Brilliant, okay? So this is going to be negative, you add 1 to the power, divide by it, so it's a half u squared, yeah? And then we sub back in u, and we said that u was that, so it's basically minus a half ln cos x squared plus c. That's the final answer for number 76. Hey Taylor, thanks for the message. Glad you guys are all backing me. Thanks for the message, really appreciate it. Okay, let's do number 77. Okay. Your mom is so tired. Number 77. Let us do the integral of 1 over the cube root of x plus 1 dx. Okay, I think let's make the whole bottom equal to u, because then we're going to get hopefully a nice u sub. Okay, so let's let u equal to the cube root of x plus 1. Now let's solve for x. So if we move that across, it's going to be cube root of x, I'll do it slowly. Cube root of x is equal to u minus 1 cube root. So if we raise both sides to the power of 3, then x is equal to u minus 1 cubed. Okay, so now from here we can find that dx is equal to, chain rule, so it's going to be 3 times u minus 1, and the derivative of u is just 1, so it's just that, du. U squared, sorry. Cube squared, yeah. Okay. So now, we're going to get our integral is equal to 1 over u times 3 u minus 1 squared du. Okay, cool. So I'm going to take out the 3 and I'm going to expand the square. Okay, so it's going to be 3 times the integral of u squared minus, multiply those two together, minus u times 2, so minus 2u plus 1 over u du. And we can break this up into 3 times the integral of u minus 2, because the u's cancel, and then plus 1 over u du. Let's continue here. So that's going to be equal to 3. The integral of u is just a half, so a half u squared. The integral of minus 2 is minus 2u, so it'll be minus 6u. And the integral of that is ln of u, so it'll be plus 3 ln of u. Let's sub in back our u sub, so it's 3 over 2 times cube root of x plus 1 squared minus 6 cube root of x plus 1 plus 3 ln cube root of x plus 1. Just enough space for my plus c here. I remember in AP Maths, I used to forget my plus c's, and Mr. Dawes never happy, so yeah, remembering them now. Okay, that's number 77. Let's move on to 78. Okay, number 78. We are going to do the integral of e to the power of tan x over 1 minus sine squared x dx. So the immediate thing that jumps out to me is we know that the identity 1 minus sine squared x is equal to cos squared x. Okay. So basically what we have is we have the integral of e to the tan x over cos squared x dx. Okay, and then another thing that I see is that tan and sec are friends, and sec is 1 over cos, okay? So we have 1 over cos squared, so we can kind of write that as sec squared, okay? So we can write that as the integral of sec squared x times e to the power of tan x dx. That's going to be really nice, because now the derivative of tan is sec squared. So now we can just do it by looking, but we can also do a u sub, just to like really show all our steps. So if we say that u is tan x, then du is going to be sec squared x dx. Okay. So we have that. So it's basically just going to be the integral of u du, and that is a half u squared. And we can sub in u squared, so it's going to be a half. And u was tan x squared plus c. And I think that's our final answer. Is that right? Sorry, not u. It should be e to the u. Sorry, my bad. Let me just... Yeah, because you said u was tan x, so it should be e to the u, yeah. So it's going to be the integral of e to the u du, yeah. And now the integral of e to the u is e to the u. Still bring it up here if you want. And then we can say that's going to be e to the tan x plus c. Brilliant, brilliant. Okay, that is 78. Let us go on to 79. Yo, my whiteboard's getting good workouts. Okay, 79. Okay, we're going to do a piecewise function now. So we're doing integral from 0 to 5 of f of x dx. And f of x is defined piecewise, so it has like a few different parts. This one has 2. So it's basically equal to 10 if x is less than or equal to 2. And it's equal to 3x squared minus 2 if x is greater than 2. Okay, so that's what f of x is. So whenever you have something that's defined differently in different regions, you often want to split your integral up into where it's constant. Okay, so I'm going to do the integral from 0 to 2 of f of x dx. plus the integral from 2 to 5, because we want to go all of our bounds, of f of x dx. Okay, so from 0 to 2, that's when x is less than or equals to 2, so f of x is 10 in that bound, dx, integral from 2 to 5. F of x in this bound is 3x squared minus 2 dx. Okay, this one's easy. It's going to be 10x, evaluated from 0 to 2. This one's also easy. It's going to be x cubed divided by 3 times 3, so it's just going to become x cubed minus 2x, evaluated from 2 to 5. This is a 0, make that clear. Okay, so if we sub that in, 2 times 10 is 20, 10 times 0 is 0. So that's going to be 125 minus 10, which would be 115, minus, and then it's going to be 8 minus 4. Yeah, minus 4. Yo, my brain is fried. So that's 20, 135 minus 4 is 131. Final answer. Okay. Nice little piecewise function. Nothing too hard. Like, could have put harder functions in here, but I just want to show how to like split up a function. Okay. Let us have a look at number 80. Okay, final mixed bag question. So, we're going to be doing the integral from 0 to infinity of 1 over 1 plus x squared times 1 plus x to the power of 2022 dx. Okay, a little bit of a spicy one. And we're actually going to use a really interesting substitution here. So we're going to use the substitution, let's let u equal to 1 over x. And you might think this is crazy, but let's just have a look at how it will result. Okay, so if we solve for x, then x is going to be 1 over u. Okay, and then dx, what's the derivative of 1 over u? Negative 1 over u squared. Okay, so let's sub this in, right? So it's going to be the integral from 0 to infinity of 1 over 1 plus, so x squared will be 1 over u squared, 1 plus, and this will be 1 over u to the 2022. And then that'll be times, should be du, sorry. That'll be times negative 1 over u squared du. Okay. So let's see what we're going to do here. So maybe you can see this u squared is going to kind of cancel out. Let's cancel out with like this bracket. Okay. So it's going to be, and also check our bounds. Let's double check that. I don't even check it. So if x is at 0, then u, 1 over 0, or I guess 0, we'll call it 0 plus, whatever, is going to be infinity. And infinity, 1 over infinity is going to be 0. So our bounds actually swap. It was going from 0 to infinity. Now when you do 1 over x, it flips the bounds. Okay. I'm going to use this negative to actually flip the bounds back. Okay. Because when you multiply it by negative, the bounds always swap. Okay. So it's 0 to infinity, and then we're multiplying the u squared. So it's 1 over u squared plus 1 over 1 plus 1 over u to the 2022 du. Okay. And now I also don't like fractions over fractions at the bottom, so I'm going to multiply this by u to the 2022, but we can't multiply the top, we also have to multiply the bottom. Okay. Now we can multiply that in there, and it will give us the integral from 0 to infinity of 1 over u squared plus 1, times that in there, so it'll be plus, brackets, sorry, not plus, times u to the 2022 plus 1, and that'll be over, top will also be u to the 2022 du. Yeah. Okay. So I think we did something quite similar earlier, but we showed that two things are the same. So I'm going to call our original integral I, but then we know that that's also equal to this integral I. So both of the i's are the same. So what I'm going to do is I'm going to add these up. So I'm going to say that one plus that one. And we can add them up. Like, it seems a bit weird, but we actually can. So, and we also see that this u is just a dummy variable, so we can change it to x and it'll be exactly the same integral, because the thing that we have for integration is just like a dummy variable, so you can have u, x, y, whatever. So these are actually, the base is actually the same, so we can add them up quite easily. So when we add them up, we're going to get the integral from 0 to infinity of 1 plus, let's call this 1 plus x squared, because I'm going to change the u's to x's. Sorry, not x squared, x to the 2022, over x squared plus 1 times x to the 2022 plus 1 dx. And this is equal to, this is 2i. 2i is equal to that, so that's not equal to that, okay? But we notice something quite nice. We notice that that cancels with that. So then we get that I'm just going to divide a half on both sides. Is a half integral from 0 to infinity of 1 over x squared plus 1. Very cool. Okay. And we know what this is, right? We've done this so many times. This is just inverse tan. So this is just a half times tan inverse of x evaluated from 0 to infinity. Okay, I'm just going to move up from this one. So that's equal to a half. We know that tan inverse, it levels out at pi over 2, so that's going to be like your limit as x tends to infinity. And then tan inverse at 0, because the shape looks kind of like, this is going to be pi over 2, so at 0 it's just 0, so minus 0. The overall answer is just pi over 4. Cool. Very nice. Let's erase this and go on to, okay, now, cool. So now we finished this is our section. So we have 2 more sections left. Question 81 to 90. Those are all a bunch of like famous integrals, and some of them are really tricky. And then our final 10 are double integrals. So those are kind of like, yeah, it has 2 different variables and stuff. So we'll get to those. So let's rub this out and then we'll start with our new section. Oh, my hands are looking quite crusty. I don't know if you guys can see. Definitely going to have a good hand wash after this. Okay. So that is the end of that section. So now we're going to start with a new section. These are famous integrals. Oh, the first one is probably the longest one. It is the, let me write it and then I'll label it. So it's integral from negative infinity to infinity of e to the negative x squared dx. Famous integral in stats, because that's kind of like the form of the normal. It's called the Gaussian. Okay. So, big one. Okay. So, what I'm going to do, firstly, is we know that this is symmetrical. So we can say that it's just equal to 2 times the integral from 0 to infinity of e to the negative x squared dx. Okay. And what I'm going to do is I'm going to let this equal to I, okay? And since we know that the dummy variable doesn't matter, we can also say that that I is also going to be equal to e to the negative y squared dy. They're both equal because this one's just dy and it has a y variable, the dx has an x variable. Well, actually, let's just say, okay, wait, actually, I want to do a different order. So I want to first state that. And then what I want to do is I want to say, let's let I be equal to, so I'll multiply the 2 at the end, integral from 0 to infinity of e to the negative x squared dx, which is equal to the integral from 0 to infinity of e to the negative y squared dy. Okay, brilliant. So now what we're going to do is, what about I squared? So I'm going to multiply these two together. So we've done some where we add them. What about multiplying them? Okay, so we multiplied, we have the same base, so we can add the exponents. So I'm going to say that's going to be the integral from 0 to infinity, integral from 0 to infinity, because you're multiplying them, right? Multiply that by that, so it's going to be e to the negative x squared plus y squared, and then it's going to be dx dy. I hope that wasn't too fast. I'm basically just multiplying these two together, and when you multiply them, it becomes a double integral, and then e to the negative x squared times e to the negative y squared becomes that, and then dx dy. Okay. Oh, Hayden's asking how hard do I find these. Honestly, this one is a crazy one. Like, I would say this is probably one of the hardest ones that I'm going to be doing today. So I'd say this one is maybe I would say this one's like a 9 out of 10. This is like pretty much as hard as it gets. Because you have some crazy like substitutions and like even just thinking of this, like I mean, I didn't think of this, like there's someone else thought of this. But like, yeah, this is a crazy proof that I'm doing. Okay. But some of them are easy, some of them are hard. Okay. So now we're going to do something called polar coordinates. Okay. So I don't know if any of you remember polar coordinates from like second year, but we basically let x equal to r times cos of theta, and we're going to let y equal to r times sine of theta. Okay. And then let me just show it actually, because we know that. So let's say x squared plus y squared. We can see what's going to be. So it's going to be, if we square that, it's going to be r squared times cos squared. And then that's going to be r squared times sine squared. So I'm going to factor out the r squared. And it's going to be equal to cos squared theta plus sine squared theta. And we know that this is just equal to 1. So it's just equal to r squared. So x squared plus y squared is r squared. Okay. And since we're doing this like change of variable, we also need to find the Jacobian. Okay. So dx dy is basically, it's going to be, it's like a determinant of basically all the partial derivatives. So we used to do partial x, partial r, partial x, partial r, partial x, partial theta, so let's just do it. I'll write out the general form, so it's partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta. Okay. And that's then going to be in terms of dr, d theta. Okay. So let's see what it would be in our case. So if we do the derivative of x in terms of r, it's just going to give us, so basically, when you say partial derivative, you treat anything like, for example, this cos of theta, there's going to be a constant. So then this is just going to be cos of theta. Okay. Now we're doing the derivative of x in terms of theta. Okay. So that is going to give us, so the derivative of cos of theta is negative sine of theta. So it's going to give us negative r sine of theta. Okay. Now we're doing derivative of y in terms of r, which is just going to be sine of theta. Okay. And now we're doing the derivative of y in terms of theta, which will just be r cos of theta. dr d theta. Okay. So now let's find the determinant of this. So to find the determinant, all you have to do is you have to multiply that by that, and you multiply that by that, but it's like a negative, so you have to multiply by negative. Okay. Move back up. So dx dy is equal to, so it's going to be r times cos squared theta. So it's minus minus, so it becomes plus r times sine squared theta. Okay, and this will be dr d theta. So now what we can see is if we factor out an r, for this, we're going to get a cos squared theta plus sine squared theta, and that's just going to be 1. So basically, our Jacobian is just equal to r, dr d theta. Okay. Brilliant. Okay. So now what we can do is we can do our change. So we saw that x squared plus y squared is just r squared. Okay. So basically our I squared is going to be our double integral, but let's just check the bounds now. So I'll leave the bounds out for now and we'll do it. So it'll be e to the negative x squared plus y squared, which we said was r squared, right? negative r squared. And then we're going to times that by our dx dy we said was, because we have dx dy here, and we said that that's equal to r dr d theta. Okay, so let's think about the radius of orbits. Okay, so the radius of a circle, the smallest it can be is 0, and the biggest it can be is infinity. So the radius goes from 0 to infinity, and theta is our angle when we do polar coordinates. So the smallest an angle can be is 0, and then the biggest it can be, I think we only go up until, let me think. I think with polar coordinates we go up until pi over 2. Okay, hope that's right. That's 0 to infinity. It goes like 90 degrees, yeah. Okay, cool. So now we can actually evaluate this using like integration by part, basically. Not by parts, integration by u sub. So we now have an r at the bottom, which is awesome, because now we know that the derivative of the top is going to be negative 2r. So if we have a negative 2 here, I'm going to put a negative half here. Then we know that that is going to be the integral from 0 to pi over 2 of this, which will be negative a half, derivative of that, which is e to the negative r squared, because you have the derivative at the bottom, 0 to infinity, d theta, 0 to pi over 2, negative a half. So if we sub in infinity, we get 0, and if we sub in 0, we get 1. So it's times minus 1, so it just becomes plus. So it basically becomes the integral of a half d theta. Super easy. Half theta, evaluated from 0 to pi over 2. So it becomes pi over 4. Nice. That's r squared. Don't forget that. That's r squared. So we get r squared is equal to that. So therefore I is the square root of that. So it's going to be the square root of pi over 2. Okay, we're almost done. But remember that we said that r was this thing. And we said that our whole Gaussian integral was 2 times that. So therefore, let's write the big result at the bottom. Integral from negative infinity to infinity of e to the negative x squared dx is equal to that times 2 square root of pi. Okay, you guys can go crazy in the chat now, because that is a tough one. Hope you guys enjoyed it. Yeah, very cool. I think that's a really cool result. Let's even underline it in red, because it's such a cool one. Okay, very nice. Honestly, I just want to leave it on the board just to look at it for a little bit longer. It's such a cool one. Okay, I think that's enough. I'll erase this and we'll move. This is actually question 81. Not question 1. 81. Okay, we're gonna move on to question 82 now. Thanks, Taven. Thanks for the hype. Oh yes. Even Tristan said it's peak. Can I get away? Yeah. Thank you guys. Yeah, that was a tough one. Glad you guys enjoyed it. Luckily, I'm backing it up with, who knows, maybe it'll be easier or maybe it'll be tougher. So it looks really similar. E to the negative x squared dx. So the integral we just did was from negative infinity to infinity, okay? So now what we're trying to do is we try and do it, but now we don't have bounds, okay? So maybe what we should do is we should draw this graph, okay? So let's see what it looks like. I'll give you like a rough picture. It looks something like that, okay? And we're trying to find the integral of this without bounds. There's actually no closed form solution. So the answer to this, which I know is a bit of a cop-out, is basically, it's just square root of pi over 2 times ERF, which stands for the error function of x. So this is kind of like the definition of the error function. I'll write the definition here. So basically, the definition of the error function is basically 2 over square root of pi times the integral from 0 to x of e to the negative t squared dt. So this is basically just the definition of, yeah, very lame. I know, not so crazy, but I couldn't do it. Not everything can be as good as the as the gamma function. Okay, cool. I'm going to erase this one, then we go into 83. I think you guys will enjoy question 83. It's the zeta function integral. So yeah, that one's pretty crazy. Okay, question 83. And it is, I'll do it in purple. Now let me write it first. Okay. So it's basically the integral from 0 to infinity of x over e to the x minus 1 dx. And this is the zeta function. But by the way, integrals 81 to 90 are all like famous integrals. So yeah, zeta function. Yeah, so the zeta function integral. And the reason for that is basically this is the definition of zeta of 2. The zeta function evaluated at 2. Okay, so let's go through it. So there's one thing you need to know. I think it's the Basel identity. You need to know that the sum from n equals 1 to infinity of e to the negative nx is equal to 1 over e to the x minus 1. So you can see how that links because it's basically what we have at the bottom there. So basically what we have is we have x over e to the x minus 1. That's basically going to be the sum of x times e to the negative nx from n equals 1 e, yeah, to infinity. Okay, very cool, eh? So we're basically doing the integral from 0 to infinity. Instead of writing it like this, I'm going to write it using the sum. So it's the sum from n equals 1 to infinity of x e to the negative nx dx. And by the way, we can multiply the n in because our sum is in terms of n. So we can multiply x, which is a constant. Okay, so we can see that all these terms are going to be positive. So by the monotone convergence theorem, we can swap the integral and the sum. Okay. I know some of you guys are getting flashbacks to stats 3045, but yeah, we can actually swap the sum and the integral. Okay. So we can write that as the sum from n equals 1 to infinity, integral 0 to infinity of x e to the negative nx dx. Okay, very cool. And now what we can do is we can just evaluate this easily by integrating by parts. Okay, so let's let u equal to x. So the derivative of that's going to be dx. And then we let dv equal to the rest, which is basically e to the negative nx dx. So then v is the integral of that, so it's going to be 1 over n e to the negative nx. Actually, let's actually just do a u sub, I think. I think a u sub is going to be way easier. I think. Well, let me think. Yeah, I actually think you do this a different way. So let's just let u equal to nx, maybe this top thing. Okay. And the derivative of that in terms of x will just be n dx. Okay, so we're going to need okay. So now what we're going to get, basically for our integral, is we have the sum from n equals 1 to infinity of the integral from 0 to infinity of, we know that implies that x is equal to n over u. Yeah. So the integral of n over u, I guess it's just constant, so we can take it out, whatever. No, u over n, I did this wrong order. Yeah. U over n, this is going to be u over n, e to the negative u d, and dx is n, so times n dx. Okay, that's quite nice because now this n and this n cancel. So now we just have the integral from 0 to infinity of u e to the negative u. Okay, I don't know if any of you guys were here earlier, but we did the gamma function. And we said that gamma of alpha is the integral from 0 to infinity of x to the alpha minus 1 times e to the negative x dx. And you can see it kind of looks like this. So we can write this as u to the power of like 2 minus 1. Okay? Yeah, 2 minus 1. Okay? So now this is basically the definition of the gamma function of 2. This is the definition of the gamma function of 2. Okay. So the way we can write this is, well, where do I go from here? So we got the integral now. So basically doing the sum of the gamma function of 2. Okay. And we can easily evaluate the gamma function of 2, because the gamma function of 2 is equal to 1 times the gamma function of 1, and that's just equal to 1. So this is just equal to 1. Wait, I feel like I messed up something. Oh yeah, it's because I messed up this thing, so then this should have been 1 over n. du is 1 over... No, this is n. Yes, I messed it up, because this should be 1 over... Yeah. This should be n. And then dx is 1 over n du. So we want to flip this to du, and it's 1 over u. Yeah. Okay. So now we can take the u's out, and then we still have the gamma thing. So then it's going to be the sum from n equals 1 to infinity of 1 over n squared. Brilliant. Okay. And you can just know that this is like Euler's Basel problem, I think. So let's just write Euler's Basel problem. I think it basically is the sum from n equals, it's like bigger than this, but it basically gives you this result, or it gives you one of these results, and it's equal to pi squared over 6. So then this thing is just going to be equal to pi squared over 6. Another very cool one. Hope you guys enjoyed. Yeah, get in there. Thanks, Olive Oil. Don't know who you are in real life, but I'm sure I know you. Cool. So that's your final answer for 83. Let us erase this. I think it's quite a cool one. It uses like a bunch of different cool things. Let's erase this, and now I'm going to prove some cool things about the gamma distribution, or the gamma function. You can see how many integrals I've done. Look at my erasing cloth. It looks crazy. Okay. Thanks, Tristan. Glad you enjoyed that one. Okay, we're now doing question 84. So, this is the gamma function. We've been talking about it. The definition of the gamma function is equal to the integral from 0 to infinity of x to the alpha minus 1 times e to the negative x dx. So I'm going to prove a few things. So the first thing I'm going to prove is I'm going to prove that gamma of alpha plus 1 is equal to alpha gamma of alpha. Okay. So let's start with gamma of alpha plus 1. So gamma of alpha plus 1 is equal to the integral from 0 to infinity of x to the alpha, right? Because it's alpha plus 1 minus 1, e to the negative x dx. Okay. What I'm going to do now is I'm going to do integration by parts, okay? So I'm going to say, let's let u be equal to x to the alpha. So then the derivative of that is going to be bring down, so it's going to be alpha times x to the alpha minus 1 dx. And then dv is going to be what's left, so it's going to be e to the negative x dx. So then v is just going to be negative e to the negative x, because the integral of that. Yeah. Okay, so let's work out what this is going to be. So it's going to be u times v, so it's going to be negative x to the alpha e to the negative x minus v du, but it's already a minus, so I'm just going to make it a plus integral of, how do I write this? I'll just write it, times alpha x to the alpha minus 1 dx. Okay. Let's, oh yeah, and it's from 0 to infinity. And then this is all that we can sub in, 0 to infinity. Okay, so if we sub in infinity into this, it's going to be let's actually think, because it's, so this is growing to infinity, this is, okay, but I'm pretty sure exponentials grow faster than, so, okay, I'll write my argument. So my argument for that one is as x tends to infinity, I'm going to say that negative x to the alpha over e to the x tends to 0, because basically the e to the x, I think, yeah. The e to the x grows faster than the x to the alpha. So basically it outgrows it, so that means it tends to 0. Okay? The exponent basically, yeah, the exponent wins. Okay? So that's going to become 0, and if we sub in 0, it's also going to become 0. Okay? So this whole thing is basically equal to 0. So now we only really need to worry about this. So we can take out alpha, and we can say that that thing is equal to alpha times the integral from 0 to infinity of x to the alpha minus 1 e to the negative x dx. And now what does this look like? It looks exactly like the definition of the gamma, right, that we wrote here. So this is just equal to gamma of alpha. And then we've just proved what we wanted to. We showed that gamma of alpha plus 1 is equal to alpha times gamma of alpha. Let's write that out actually. So therefore that proves that gamma of alpha plus 1 is equal to alpha gamma of alpha. Okay. That's actually, that's just the first part of this question. So I actually wanted to prove 3 things with the gamma. So I wanted to show this. Okay, let me erase this and I'm going to show my next thing. Okay, the second thing I'm going to show for question 84 is second thing I want to show is that gamma of alpha is equal to alpha minus 1 factorial. Okay, so we just showed, I'll just put what we just proved here. We showed that gamma of alpha plus 1 is equal to alpha gamma of alpha. Okay, so we can use this to show this. So let's start with gamma of 1, right? Okay, gamma of 1, if we sub it in, it's the integral from 0 to infinity of, so x is 1, sorry, alpha is 1, yes. So it's x to the 0, which is just 1, so it'll be e to the negative x dx. We know how to do this, we've done plenty. Put a negative here, negative here. So that's going to be negative e to the negative x from 0 to infinity. So it's going to be negative, if you sub in infinity, it's going to be 0, minus 1 when you sub in 0, so it's going to be 1. Okay, gamma of 1 is 1, we've just shown that. What about gamma of 2? We don't have to re-integral, we don't need to do the integral, we can just say it's going to be 1 times gamma of 1, using what we showed in part 1. That's going to be 1 times 1, which is 1. What about gamma of 3? You can just say that's going to be 2 times gamma of 2. Gamma of 2 is 1, so that's just 2. Gamma of 4 is going to be 3 times gamma of 3. We show that gamma of 3 is that, so it's 3 times 2, which is 6. Okay, and you can see how this is going. We're basically just showing that it's like, therefore, gamma, it's just basically factorials, because this is basically just 3 factorial. And this is basically just 2 factorial. So gamma of alpha is equal to alpha minus 1 factorial, because you see, gamma of 4 is 3 factorial. Very nice one. Okay, that's the second thing. And then the final thing is I just want to find what gamma of a half is, because it gives a really cool result. So let's erase this, and then I'll show that. Okay, so the second thing I showed was that gamma of alpha is equal to alpha minus 1 factorial. The final thing I want to show for question 84 is I want to find gamma of a half. Okay, so mean the integral from 0 to infinity of x to the power of a half minus 1, which is negative a half, right? E to the negative x. Okay. I want to do a u sub. So what do you think we should do for a u sub? So let's do, maybe u is like the square root of x. Okay. Because this is like 1 over the square root of x. That means that if we square both sides, x is going to be u squared. That means that dx is going to be 2u du. Okay. I think that's all we're going to need for this one. So then we can just say that's going to be equal to the integral from 0 to infinity of 1 over u times e to the negative, and we know that x is u squared, times dx, I should put a dx here, which will be 2u du. That u and that u cancel, which is awesome. And we can take the 2 out, so we just get 2 times the integral from 0 to infinity of e to the negative u squared du. And we just did that we just did the Gaussian, right, which was really crazy. And we showed that this thing, when we did the Gaussian, was equal to pi over 2. So like square root of pi over 2, yeah, that's when we did the Gaussian. So now it's 2 times the square root of pi over 2, so the 2's cancel, it just gives you the square root of pi. So how crazy is that? The gamma function of a half is the square root of pi. And we know that so can you say that maybe gamma of like a half, which is equal to a half minus 1 factorial, which is equal to negative a half factorial. Can you say that's equal to square root of pi? Can you do factorials of negative fractions? Like, we don't even know if we can do factorials of fractions, never mind negative fractions. So yeah, that's quite a cool little thing you can see. Yeah, kind of shows that, like, yeah, gamma function links a lot to like factorials when you try expand it into non-integers. Okay, so I know that was a long one, 84. Let's swiftly move on to 85. Thank you, Nathan, absolute legend. Thanks for the message. Let's go on to question 85. Okay, so we're going to be doing integral from 0 to infinity of sine x over x, and this is called Dirichlet integral. Okay. And Kieran actually sponsored this, so I'm going to say by Kieran. Absolute legend. Kieran. Okay. Awesome. One of my friends from first year res. Cool. So for this one, we're actually going to use, so there's a few ways to do this. There's actually quite a few ways. Gamma function supremacy, hell yeah. So for this one, what I'm going to use is the Feynman's technique. Okay, so what I'm going to do is I'm going to do something a little bit weird. So I'm going to basically say, let's find I of b. Okay, I know that this isn't going to be our integral, but it might help us. Okay, so basically it's going to be integral from 0 to infinity of sine x over x, and I'm going to times this by e to the negative bx dx. Okay, this is kind of similar to a Laplace transform, but don't worry about that. We'll get to that. But yeah, I'm multiplying by something else. So I'm not saying it's the same, I'm just saying it's something else. Okay. So we see that this is equal to, so I'm going to say integral from 0 to infinity of sine x over x, supposed to be dx, is equal to, so if x was 0, then they would be the same, right? Because then this would just be 1. So I'm going to say it's equal to I of 0. So you see, it kind of links. So maybe what we should do is we should find the derivative of this in terms of b. So that's normally how you use Feynman's technique. So I'm going to find partial b of I of b. Okay. So how do you do the derivative of this? We're going to do the derivative of this integral, and we can use Leibniz's rule to actually swap it. So we can do the integral of the derivative. Okay. So that's the integral from 0 to infinity of the derivative of this in terms of b. So this is all just constants if we talk in terms of b. And then the derivative of this is going to be negative b, right? Negative b, right? Blanking out, just so we're doing the derivative in terms of b. B is so it's going to be negative x. So it'll be e to the negative bx, and the derivative will be negative x. Yeah. dx. Exactly. And we see why this is so nice, because that cancels with that. How cool is that? Okay, very cool. So now I'm going to take out the negative. So now we get its negative integral from 0 to infinity of sine x times e to the negative bx dx. That's our derivative. Okay. And then we did a really similar question earlier, right? So I'm not going to redo all the steps. We did a really similar question, but we remember that this result was negative. I can't remember when we did it much earlier in the day though. And it was negative e to the negative bx times cos of x plus b sine x. Okay, divided by b squared plus 1 from 0 to infinity. So we did something really earlier, really similar earlier in the day. Okay. So now we can sub in our bounds. Let's think. IB, so we got the derivative. What would we do here? Well, we sub in 0 for x. Sub in 0. Or we can say that that's the negative and the negative will cancel. Oh, yeah, we did this exact question earlier, I remember. We got basically 1 over b squared plus 1. Yeah, that's what we did earlier. Yeah. You can go back in the VOD and check if you want to check where we did that. Okay, so that's going to be, let's just remember, that's I dash of b. Okay, but we don't want I dash of b. Yeah, it's negative actually. We want the integral of this. So let's do the integral of both sides, db. Integral of that, db. Okay, so this is where the magic happens. So the integral of this, what we'll do is we can see that this is in the form of like the inverse tan, right? So then IB, because we did the integral of the derivative, so it cancels it out, is basically tan inverse of so negative, yeah, b plus c. Okay, brilliant. Okay, but now we need to find what the c is, right? So to find what the c is, we can let the b tend to infinity. Okay, so as b tends to infinity, this thing will tend to pi over 2, and as b tends to infinity here, this thing will tend to 0. So we basically get negative pi over 2 plus c equals 0. So we basically get that c is equal to pi over 2. Yeah. Okay. So now we get our final function, I of b, is equal to negative tan inverse of b plus pi over 2. And we said that right at the start, I don't know if you remember, but we said that this function is equal to our actual integral if b is 0. So let's find I of 0, right? So we know that tan inverse of 0 is just going to give us 0. So it's just going to be pi over 2. Very cool. So now, that's our final answer. Our integral from 0 to infinity of sine x over x is just equal to pi over 2. What a crazy, yeah. So that's Feynman's technique. You kind of introduce something unnecessary, or something extra to help you, and then you do the derivative of it, and then you integrate it out, and then you find, yeah, you find everything we've done. Cool. Hope you guys enjoyed that one. That one was a tricky one. That's question 85. Let's go on to question 86. Oh, 8.5, 6.5 hours. So I think it'll probably take me 7.5 to finish. We'll see. Question 86. We have the integral from 0 to pi over 2 of sine n of x dx. Okay. And I don't know if you remember, but earlier in the day, we actually did a very similar question to this, and we got a nice recurrence-like formula, okay? So when we did it earlier, we got, what did we get? Should we just do it again? I can't actually remember what we got. Okay, let's just do it again. So let's split this up into two parts, okay? So I'm going to split this up into the integral from 0 to pi over 2 of sine squared x times, that's exactly how we did it, it's like earlier in the day, minus 2x dx. And then we're basically going to change our sine squared x, change this into a 1 minus cos squared x. So this will be equal to integral from 0 to pi over 2 of sine n minus 2 of x dx minus the integral of cos squared x sine n minus 2 x. Okay. Dx. Yeah. 0 pi over 2. Okay. Cool. So what we can do now is we can change cos squared. We can change this into 1 minus sine. Right. Yeah. Yeah. Change this into 1 minus sine squared x. Okay. So then we basically get integral from 0 to pi over 2 of sine n minus 2x dx minus, so 1 times that will be the integral from 0 to pi over 2 of sine n minus 2x dx minus minus will become plus 0 pi over 2 of, so if you multiply them together, it just becomes sine of n x dx, which is exactly what we started with. Okay. Sine. I'm losing my mind a little bit. I feel like I've made a mistake somewhere. Let me just see. 1 minus cos squared x sine n minus 2 becomes that times that. Then cos squared x becomes 1 minus sin squared. I think I've got a bit lost in the weeds here. We'll come back to this one. Let's move on to question 87. Sorry, we'll come back to that at the end. That one was, I don't know, I got a bit lost in the weeds there. Let's go on to question 87. So, question 87 is the integral from 0 to infinity of sine of bx times e to the negative ax dx. Okay, and this kind of links to the Laplace transform. Okay, cool. So, what is the Laplace transform? So, basically, the definition of the Laplace transform, I've got it here. Basically, what it says is you get like Laplace transform of some function f of t, and that's going to be equal to, I'm running out of space, it's going to be equal to the integral from 0 to infinity of f of t times e to the negative s of t dt. So you can see how this kind of links. This is the Laplace transform of sine of b of x. Okay, you can see how it links. Okay, so the first thing you need to know for this one is we can split sine of theta into e to the I theta minus e to the negative I theta over 2i. So you can split up into imaginary numbers. Okay, so I'm going to do exactly that. So we can obviously take out our 1 over 2i because it's just a constant. Don't, we won't end up with imaginary numbers in our solution, they'll probably cancel out somehow. And then I'm going to multiply these by that. So it's going to be e to the power of negative. Let's do that one by that one. So it'll be ax plus I theta, right? Sorry, let's actually, we actually have, this is in general, but we have theta is equal to bx. So this should be, so it should be negative ax plus bx. Yeah, plus bx, okay? Plus ibx, plus bxi, okay? And then it'll be plus, because you have, or minus, I guess, e to the power of negative ax minus bix. Okay, cool. Dx. Perfect. So now what I'm going to do, 1 over 2i, integral from 0 to infinity, is I'm going to group these in a certain way. So I'm going to write it as e to the, I'm going to take out a negative, and I'm going to write it as a plus b, let's say a, actually take out a negative, so it'll be a minus ib, x minus e to the negative a plus ib x. Okay, dx. Cool. So now we can see quite clearly, we can just do the derivative and we can do like 1 over it. So it's going to become 1 over 2i. The integral of this is going to be, let's just do a big square bracket, it's going to be 1 over negative a minus ib times e to the negative a minus ib minus 1 over, okay, negative, I'm just going to write it as a plus, okay, a plus ib e to the negative a, what should be, ibx, sorry, a plus ib x, we're doing this from 0 to infinity. Okay, so let's see what we get. 1 over 2i. Okay, so if we sub in infinity, that gives us e to the negative infinity, so that gives us 0. And if we sub in infinity here, we also get 0. Okay? If we sub in 0 here, then we get e to the 0. So it basically just becomes this thing. So it becomes minus 1 over a minus ib. And if we sub in 0 here, we just basically get this. So it becomes plus 1 over a plus ib. Brilliant. Okay. And now let's try to get a common base. So it's going to be 1 over 2i. We want our common base to be a minus ib, a plus ib. This is already like a difference of 2 squares. The top is going to be a. This is going to be a plus ib. And then it's going to be minus a minus ib, yeah. And then we want this one to be that one. So it's going to be plus a plus a plus, okay, so it's going to be, sorry, I messed up the signs. So it's a plus ib. And the other one, so then it'll be minus, yeah. So that's for that one. And then it'll be minus a minus ib. Yeah, a bit messy here. So the a's will cancel. And then at the top we're going to get ib plus ib. So we're going to get 2ib. So, okay, let me actually write it out. It's a bit hard to picture maybe. So it's 2ib over a, so let's actually multiply it out because the difference of 2 squares, it's going to be that squared, which is a squared. And then that squared is going to be minus, but then it'll be I squared, so it'll be plus b squared. And that's all times 1 over 2i. Ah, brilliant. Our i's cancel. And then we get as our final answer, b over a squared plus b squared. What a long integral. Yeah, not an easy one, but we got it in the end. Okay, and that is our Laplace transform like kind of integral. Okay, brilliant. Let's get on to the next one. Okay, question 89. Okay, we're going to do the integral from 0 to infinity of sine of x squared dx. Okay, and this is called Fresnel integrals. Okay, Fresnel integrals. Cool. Whew, final push. Okay. So, I think, let me think. What are we going to do here? So, let's do it maybe in general let's do it in general, and then we can just sub in 2, okay? So let's call it I is equal to the integral from 0 to infinity of sine of x to the power of n dx. Okay, so we're going to do it in general. So let's do a u sub. So let's let u equal to x to the n, okay? U sub. So then du will be equal to, the root of that will be x to the n times x to the n minus 1. Cool, dx. Yo, my brain is fried. And if we want to solve for x, then we can say that x is equal to u to the 1 over n. Okay. Okay, so where would we go from here? So let us sub in this u for this x, okay? So then this is going to be equal to n, and instead of x, I'm going to write u to the 1 over n to the power of n minus 1 dx. Okay, we can multiply that in, so that's going to be n times u to the power of 1 minus 1 over n dx. Okay. Yeah, we don't need the brackets here because it's a power, yeah. 1 minus 1 over n. Okay, cool. So that's d. Wait, what was that doing? Okay, so that's du. So if we want to find dx, then what we can do is we can just like flip it. So it's going to be 1 over n times u to the 1 over n minus 1, right? Because you're raising both to -1 du. Okay, so let's see what we have now. So we have basically our integral here is equal to the integral from 0 to infinity of dx is 1 over n, so I'm going to take that out. 1 over n times sine of x to the n, which is u, so sine of u, times dx, which is u to the 1 over n minus 1 du. Okay, that's where we're at now. So what we need to do now is we need to know that e to the ix is equal to cos of x plus I times sine of x. Okay, so we're going to use some more imaginary numbers. So basically sine of x is basically just the imaginary part of e to the ix. Because you can see this is the only imaginary thing, that's all real. Okay, so I'm going to say that our integral is equal to the imaginary part, so we have sine, of well, let's do our 1 over n as well outside. Integral from 0 to infinity of u to the 1 over n minus 1, and then we have that times e to the ix du. Oh, but instead of x, we want to use a u, so let's use iu, right? Because we have sine of u, yeah. Okay. So we can make this into a slightly different form. So we can say that's 1 over n, the imaginary part of the integral from 0 to infinity of u to the 1 over n minus 1. And I'm going to change this. Instead of writing it like that, I'm going to write it as negative 1 over I times u, and you'll see why. Du, imaginary part of that. Yeah. Okay. So let's think about our gamma function, right? We used the gamma last, we're going to use it again. So the definition of gamma of alpha is the integral from 0 to infinity of x to the alpha minus 1 times e to the negative x dx. And you see that's really similar to what we have, right? It looks kind of like we're on the right track, okay? But we just need to do a quick use. So the substitution I'm going to do here, let's use t. So I'm going to let t equal to 1 over I times n. So then dt is just 1 over I. dt. Yeah. Wait. 1 over I times u. So then that's going to be du. So that means that du is equal to I times dt. Okay. Good stuff. Like I'm losing my mind a little bit with these questions. So, we're trying to find, okay, I'm going to erase, and I'm just going to write what we're trying to find, because I don't have enough space to write what I need to write. Okay, so I'm just going to erase some stuff. We'll remember what we've said, though. Okay, so we're trying to find the, so we were on the integral from 0 to infinity of u to the 1 over n minus 1, e to the minus 1 over I u du. That's where we were. And then we did that t substitution, right? So after that t substitution, we said that u was equal to it, okay? That's going to be the integral from 0 to infinity of it to the power of 1 over n minus 1. And then e, we said that that was t, right? And then it was dt. Okay. So what I'm going to do is I'm going to take the n. I'm going to take that out, so it's going to become I to the 1 over n, integral from 0 to infinity, of t to the 1 over n minus 1, e to the t, dt. And now we can see this is gamma of 1 over n, right? I wrote it earlier. So this is gamma of 1 over n. So, our overall integral, let's just recap, it was 1 over n times the imaginary part of this, which is I to 1 over n gamma of 1 over n. Okay. And this is real, so we can kind of take that out, and it's basically equal to 1 over n, the imaginary, 1 over n. Let's put gamma of 1 over n at the top, imaginary part of I to the 1 over n. Okay. Cool. So let's do another sort of thing. Let's let theta be equal to pi over 2. Okay, might seem crazy, right? But then, because we know that e to the I theta, we kind of used the substitution earlier in this question, is cos of theta plus I times sine of theta. Okay? So if we do that substitution, then it's e to the I pi over 2. So then e to the I pi over 2 is just going to be I. Because that cos of pi over 2 is 0, and sine of pi over 2 is 1. So that should equal to I. Okay? So basically, what we're going to have is we're going to have gamma of 1 over n, and then sine. Instead of writing I, we're going to write it as e to the I e to the I pi over 2n. Okay? Okay. And, okay. And from here, we can, yeah, I'm getting a bit tired now, I can feel my brain shutting off. So we can basically say that this is just, because it's the imaginary part of this, sorry. Imaginary part of this. So it's basically equal to gamma of 1 over n times sine of e to the, sorry, sine of pi, yeah, we're using this again. So it's sine of pi over 2n. Okay, so that's the general thing. So we have it for 2. So for us, n is equal to 2. So it's going to be gamma of 1 over 2 times sine of pi over 4. Okay, we know that gamma of a half is root pi over 2. Sine of pi over 4, anyone know what that is? Pi over 4 is root 2 over 2. So basically what we have is square root of pi times root 2 over 4. And if we want to write this all as a square root, let's leave it like this. I think I'm happy with that. Okay. Brilliant, that's 89. Let's erase this and keep going. Okay, our final famous integral, number 90. The log sine integral. Okay, so this integral is integral from 0 to pi over 2 of the natural log of sine of x dx. Okay, so we're going to do the u substitution. I'm going to say let's let x equal to pi over 2 minus u. Okay, that means that dx is equal to negative du. Cool. So we're going to get negative integral from 0 to, hello?
James, 10 left.
Hey, 10
You
left.
got it.
Thank you.
You got it. Lovely.
Thanks, Tash. Okay, so let's just check our bounds. So we're going from 0, so pi over 2 minus 0, this will be pi over 2. And then pi over 2 minus pi over 2 will be 0. And then we can use the negatives to flip back, but yeah, let's just do that. And then it will be of ln of sine of, instead of x, we're going to do pi over 2 minus u times negative du. Okay, good. That's the integral from, so now I'm going to use this negative to flip it back. So I'll be the integral from 0 to pi over 2. And then we know that this changes to cos, right? That's like literally the definition of how you change from pi to cos, so it'll be cos of u du. Okay. So now let's actually, very similar to what we did before, we're going to add them together. Okay. So if we add them together, then we get, so I'm going to call this, let's call this I. Well, it's also going to be I because they're the same. So then we get that 2I is equal to the integral from 0 to pi over 2 of ln of sine, let's say x, plus ln of cos of x. So we've done this trick quite a bit, right, where we add the two different things. Okay, so we know we have lns, we adding, we can multiply them together. Okay, well, 7 hours, yeah, that's crazy. That is insane. 0 to pi over 2 ln of sine x times cos x dx. Okay, and we know that we can use the rule to change this into sine of 2x, but we had a 2 here, so we can just change this to sine of 2x over 2. Okay, that's equal to the integral from 0 to pi over 2 of ln of sine of 2x over 2 dx. Okay, good stuff. Now what we can do is, how can we simplify this? We can split this up into two different lns now. Yeah. So now we can split this up into the integral from 0 to pi over 2 of ln of sine of 2x. And remember, when we're dividing, we're going to have to minus, so this will be dx minus the integral from 0 to pi over 2 of ln of 2 dx. Okay, so let's evaluate this. We can't evaluate this one easily, but let's just leave it. Pi over 2 sine 2x dx. We can probably do it at some point. This is just going to be ln of x, so we're going to times it by pi over 2. This is just going to be minus pi over 2 ln of 2. Okay, it's pretty good. So now what we're going to do is, what would be even useful here? Let's think about this. Ln of sine of 2x. Ln of sine of 2x. Ln of sine of 2x. Is this maybe like an even or odd function, something like that? No. Also just remember this is 2i. Ah, this is what we started with. Ah, that's the trick. So this is I. This is I. I see that now. Ah, that's a beautiful trick. So we get 2i is equal to I minus pi over 2 ln of 2. So we can just move that across, and our I, which is our original integral, is equal to negative pi over 2 ln of 2. Oof. Glad I saw that one. Awesome. How cool is that? And that is the end of our famous integrals. I'm going to rub this off, and we have 10 left. Ugh. Okay, the last 10, I didn't give myself an easy end. The last 10 are double integrals. So let's get cracking. So number 1, the integral from 0 to 1 over root 3, integral from tan inverse of x to pi over 6 of sec to the power of 5 of y dy dx. Okay, so this looks like a prime candidate for something that we should swap the order, because if this was a dx first, then we could easily evaluate this because this doesn't have any x's in. So let's sketch it out, and then let's see how we can swap the order. So I'm going to draw it here. So let's draw what tan inverse of x looks like. I'll do it in purple. Tan inverse of x, it looks something like, it goes like there and then it goes there. Okay. So this is y is equal to tan inverse of x. Okay. And we're going from that, so from y equals, because it's dy, so it's going from that up until pi over 6. Okay. So let's draw this line. I'm going to say this is at pi over 6. And then x goes from 0 to 1 over root 3. And if you sub in 1 over root 3, you'll actually get pi over 6. So it meets nicely there. So we're trying to find this area. Okay. So now what I want to do is I want to swap the order. So I'm going to write that, I'll put in the bounds. So I'm going to write sec to the power of 5 of y. I want to write dx dy. Okay. So let's think, what does x go from? So we need to find basically this in terms of x. So that's easy, right? We can write this as x is equal to tan of y. Okay. So if you were doing the x's would go from 0 to tan of x. Do you agree? Because you would go from like 0 to tan of x. Okay. So you go from 0 to tan of x. And then your y's go from 0 to pi over 6. 0 pi over 6. And now I've successfully swapped the order, so now it's really easy, right? 0 to pi over 2. This is now in terms of x, so this is all a constant. So this will be 6 to the power 5 y times x dy. Integral from 0 pi over 2, pi over 6. Should be over 6. 6, okay. This is from, 0 to tan of x. Okay, so if we sub in tan of x, it's just going to be 6 to the power 5 y. Sorry, tan of y, yeah. Tan of y times tan of y dy. Okay. And now what we can do is we can do a u sub. I'm going to be doing more integrals tonight. So now we can let u equal to sec y. If u is sec y, then du is going to be sec y times tan of y dy. So we can kind of use one of the secs here to make our du. So we'll have the integral of 0 to pi over 6. Don't worry about the bounds. I'll sub it back in terms of y. So yeah, of u to the power of 4. Because remember we use one of the secs for that. Du. Okay. So that's going to be 1 over 5 u to the power of 5. Okay, we said that u was, so that's going to be 1 over 5 u to the power of 5 evaluated from 0. No, let's sub it in. Where's my clock? So we said that u is sec y, so it'll be sec power 5 of y evaluated from 0 to pi over 6. Okay, and we can say that's 1 over 5. So sec of pi over 6, we can just use our calculator to work that out. So that's going to be 2 over root 3. So 2 over root 3 to the power of 5. And then sec of 0 is going to be 1. So it's going to be minus 1. 1 over 5 times 1. Yeah, to the power of 5, I guess. So if we had to multiply all this out, it'll be 32 over, so root 3, so it'll be 3, 9, 45, root 3 minus 1. Minus 1 over 5, sorry. I'll just leave it like that. I think that's good enough for me. Okay, that's our first double integral. Not bad. Let's get on to the next one. Okay, question 92. We have the integral from 0 to 1, integral from y to 1 of 1 over 1 plus x to the power of 4 dx dy. Okay, it's another case where we'd love to swap the order, right? Because if there's no y's here, so if we can get in terms of y, it'll be really easy. So let's sketch it out. Okay, so our x's go from y. Let me draw this line. This is our x equals y line, up until 1. So basically, up until this point, this is basically 1. And then our y's go from 0 to 1. Okay, so basically we are integrating that area there. Okay, we want to swap the order. So let's say that this is equal to, I'll leave out the bounds for now, x to the 4 d, we want to make dy dx. Okay, let's think about our y's now. So now our y's go from 0 to this point, right? And this point is x. So our y's go from 0 to x. Okay, and then our x's go from 0 to 1. Cool. We can do this integral. So the integral of this, because in terms of y, it'll just be that times y. And we sub in x, it'll just be that. So it'll be integral of 1 over x. And there'll be x over 1 plus x to the 4. Because when you sub in 0, it'll just be 0. dx. Okay. We can write this in a certain way. So we can write x to the 4 as x squared squared. Okay. Because I'm trying to kind of get into the arctan, like, yeah. So now let's do our u sub. So let's let u equal, let me write in green for my u sub. So let's let u equals x squared. Okay. And that means that du is going to be 2x dx. Okay. Yeah. Okay. So what we're going to get is we're going to get, so we need a 2x to get our du. So if that was a 2, then we can do a half here. Yeah. Okay. So it's going to be a half integral, let's just check our bounds from 0, yeah, still to 1, of 1 over 1 plus u squared du. So our old friend arctan, so it's a half tan inverse of u from 0 to 1. Okay. So it's going to be a half. We know that tan inverse of 1 is going to be pi over 4. Pi over 4. And then tan inverse of 0 is just 0. So that's our final answer. Pi over 8. Brilliant. That is question 92. Let's erase this and go on to 93. Oh, taking even longer than 2 oceans is going to take me in a few days, in a few weeks, I guess. Okay, 7 hours and 15 minutes. 93. Double integral. Integral from 0 to 1. Integral from pi y to pi of sine x over x dx dy. Okay. This is going to be really tricky if we do it in terms of x. So again, we're going to swap the order. Okay. So let's draw it out. So we're going from pi y. So it'll be a straight line. So that'll be x is equal to pi y. We could write it as y is equal to 1 over pi x. That's why it's a straight line. So x goes from basically that, up until pi. So let's draw it goes up until, let's say this is at pi. Okay, and then y goes from 0. Y goes from like 0 up until 1. And if you think about it, this is like 1. So if y equals 1, then x equals pi. So it's going to be exactly it when you draw it nicely. Exactly it like that, right there. Okay. So what's the area we're trying to find? We're trying to find that area there. Okay. So let's swap the order. So we're doing integral of sine x over x dy dx. Okay. So before now we're going to think, what does y go from? So in terms of y goes from 0 to 1 over, I'll call it 1 over pi x, or we can just call it x over pi. So it goes from 0 to x over pi. And then our x's, they just go from 0 to pi. Brilliant. Okay. So now this is going to be integral from 0 to pi of sine x over x y, if I went from 0 to x over pi dx, integral from 0 to pi. If we sub in x over pi for y, then the x's are going to cancel, so it's just going to become 1 over pi sine x dx. Okay. The integral of sine is negative cos. I hope I know that by now. So it's 1 over pi negative cos of x from 0 to pi, which is equal to 1 over pi. We know that cos of pi is negative 1, so negative 1 is 1. Cos of 0 is 1, so minus 1, but minus 1 is plus 1. So our answer is 2 over pi for that area there. Brilliant. Let me rub that off when we go to question 94. Okay. Question 94. Let's get a sip of water. Let's get a sip of water first. It is integral from 0 to square root of pi. Integral from 0 to pi of y times sine of x plus y squared dx dy. Okay, it doesn't seem like there's any real advantage to changing the order. In fact, I think it's probably a disadvantage, because then we want this to be like a constant. So we can just do the derivative, the integral of this straight away. Okay, so it's going to be from 0 square root of pi. So this is just a constant, so it becomes y. So the derivative of, integral of sine is negative cosine of x plus y squared dy. And do we have to do anything with this x? No, because it'll just become 1. Right? Yeah, using the chain rule, it just becomes 1. Yeah. And we evaluate this from 0 to pi. Okay. So 0 square root of pi. Let's see what this value. 0 to no. Yeah. So we're subbing in pi for y. Subbing pi for x. Yeah. So it becomes y, negative y, times cosine of pi plus y squared minus minus, so it becomes plus y times cosine of y squared dy. Okay. We know that this is going to become negative cosine of y squared. So then we cancel out with that. And you see now they're actually the same. So now we get integral from 0 to the square root of pi of 2 times cosine of y squared dy. Okay? We're going to do a u sub. So we're going to do this by u sub. So we're going to say, let's let u equal to y squared, so then du is equal to, so it's 2y, yeah. So then du is going to be 2y dy, and we see we have a 2y dy here. So then it's just basically going to be the integral from 0, let's just double check our bounds, so 0, and then square root of pi squared just goes to pi now, of sine, of cos of u du. Brilliant. Let's move that up here. Equal to the integral of cos is sine, so sine of u from 0 to pi. So we know that sine of pi is going to be 0. Sine of pi minus sine of pi. Sine of pi minus sine of 0, so it's just 0. So the whole thing is just 0. And that's our answer. Brilliant. Okay, let's rub this out and do question 95. Question 95. We have integral from 0 to 1, integral from tan inverse of x to pi over 4 of cos of y dy dx. Okay, so if we really wanted, we could switch the order, but it's not too hard to integrate cos of y, so I think let's just do it like this. So we have the integral from 0 to 1, or integral of cos of y is sine of y, evaluated from tan inverse of x to pi over 4 dx. Okay? We have the integral from 0 to 1. Sine of pi over 4 is 1 over root 2 minus sine of tan inverse of x dx. Good. What should you do here? Well, we can so we can maybe use a right triangle to figure out what this thing is. So let's make this a 90-degree angle. And then let's let this equal to theta. Okay? Because if we know that tan inverse of x implies that basically tan of theta is equal to x, right? That means that that's x and that's 1, and this is the square root of x squared plus 1. So then sine of that is just going to be opposite over that. That's just going to be the integral from 0 to 1 of 1 over root 2 minus that over that. So x over square root of x squared plus 1 dx. That helps us, because now we can do a u sub. We can let the whole bottom equal to u, right? So let's let u equal to x squared plus 1. So that means that du will be equal to 2x dx. So if we have a 2 here, it'll be good. Let's put a half outside. Okay. So let's evaluate this thing. This thing's easy. So it's just evaluates from 0 to 1, so it just becomes 1 over root 2 minus a half the integral of 1 over, I'll just write it as u, the negative a half du, right? And then we need to check the bounds. So the bounds were 1 to 2, but now we're saying 0 squared plus 1 is 1, and then that's going to be to 2 because it's 1 squared plus 1. Yeah. Okay. So we get 1 over square root of 2 minus a half times, that's going to be, we add 1 to the exponents, so it's u to the half, and we divide by half, so it's going to be 2 times that. So it's going to be 1 over square root of 2 minus a half, from 1 to 2. So that's going to be 2 root 2 minus 2. Okay. Now if we simplify that, 1 over square root of 2 minus root 2 plus 1. Okay, and I think I'm going to leave it like that. Good, that's 95. Let's erase and do 96. The pace is definitely slowing down. I can feel my brain getting tired. 96. Okay. Integral from 0 to 2. Integral from x to 2 of x times square root of 1 plus y. Thank you guys for all the messages. 1 plus y cubed d y dx. Okay, so this is going to be difficult to integrate in terms of y, but easier with x, right? So let's maybe try to swap the order. So let's draw out our region. So we need the y equals x line, because that's one of our bounds. This is going to be y equals x. So we're going from y equals x to 2. So let's draw our y equals 2 line. And then x is going from 0 to 2. This is like x equals 0, x equals 2. So we're basically doing this region. Okay. So let's swap the order. So integral of x1 plus y cubed, but now we're going to be doing dx dy. So let's think about where x goes from. So x basically goes from 0 up until this line, which is y. So x goes from 0 up until y, and then y goes from 0 to 2. Okay, hope that makes sense. Now we can do this integral easily in terms of x, because this is basically all a constant. This is the integral from 0 to 2 of, we can just write out constant, and then the integral of x squared is going to be a half. I'll write the half at the front. X squared, that is from 0 to y, dy. Okay, so it's going to be a half integral from 0 to 2 of, if we sub in y, it's going to be y squared, and if we sub 0, it's just going to be 0. So it's basically going to be y squared times the square root of 1 plus y cubed dy. Okay, so let's do a u sub. Let's do a u sub for whatever's in the square root. So let's let u equal to 1 plus y cubed. Then du is going to be 3y squared, which we have here, but we just need a 3. So then we need a 1 over 3 at the front. Okay. So then we get 1 over 6. Integral of this is going to be, so that's all going to be our, it should be dy, yeah. So this is all going to be kind of absorbed into our du, so we basically just get u, it's the power of a half, du, or the integral of it actually. From, let's just check our bounds, so it goes from 0 cubed plus 1, so it goes from 1. Now 2 cubed plus 1 to 9. Yeah, okay. So let's work out what this is. This is 1 over 6, and this is going to be, we add 1 to the exponent, so u to the 3 over 2 times 2 over 3, evaluated from 1 to 9. Okay. So this is going to be 1 over, no, let's times it in. So it's going to be, we can cancel 1, 3. So it's going to be 1 over 9, right? 9. And then times, so that's going to be the square root of 9 cubed. Yeah. Minus 1 over 9, the square root of 1 cubed. Okay. So basically this is going to become, let's factor out, okay, I maybe shouldn't have multiplied in. So the cube root, so this is going to be 9 times 9 times 9. So you can take out a 9 squared, so it'll basically be 20, so this is 27 squared. So you can write this as 27 minus 1. So that's 26, so it's 26 over 9. Hooray. We've done question 96. Let's erase and keep moving. Ugh. (26 over 9), that's the answer, yeah. Yeah, woohoo, thank you. Thanks for the chats, always makes me smile. Okay, 97. Okay, so this is the integral from 0 to 1. Integral from square root of pi to 1 of cos of y cubed dy dx. Okay, this is a classic one. We have to swap the order because we want in terms of x so that this is all a constant. So let's draw our region. Okay, square root of x graph, how does it look? It looks something like that. This is y square root of x. So basically y goes from the square root of x up until 1. So let's draw that in maybe like that. So this is 1. And then x goes from 0 up until 1, which will also be at that exact point, 1. Okay. But now we want to swap the order, so let's write it out. So we want, I'll put the bounds in later, cos of y cubed. Now we want dx, dy. Let's think about where does x go from, okay? So x goes from 0 to this point. And if we do that, if we like find this in terms of x, we see that x is equal to y squared. Okay. So we see that x goes from 0 to y squared, and then y goes from 0 to 1. Okay. Hope that makes sense. Now we can easily do this. Integral from 0 to 1. This is all a constant. This is all going to come out, so it's just going to be an x, and we're going to times in y squared. So I'm just going to do it quickly in my head. So it's going to be y squared times cos of y cubed dy. Okay, and this is nice because we kind of have the derivative outside, so we can, this is a good example for a u sub. So let's let u equal to y cubed. So then du is equal to 3y squared dy. So if we have a 3 here, let's do a 1 over 3 here. So then we have, that's going to give us du. So that's all going to be equal to 1 over 3 integral from, we're going to check our bounds. 0 cubed is still 0, 1 cubed is still 1, and it will be of cos of u du. Okay, so that's going to be 1 over 3, integral of cos is sine of u from 0 to 1, which will be 1 over 3, sine of 1, I don't know what that is, I'll just leave it sine of 1, sine of 0 is 0, so that'll cancel, so that's your answer. Yay, that is question 97. We're getting near the end now. It's time to feel excited. Three more integrals in 2 days to your birthday. Yeah. Cool. So, let's do question 98. Let's do the integral from 0 to square root of pi over 2. Integral from 0 to x squared of x times sec, two more to go, 3 more to go, sec squared y dy dx. Okay. We could swap the order here, but I don't think it's going to be too hard to evaluate this one. So let's think about it, right? We're doing the integral in terms of y, and we know that the integral of sec squared of y, let's just write that here. We know that the integral of sec squared of y is dy is equal to tan y basically. Yeah. So that's basically what we're going to do, right? So it's going to be, I'm not going to swap order, so it's integral from 0 to square root of pi over 2. This integral is going to become x times, remember we did the integral, so it's going to be tan of y evaluated from 0 to x squared dx. So we have integral from 0 to square root of pi over 2 of x times tan of x squared, and if we sub in 0, we just also get 0, so it's just going to be that basically. dx looks very familiar. We're going to do another u substitution. So u is going to be x squared, du is going to be 2x dx. So we want 2x here, so that means we need a half here. So then we're going to get a half. Integral to check our bounds, so it'll be from 0 squared. So that squared will be pi over 4 now, because we have to square that. That's all going to be du, so it's just going to be tan of u du. Okay. Good. And we did this exact one earlier. I'm not going to redo the whole thing. But it basically gives you a half. And then this is going to be, I think we found it was ln of sec of u, right? Sec of u. And we're evaluating this from 0 to pi over 4. Okay? So it's going to be a half ln of sec of pi over 4 is going to be 1 over, so cos is 1 over root 2, so it's going to be root 2. Yeah, minus a half ln of 1 over, so cos of 0 is 1, so 1 over 1 is just 1, so that's ln, I don't need the absolute value, you can just put brackets, bracket 1. Yeah, and that's your final answer. Or actually you can simplify it further, ln of 1 is just 0. This is just going to be 0, so you can just write it. And you can just write this as like, okay, this is a bit much, but you can write this as like a half ln of 2, because you can take out the power. So you can write this as like 1 over 4 ln of 2. Brilliant. Okay, getting there. So that's question 98. Question 99, the penultimate question. Okay, question 99, what does it say? Okay, integral from 0 to ln of 2, integral from e to the x to 2 of 2xy divided by ln of y dy dx. Awesome. Okay, so this one, it looks like it's going to be hard to do in terms of y, but easier in terms of x. So let's swap the order, right? Let's draw it. So e to the x looks something like that. So y goes from e to the x to 2, so let's draw this as y equals 2. And then x is going to go from 0, that's 0, and so that is going to be ln of 2. Okay, so what area are we finding? We're going, y goes like that, so that area. Okay. And also let's write this is e to the x, y equals e to the x. So we're going to have to find the inverse. So x is going to be ln of y. That's going to be the inverse of it. So, swap the order. Integral of 2. I'm going to write it into like y over ln of y, because I'm going to get all the constants times x, dx, dy. Okay, let's see how x now goes from 0 to ln of y. Okay, 0 to ln y. And our y goes from 1 to 2, right? Because it basically starts, this point here is 1, and this point here is 2. So it goes from 1 to 2. Okay. Cool, so now let's evaluate this. So that's all a constant. Integral from 1 to 2. That's all going to just become like 2y over ln of y. And then this is going to be a half, so I'll write the half outside. X squared. Evaluated from 0 to ln of y, dy. Okay. Sub this in, so it's going to be a half integral from 1 to 2 of 2y over ln y times ln y squared. If you sum 0, it just gives you 0, dy. We can see that this ln y cancels nicely with that one. Okay. That's really nice. So now we're going to have to do, so we have 2y times ln of y. So now we have to do integration by parts. Okay. Okay, so we always like to differentiate the lns. So let's let u equal to ln of y, and du is going to be 1 over y, and dv is going to be 2y, and the integral of that is just going to be y squared. Good. Yeah. Actually, we can even just cancel out that with that, and then we can just say that's y, and then that's going to be a half y squared. Okay. So, the integral of this is going to be u times v, so that's going to be ln y times a half y squared, evaluated from 1 to 2, minus the integral of that times that. And we can see that the 1 over y will cancel with 1 over y, so we get minus a half y dy from 1 to 2. Okay, so let's sub it in. So we're going to get a half ln of 2 times 2 squared, which will actually be 4. So that'll cancel with a half, and that'll give us 2. And then minus a half ln of 1 times 1 squared. So that's actually going to, ln of 1 we know is 0. Okay, minus a half. Integral of y is a half y squared from 1 to 2. So it's going to be 2 ln 2 minus, so it's going to be 1 over 4 times 4, so minus 1. And then if you sub in 1, it's going to be plus 1 over 4. So it's going to be 2 ln 2 minus 3 over 4. Okay, we have final integral to go. And this integral was actually sent by Jason. So I'm going to do the last one. Okay, so let's have a look at Jason's integral that he sent. Number 100. See, I'll write a bit bigger for the last one. Well, it's just quite hard to fit everything in, that's the problem. Okay, final one. Hope everyone's excited. Number 100. Okay, and this is sent by Jason de Villiers. So let's have a go. Let's see what he sent me. So he sent me the integral of the integral of the integral of the integral of from 0, all of these are from 0 to 1, of x plus y plus z minus w over x plus y plus z plus w, and then it's dx, dy, dz, dw. So this is crazy. This is a quadruple integral. How insane. So we can, what I'm going to do is I'm going to write this in a certain way to split it up. So I'm going to write like plus 2w minus 2w, okay? Because you see those cancel out. But then this part with the plus 2w, that's just going to equal 1, okay? And let's think about it. We'll basically have integral of 1 dx, dy, dz, dw. And then it'll be minus. I'll take out the 2. Integral of w over x plus y plus z plus w dx, dy, dz, dw. Let's go. Okay. So let's first have a look at this thing. So, let me put it in balance actually. They're all from 0 to 1. 1, 1. 0, 0, 0, 0, 1, 1, 1, 1. Okay. So let's think about this. If you're doing the integral of 1 in terms of x will be x, and then from 0 to 1 it'll just give you 1. And then it'll all actually end up giving you 1. So this whole thing will just evaluate to 1. This whole thing just evaluates to 1. Okay? So all I'm really going to worry about is that thing now. So one thing we can say is, one thing we see is that there's no letters as the bounds, right? So we can swap order as much as we want. And another thing is that these letters are just dummy variables, right? So what I can say is, I'm going to say that I is equal to, I'm just going to write it as integral 0 to 1. I don't know the notation. I just want to write the integral 4 times. So I'm just going to write something like that. Okay. Of w over x plus y plus z plus w dx, dy, dz, dw. Okay. And we can say that that's equal to 4. We can say that's equal to, like, for example, x over x plus y plus z plus w dx, dy, dz, dw. And the reason that these are actually the same is because, for example, imagine it's a w variable, right? So imagine I change w to x and x to w, right? And then we can swap the order to make it back to this order because all of these bounds have constants, okay? And we can do it similarly for, let me actually write it. We can do it similarly for the other, so we can say 0 to 1 of y over x plus y plus z plus w dx, dy, dz, dw, and then I is equal to integral 0 to 1, I'm just doing it for like 4 dimensions, of z over x plus y plus z plus w dx, dy, oh, I'm covering a little bit, sorry, dz, dw. Okay. Now what I'm going to do is I'm going to actually add all of these together. Add. Okay. Because we see if we add all of them, we're going to get w plus x plus y plus z over w plus x plus y plus z. So we're basically going to get 4i is equal to, and it's this integral 0 to 1, 4 of 1 dx, dy, dz, dw. So basically this thing here is basically the same as 1 over 4 times that. Okay, so that kind of, I'm just showing how they link, like that comes from that. Okay? And we already showed that this is equal to 1. So therefore, we call this equal to I. So therefore we said I is equal to 1 over 4. Okay, we're almost done. So now, our overall equation, our answer, I'll call it, our answer is going to be 1 from here minus 2, and we said this was I. So minus 2 times 1 over 4. So 1 minus a half. And the overall answer, we write it nicely, is a half. And we're done! Hey! Thank you so much.
Yay! Well done.
Hey!
Woo!
We got some sparklers. Very cool. Let me show. Mom and sister bought me some cool sparklers. Thank you guys.
Well done, James. Very
Hey,
inspirational.
hey. 100 integrals in one
Finally
day.
done.
Yeah, that is a lot.
Yeah, well done.
Hey, thank you.
So proud of you.
Did you enjoy the video?
It was really interesting. I learned a lot.
Very cool.
Yeah.
Oh, that is 100 integrals in a single day. Let's go.
Well done.
Let me just finish up and then I'll come. Okay, awesome. Thank you so much for watching. That is 100 integrals in a single day. Yeah, we had quite a tricky time. There were some easy ones, there were some hard ones. I really hope you guys enjoyed. Just under 8 hours, so not too bad. Yeah, it was a really fun experience. I'm tired. I think I'm gonna have a good sleep tonight. But yeah, that's 100 integrals in a day. Just a reminder, this was a charity live stream for Choc. So if any of you guys are watching and you'd like to donate to Choc, you can ask for the link. I'll send it in Twitch chat, and it's also on my WhatsApp story. So yeah, thank you all for watching, and have a good rest of your day. Cheers. Bye.